All right, hello everyone. Thank you for joining us today for the AIAA Los Angeles section um, Planetary Asteroid Exploration mini conference. Actually, we hesitate to call it mini conference again because we're kind of growing and it's getting bigger. So today, actually, we have 150 people registered, but mostly online. That's the dilemma after the pandemic. But I'll try to be short. So welcome everybody here in person, also folks online. So if you're here, you have the wonderful coffee and the refreshment on the back. At lunchtime, we have the sandwiches. We don't have a lunch break because we have a full schedule. We don't want to make it 2 days this time, hopefully next year. So the program will keep going, but if you have sandwiches, think you're welcome to go anytime to grab the sandwiches. So first we'll have to thank Mr. David Ramirez. He's a teacher here, the director of STEM education. He offered this wonderful meeting room and set up students. So let's give him a round of applause. Thank him for his great effort. Thank you. Thank you. Yeah, he has a wonderful. You can see beautiful program and facility here. Do you want to say a few words? Okay, maybe later on. So I'll be quick. And the second thing I want to thank is Mr. Bill Maloney. Initially, he's one of the speakers at lunchtime, but he finally cannot make it. He didn't feel very well today. But we thank him for the generous donation. So the sandwiches, thing is thanks to him for the generous donation for the support. That's really highly appreciated. And of course, we also thank all the volunteers here. Dennis, do you want to say something? Okay, Dennis is our career workforce development. He's a retired director from Northrop Grumman. So he's very knowledgeable, very helpful for education and support. So without further ado, let's start the program. So let's give the mic to Dr. Nahu Mena, who is the overall lead of this program. He's also the moderator for today, and he is the mastermind behind all this program. Thank you, Dr. Mena.
Thank you, and good morning to everyone, both in the room and online. Today I'm going to support it remotely. I'm not going to talk too much because we have a full agenda that was organized by Ken. So many thanks to Ken for the hard work in the last few months organizing that event, which is an amazing event about planetary defense, probably semi-unique in the region at least. I see there is plenty of participants in the room. So good morning, everyone. Hey, Paul, is this you? Wow, good to see you. Sorry about remotely. So we are going to have a full agenda today. I've been involved with planetary defense for over 10 years, working at the Aerospace Corporation. And most recently, I've been involved with organizing the international conferences that are held every other year somewhere around the world. The next one will be held in Montreal, Canada, and I'm sure that we are going to talk about it further during today's event. We are introducing a new element today in the afternoon, which is an asteroid deflection contest. We are going to divide into teams. I assume that has been done. And we are going to try to deflect an asteroid and see how the different teams get the idea of deflection of an asteroid and who is going to be the winning team. So I think without further ado, I believe that Andy Rifkin is waiting online to support the first talk. I'm going to give it to Andy, and we are going to convene in the afternoon with a panel and a competition. So thank you everyone for joining us today. And Andy, take it away.
All right. Hopefully folks can hear me. I don't see anyone nodding, but I guess I will just assume that if you can't hear me, that someone would say. So
we can hear you well, Andy, so go ahead.
Thank you. And it looks like a good crowd, so I'm happy to lead this off today. Hello from Maryland, where it's a little cloudy outside. I think we're going to get some rain. Hopefully it's better out there in California. So I'm here to talk about planetary defense after DART. What have we learned and what comes next? And of course, part of the reason we're doing this is because Asteroid Day is coming up. This is new. I figured I'd post a screenshot here that I think just a day or two ago, the U.S. Senate unanimously resolved past this resolution, kind of agreeing that June 30th is 2026 is Asteroid Day. So this, of course, there's a UN ongoing. I guess it would be a General Assembly resolution that that June 30th is Asteroid Day. So again, this is what brings us here. And part of the reason that people are interested in asteroids, in asteroid impacts, is because we've seen some in the, in our recent past. This is a map of the Earth. This each dot shows a place where a fireball or a bolide or and basically an impact has been seen by, it says U.S. government sensors, so satellites looking down on Earth looking for flashes. The color of each circle corresponds to the energy of the impactor, and that gives us a sense of the size of that impactor. That large circle there is Chelyabinsk, which is a city in Siberia that was hit by an impactor in 2013. Happily, the impactor broke up in the atmosphere, so there was not really it didn't make it to the ground intact. But I'm sure you've all seen videos of shockwave coming over the city and windows breaking after this impressive fireball. And then there on the right, as I said, is kind of a scale bar showing how the colors correspond to energies. I also then put kind of the size of an impactor that might make an impact, might make and give you an energy of that particular color. So a lot of these are small, maybe only a meter or so in size, either rocky or metallic. Every year or so, we get hit by something like 4 or 5 meter size impactors. And then the larger the impactor, the more infrequent it is, as I'll talk about in a slide or two. So just to give you a sense of scale, I was wondering this earlier this year and thought I'd work out the math. So firecrackers, these are firecrackers that, at least in some states, you can just go and buy and set off. I think M150s are kind of the biggest ones. And so the question I will pose to you, I guess you can think about as we go through this, is what size of an impactor you think would it take to give you the same energy as you get from a firecracker? And hopefully none of you have had mishaps with firecrackers, but we all, again, every year around this time of year, hear about people who maybe were not as careful with firecrackers as they might be. So 50 milligrams of gunpowder is kind of the legal maximum in most places, including in the US. And if you multiply the energy density of a gunpowder versus the amount of gunpowder in a firecracker, you get a particular energy. This is 3 megajoules. I'm sorry, 150 joules per firecracker. For those of you that are happy with metric system. The way that we determine the impact energy of an impactor is just basically to say what's the mass, what's the velocity, and do a equation that is again familiar. Hopefully, most of you have at least seen this at some point in your school, even if that school was long ago. 1/2 mv squared is the kinetic energy. And so if you go through the math, which I will mostly save you, basically you end up with a grain of salt. If you have a grain of salt hitting the Earth's atmosphere, it brings in the same energy as one of these firecrackers. For the Earth, all of these burn up in the atmosphere, so that's not a big deal. But you can imagine if you were on the moon, say, every time something of the grain of salt hits the surface of the moon, you get the energy of a firecracker. We don't worry about these small ones again because they burn up in the atmosphere and we go out and we see a meteor shower and those are very pretty. So it's the bigger ones we kind of tend to worry a little bit more about. An impactor that's about 4 meters in size happens about every year. 4 meters is, you know, well, it's 4 meters. It's 12 feet or so in diameter. Those burn up in the atmosphere. You get a great big flash. You'll see a fireball. some of the pieces might make it to the Earth as, kind of fist-sized rocks, but they really don't do any damage unless you happen to be underneath a rock that falls on you. That's not so great. But in general, we're not worried about objects that size, which is good because there's 500 million of them or so out there, we think, and we have only discovered a very tiny fraction. At the other end of the scale, uh, I'm sorry, just a little bit bigger, this 25 meters. This is about the size of that object that hit Chelyabinsk, as I said before. Those maybe happen every 100 years or so. We think there's about 5 million of them out there. We have discovered very few. Um, but again, they're not great if they're going to hit the place you are, the city you're in, but mostly because you might get hit by broken glass, something like that. You'd like to know if one is incoming, but it's not going to, it's not going to be a sort of thing that is going to have more than very local effects. On the other end, you get something like the impactor that killed the dinosaurs. Um, that is caused by asteroids, we think, about 10 kilometers across, so about 6 miles. Um, this would be this would be a mass extinction event if when they happen. And they have happened before in the past on the Earth. They have profoundly affected the evolution of life on Earth. Um, we don't think they happen very often, maybe every 100 million years or so. Perhaps more to the point, we think that we have found all of the objects big enough to cause a mass extinction on Earth. We know where they are, so we think we're pretty in good shape there. None of them are gonna hit the Earth in the foreseeable future. So that kind of leaves these next two columns as where um, work and attention has come for planetary defense. That next size down, 1 kilometer in size, we think that those are big enough to really give human civilization a hard time. We think maybe they happen twice every million years. They would certainly make it to the ground intact. They would make a crater about 10 kilometers across, but the global effects would be much, much worse, given the amount of debris put in the air, which would change the climate. There would be just devastation due to a fireball upon impact. So it would be bad news. Um, we think there's about 900 of them out there. We think we've found 95% of them, possibly more. There are some arguments that we've actually found closer to 100%. Um, again, once you start to then run the numbers and say they happen twice in a million years, but we found 95% of them, so the odds are good that we are not going to have to worry about this in a much, much longer time scale than a million years. So 140 meters is kind of that middle slot there. Um, these are, as you might imagine, not as bad if they impact as the 1 kilometer objects. They are much worse if they impact than the 25-meter ones. We think they happen every 20,000 years or so. They would create a crater. They would not necessarily have global devastation that they'd cause, but if one of them hit in um, Phoenix, you'd worry about it in LA, I think. And so they would potentially have regional effects. We think there's about 25,000 of them out there. We think we found about half. And that is a size at which NASA and planetary astronomers and planetary scientists around the world have decided that's the size we need to find objects at kind of 140 meters and larger to as a goal of what we're trying to do. So the good news is, for the first time in human history, we can actually find these things and predict if and when they might occur, and then actually do something if we find one that's on the way in. So planetary defense really is that. We have the capability to determine if an object is on an impact trajectory with the Earth. We have the capability to characterize potential impactors and the population they're drawn from. We have the capability to determine, okay, if such and such an object does hit the Earth, what would be the consequences? And what if it hits the ocean instead of land? What if it hits this part of land instead of that part of land? This city instead of that plain? we have the capability to prevent some impacts. We have the capability to minimize the consequences of impacts, even if we can't prevent them. So all of these things together, along with the engineering it takes to carry them out, with the international agreements that are made between countries to do these studies and do that engineering, and then the policies of deciding when to do these things and how to do these things, that altogether is basically what planetary defense is. This is a famous chart among those of us that work in this field. This is put out by the NASA Planetary Defense Coordination Office, and it shows the different aspects of planetary defense. In principle, one could read this as a clock, kind of going around from search, detect, and track to characterize, to plan and coordinate, etc. But in reality, all of these different sectors are being worked on by people at once in different ways. So the one I'm going to focus on mostly for the rest of the talk is in this mitigate sector, which is where the DART mission, the Double Asteroid Redirect Test, falls. But I will touch on some other aspects of them as well. So the overall point of mitigation, you really only have a problem if an asteroid and the Earth are going to be in the same place at the same time. If they are not, then it's maybe something of interest, something that can be seen as a warning, metaphorically. But you only really have a problem if they're both going to be in the same place at the same time. So the Earth is a particular size, 12,700 kilometers in diameter. It's moving through space in its orbit around the sun at 30 kilometers a second. If you take one, you divide by the other, it takes 7 minutes for the Earth to move its entire diameter in space. So the easiest way to avoid an impact or to prevent an impact is if something is coming in and is going to hit the Earth, if you can either speed it up by so it arrives 7 minutes earlier than it would have, or delay it so it arrives at least 7 minutes later than it would have, then you're fine. The way the math works out, it's a lot less like a goalie. It's World Cup season, so I guess we'll use soccer. A lot less like a goalie kind of batting something out of the way, and a lot more of two trains that are on intersecting tracks where you can control the speed of one of the trains and not the other. So the earlier that you can start this mitigation process, the earlier you can start changing the arrival time of an asteroid, the smaller the speed change you need. And you can imagine that if you, again, to use the trains, if you have two trains and you realize that they're going to arrive at the same junction, the same intersection at the same time, how much you need to put the brakes on depends on when you figure that out. If you realize it an hour ahead of time or 3 hours ahead of time or the day before, you can very, very trivially change the speed of the train, of one of the trains, and have it arrive at different times. If you realize it 10 seconds ahead of time, obviously you're going to have to really pull the brakes on one of the trains a lot harder. So similarly, if we know that an asteroid is going to hit the Earth and we have 30 years of warning, we have a lot more options. We can do a lot more things. You don't need to change the speed as much as if you realize it 6 months ahead of time. So early detection is really important. And here we have the potato missing the Earth. Here on the right is a picture of the asteroid Itokawa taken by the Japanese Hayabusa spacecraft. And it's pretty typical of what we think asteroids are like. We think that they're rubble piles, as we call them. They're not just one big rock sitting there in space, but we think they're collections of rock and gravel and pebbles that are all held together by self-gravity. So that means that we can't give an arbitrarily hard push to an object without it coming apart. I know that you don't get a lot of snow down there, but those of us who grew up in snowy climates know the kind of different ways that you can pack a snowball and throw it, and how hard you can throw a snowball based on how well you've packed it. So we don't want to disrupt a rubble pile asteroid by pushing it too hard. And there are discussions about how hard too hard really is for the asteroids we're thinking about of that 140 meter size, so 100 meters, 200 meters, 300 meters. That means we think that the the hardest push we can give it is to change the speed by a few centimeters per second or less. So I talked about this. This is in part why we need to find things as quickly as possible or as soon as possible. This shows different mitigation techniques. This bottom axis is years until impact. This y-axis is the size of the object, and depending on the warning time you have, there are different techniques that will work better. And as you get less and less time, you start to move from deflection into disruption, into breaking them apart, because you're just going to have to push them so hard that they are going to break apart. So you might as well try to do it in a controlled manner. So what we, over the years in the community, realized we wanted to do is test one of these techniques, the so-called kinetic impactor technique, where we have our spacecraft come in and whack into an asteroid to change its orbit. So it was realized that by doing that, if you're going to do that for an asteroid that just goes all by itself around the sun, you probably need a second spacecraft to make precise measurements to see what you've done, or alternately, you need to wait a long time to see how the asteroid is moving. But my colleague Andy Chang at the Applied Physics Lab, where I am, realized that you could do this easier if you went to a binary asteroid system. This on the right is the Masha-Squanut asteroid system. This is a model of the system made with radar data by, I think, of Steve Ostro et al. And it shows the two bodies in the system. So some fraction of asteroids have moons, and if you change the orbit of a moon around the main asteroid, it takes much less time to see the results. And you can do it without a second spacecraft. If you pick the right asteroid, you can do it with telescopes on the ground. This kind of shows why and what we did. The top panel shows what's going on if you were close enough or you had a powerful enough telescope to see the moon going around the asteroid. But from the Earth, it's far enough away, and these are small enough that you would only see that as a single point of light. What we would get to see is on the bottom there. This shows the brightness of the system changing as the moon puts a shadow onto the main body and goes into the shadow of the main body. So by watching the brightness of the system go up and down, you can measure the speed of the moon around the main asteroid. You do that you do that well before you impact it. You do it well after you impact it, and that will tell you what you've done to the system and how you've changed the speed of the asteroid. So that is what we did. This is the double asteroid redirection test. All of those pieces then are there. We have the double asteroid, the Didymos Dimorphos system. We redirect it by changing the orbit of the moon, and then it's a test. We're not doing this because it's an emergency, but to see how this would work out. We launched in November 2021. We impacted in September 2022. We carried CubeSat from the Italian Space Agency and made measurements from that and also from Earth-based observations, both on the ground and in space nearby. So I'm just gonna. I've talked about DART before. Hopefully, you've all heard about DART and you know about DART. So now that hopefully we've got some setup, I will go through what DART did more quickly than I normally might. We launched again at a time when Didymos would be close to Earth at the impact time. DART's orbit stayed very close to that of the Earth's. This is looking down from above, kind of at an angle, so that's the sun in the middle. And you now see DART heading toward Didymos. I grew up in New York. Of course, I was watching the Knicks. So those of you who are basketball fans might see that DART actually drew a charge. DART did not foul Didymos, but drew the offensive foul from Didymos since DART was there in position. This shows the last few minutes of DART. Again, I don't know if some of you might have seen this live. This is sped up by a factor of 10, except for the last 6 images, which come in real time. So there's the main body, Didymos. We're getting close to it, and it's starting to move out of frame as Dimorphos gets bigger and bigger. Um, and we were aiming for the center of the lit part of Dimorphos. And here in these last few images, we hit, you know, we hit right on. This shows to scale. I put the cruise ship in there. So you can see it's not a huge system, we're used to in planetary science, things like Jupiter, images of Jupiter, and in astronomy, the sun or the galaxy, which are unfathomably big. So this is a very small system. You could easily walk from one to the other if not for the fact that they're in space. You could almost certainly jump from one to the other, although I wouldn't recommend it in case you missed. This shows that landing site up close. DART uh, ended up impacting between in the middle of this cluster of rocks. Um, to give a little more context or scale, because this to me, I'm an astronomer, it looks like a bunch of rocks. I can't necessarily tell beyond that what I'm looking at. This compares the impact site of DART to the LAX parking lot at the same scale. So you can see that a lot of the rocks at the DART impact site could easily have fit in the room with you, even the largest one. Probably could have fit in the room without too much trouble. Um, I don't know that it's necessarily drivable. I feel like there's maybe a path you could follow if you had a good enough four-wheel drive vehicle. But again, this kind of is gives you a sense of what that asteroid is like. We had a CubeSat contributed by the Italian Space Agency. The CubeSat is you probably know about CubeSats. It was about the size of a cereal box before the solar panels were deployed, and that's a rendition of it up there in the right. This goes fast. I'll try to re-show it a few times, but this is what LichaCube saw. LichaCube was deployed a couple of weeks before the DART impact, deployed by DART, and followed DART in. It didn't impact, but flew through the system, taking images of what had just happened. So here, what you see is Didymos is the upper left body. This kind of splash in the lower left is Dimorphos plus all of the debris, all of the ejecta coming off of it, and you're going to see LichaCube fly through the system. So I'll do that again, and maybe I will kind of drag through. So here it's getting closer, and you can see the debris making these beautiful rays, these beautiful lines um, as it leaves the system. Here's kind of our closest approach. Um, the Italians did an amazing job with this. This was a really innovative first time thing. So they were not, their system tracked on or tried to stay on the brightest object, but it had to turn really fast. So it was unable to keep Dimorphos in the frame the whole time. It got back, and you can see this dark halo around Dimorphos, between Dimorphos itself and the ejecta, and that we think is where the debris is so thick that it's casting a shadow. So there it is again. Let's see. Okay, and then within the debris there were larger pieces. Uh, some studies found a couple of dozen boulders a meter or larger in size that were ejected. And you can remember this. We'll talk about this in a little bit. Here's on the right, superimposed kind of the DART spacecraft are these white boxes, um, and then it shows where the solar panels struck two of these rocks. which we think, this is a paper by Tony Farnham, we think that these two rocks then got broken up by the impact and gave rise to these clusters of boulders that are circled on the left. Once LiCHA got through the system, which didn't take very long, the telescopes here at or near the Earth took over. We had telescopes on every single continent that took part, and this is everyone who took data, whether or not they were associated with the team. There were a number of spacecraft which were lined up there on the right that also took data. The first thing that happened was we had this shell of material, this vapor cloud come out, which we were not expecting, which we think is just due to some initial dust that just got knocked off very, very fast before the rest of the debris made it. This was seen by everyone, every telescope, everyone that was looking, every camera that was pointed at the time saw this. This initial ejecta that came off very fast, and then things settled down to kind of a slower ejecta coming out. And that slow ejecta eventually made a tail. So I study asteroids. I have lots of friends and colleagues who study comets. If I want to get them all worked up, I say that, we made a comet. This is a comet. And they tell me why, no, this is not a comet. But if no one knew that we had done this, people would suddenly say, oh my God, it's a comet. So all of the debris that DART made got swept backward by the solar wind and other processes, and made a tail that was tens of thousands of kilometers long, and it lasted for months and months. So Dimorphos itself, which is where this debris came from, is roughly as big as the vehicle assembly building down at Kennedy Space Center. So it's a big building, but it's a building. Again, this is kind of a human-sized system. You can imagine how big this building is. You can see cars. The tail stretched, again, tens of thousands of kilometers. This is obviously not really where Didymos was, between Earth and Moon, but just to show the scale. And then the amount of ejecta, so the amount of debris that actually made this tail, we think could fit in just one of these tanks. And again, it's a big tank, but it's not that big. There's a bulldozer. So we kind of knew from numerically what we were expecting from this impact, but none of us had seen on the sky what it would look like. So I think to the extent that we were surprised, it's because we didn't have a good way of visualizing what putting this much dust and gravel, into space, stretching this distance would look like. So again, this was actually the measurement we needed to make. We needed to let the ejecta and debris clear for a little bit before we could make these measurements. But when we did, we saw these dips. In the real data, these are just blow-ups on the bottom, zoom-ins on the bottom of the data we took over a course of a couple weeks on the top. And we saw these dips in places that showed that we changed the orbit of Dimorphos. We changed its speed by something like 3 millimeters a second. All of our publications are open access by policy, so we made sure that the public that we got to bring the public along, that the public who paid for this and are interested in this get to see the results if they want to see the actual science results. So those QR codes will take you to our pre-impact predictions and our post-impact results for at least a couple of journals. And I'll show this again at the end, I think. At least I will make sure to. So some new results that have come since then, just within the last year or so. So there are occultations. I don't know if you're familiar with occultations. Basically, occultations are like eclipses, except instead of the moon moving in front of the sun, it's some solar system body moving in front of a distant star. So there were several occultations by Didymos that have been observed. The paths are very, very narrow, just like for eclipses. You have to go to the right spot, be within the right shadow path to see a solar eclipse. You have to be within the right path to see a occultation. For occultations, these paths can be very, very narrow, or maybe only a matter of a few hundred yards wide. On the right, this just shows the map where a few of these were visible over Australia in 2024. Um, if you can observe them, then that gives you great positional knowledge of the body that you are looking at. Because these paths are so narrow, um, we can't necessarily predict really well where they are. So being able to see one means that you now know the relative position of the Earth and the asteroid and the star really, really well. And by doing that, you can very quickly improve an orbit. So the result of these occultations, we got two really interesting results. First of all, we actually were able to measure the change now, not just in Dimorphos's orbit around Didymos, but in the Didymos system orbit around the sun. We did not think we would be able to make a measurement that precise, but thanks to these occultations, we were. And so we changed the speed of Didymos by 1/100th of a millimeter per second around the sun. That sounds very small. That is very small. We changed the heliocentric orbit of Didymos by 2 kilometers. And that's out of 245 million kilometers. So a tiny, tiny change. We changed the orbit period by about 1 second out of 770 days. So we knew there would be this tiny change. You know, full full credit, great job to the people who made these measurements, who got out with their telescopes, who made the predictions that let those people go to the right places. Um, and so that allowed an independent calculation of how effective the kinetic impactor technique is. Um, and it also allowed us to make an independent measure of Dimorphos's mass and density. That's shown here on the right. The circles are measurements we had from other asteroids that are similar to Didymos and Dimorphos. The stars are the measurements made through this work of Didymos and Dimorphos, and they are pretty typical. Didymos is typical of the larger objects, and Dimorphos is maybe typical of some smaller ones, which is not a surprise, but a good thing to actually measure. There was a change in Didymos's rotation period. Didymos is spinning very, very close to a speed where it would start shedding material because it's spinning so fast. Um, People looked prior to the dart impact at the consequences of what happened if some of the ejecta coming off of Dimorphos actually hit Didymos, and there was some thought that because Didymos is spinning so fast, if material hit it, it might cause massive landslides and really reshape Didymos. Um, this this shows on the right how a reshaping of Didymos could be measured remotely because the rotation period would then change. Um, and this dotted dashed line shows the limit of what we thought we can measure. We thought a change above that line is something that we could measure. We thought a change below that line maybe not so much. Um, and a change was seen. This group of data points on the left shows the rotation periods measured before impact, and this group here on the right shows the rotation measured after the impact. And it's only about 2/10 of a second uh, that was changed, but that 2/10 of a second was enough to be measured, and it's clearly a different measurement between before and after. And so if you go back over here and you say 2/10 of a second means that you changed the size, the polar size, polar diameter of of Didymos by about 1 centimeter. That's also pretty tiny. Um, it's more likely that there was a larger change over a smaller area, and we will see soon. One other more general result is that bigger is not always better. So beta is the change in momentum that Dimorphos experienced compared to the momentum brought in by DART. So having that number be greater than one means that the debris carried away some extra momentum and gave an extra push. The ejecta that moves directly away from Dimorphos does most of the work. But as you saw, particularly in some of those pictures with the boulders, there was a lot of debris that moved kind of sideways, either mostly sideways or at least a little bit sideways. And moving sideways doesn't help in this way. So Hirabayashi et al. Um, did a study, which this kind of shows on the right, comparing what if instead of one big dart, what if you had a couple of smaller darts or a number of smaller darts, and depending on the shape of the object and how round it is versus how many flat areas it has, it may do more good to send in a bunch of small objects, which will minimize the amount of sideways push that doesn't do you any good. But that potentially has other issues. So it's not this is the sort of thing that's still under study. We're still obviously these papers are from last year, so obviously this is still being looked at. So some key planetary defense results that we summarized. There was a paper that Nancy Chabot and I put out earlier this year. Basically, a kinetic impactor can deflect an asteroid. The efficiency of the deflection depends on the asteroid's properties. Warning time is key for utilizing the kinetic impactor technique, and then international and interdisciplinary cooperation really benefits planetary defense efforts. So that's the DART. What have we learned now? Kind of quickly turn to what comes next. The first thing is Hera. Hera is a European Space Agency mission that is going back to Didymos. Here we have an artist's rendition at the top, and then at the bottom are a couple of images taken by Hera of the Earth-Moon system at different wavelengths as it was leaving. It will arrive in just a few months at Didymos. It carries cameras, a spectrometer, an altimeter. There's a Japanese thermal infrared imager. It has its own CubeSats, one of which has a ground penetrating radar. So it will land on Dimorphos, and their goals are to really measure the after effects of the DART impact. And unlike DART or LiChaCube, it's going to rendezvous. It's going to go into orbit. It's going to stick around for a while. And this shows the different phases of Hera. Again, these different phases that it moves through, which is typical for an asteroid mission. Kind of start far away, learn what it would take to go a little closer safely, and then as time goes on, to do more and more riskier things, but riskier things that you have learned to do from the data that you took earlier. It launched October 2024, just days before Hurricane Milton came in, which was kind of a wild, we had a wild time with that. And together with DART, Hera will kind of be the other bookend, will be the other parenthesis that will give us this comprehensive look at the Didymos system and let us get the most out of this impact experiment that we did. There are other things going on. Oh, I guess I do have one or two more slides on this. Hera had a Mars flyby last year and looked at Deimos. This is now the Martian moon Deimos in black and white and in color here on the right. And this is one of the few times that spacecraft has seen this side of Didymos. Usually spacecraft in the system are closer to Mars looking outward. There are just a few more things for Hera to do. There's a payload checkout coming out next month. And then the arrival maneuver is in October, and then early characterization phase begins in November. So again, it's going to be there very soon. I've talked about how early warning is important. And so that means that surveys looking for asteroids retain kind of a really central place and a central importance in planetary defense. There are currently um, 4 surveys that are funded by NASA that are looking for asteroids that do the bulk of the work, but there are more that are coming online. The Vera Rubin Observatory has had first light. Their survey should begin practically any time now. Um, it's a gigantic mirror. It's an 8.4 meter primary. Um, which is it's one of these. It's not the huge ones in the back. Um, and I shouldn't spend too much time kind of hunting around for it. But basically, it will be taking um, it has a 3.2 diameter field of degree diameter field of view, 3.2 gigapixel CCD, 30-second exposures, 6.4 terabytes uncompressed per image, and then 200,000 images per year. So this is a tremendous fire hose of data that's going to be coming in. Um, and then the software is set up to look for changes in these images compared to whatever is in their archive. So they expect up to 10 million alerts per night of, hey, something's changed, something's changed, something's changed. And they will produce an annual catalog of 37 billion stars and galaxies, and then 6 million solar system objects with orbits. And we think this is going to play a major role in completing the survey down to 140 meters. I said back at the start, only about 45% of objects that size had been found. That will be improved significantly by the Rubin survey. You probably can't read that top, but here on the bottom, this red line is NEOs, and they expect to get all by themselves something like if I'm reading this right, something like 45% of these asteroids to that size. They will be augmented by a spacecraft that will be launching within the next few years, the Near Earth Object Surveyor, um, which is a planetary defense mission. It will look in the mid infrared. It will look in a different part of the sky than the Vera Rubin Observatory will. And together, over the course of the next 10 years or so, we expect that those two efforts will get us to 140 meters. And NEO Surveyor should launch again sometime this decade. I think September 2027 is what we have right now. There are additional recommendations because things will go on, hopefully, after 2027. The National Academies facilitates a report every decade that prioritizes goals for planetary science. And it included planetary defense for the first time in 2022. So the first recommendation is for a rapid response flyby reconnaissance mission targeted to a small NEO, 50 to 100 meter diameter, which are the objects that pose the highest probability of an Earth impact that's big enough that we care about. So they recommended that as the next planetary defense mission after NEO Surveyor. And then after that, they suggested 3 possible candidates, including a characterization tour or perhaps another DART kinetic impactor test on a different kind of target, or a demonstration of some other mitigation technique. One of the more gradual ones, like ion beam deflection or gravity tractor. There are other things coming up. I should mention there are a couple of space asteroid missions that are already happening. Hayabusa 2 is a Japanese mission that is going to an asteroid called Torifune. That's going to happen in like a week. The Chinese have a sample return to a quasi-moon of the Earth, which is so technically an NEO, called Kamo-Oolewa. That is also potentially going to happen like next week. So we have a few big things coming up. In early July for international missions. 2029, the asteroid Apophis makes a very close approach to Earth. I'm sure you've heard about it, or you will hear about it a lot today. Um, and on the right there shows an animation of how we think this is going to go. Um, Billions of people will be in the region where it will theoretically be observable to the naked eye. In practice, things like weather, light pollution, topography, obstructions on the horizon will reduce that number, but still a lot of people will potentially be able to see this naked eye. And studying it will help us understand how asteroids interact with the space environment and how they react to close planetary passes. There are a few um, spacecraft that should be there, that we expect to be there. The Ramses mission by the European Space Agency is planned for a rendezvous. The Destiny Plus spacecraft, which is Japanese, is planning a flyby before Ramses. The NASA Osiris Apex mission should be there, budget permitting. There's been some back and forth about that. There are additional spacecraft encounters possible, including some CubeSats. You'll hear about one from the University of Maryland soon. Just a few talks after me, I think. And then a Chinese small sat may also go there. Maybe there will be others. Um, and all of this is, of course, possible. I mean, we've talked about this in terms of spacecraft and telescopes and kind of separating it from the human element. But of course, this is the DART team. It was a great team, of course. I'm going to say that, but they really were an international team, 300 plus people from 29 different countries. And that's also what planetary defense is. It's people, including some people in that room with you, um, whether or not they've retired, who have been working for to make these things happen. These things don't happen by themselves. It's people that do the research, people that do the engineering, people that come up with the mission plans and the budgeting. So we are all in this together, in all senses of the term. And as partially recognizing that again, the United Nations has announced that that 2029 is the International Year of Asteroid Awareness and Planetary Defense. We're calling it Asteroids 2029 for short because the other thing is a real mouthful. Um, and the U.S. node for that UN effort will be at the Applied Physics Lab, where I am. So you'll be hearing more about that. We're just starting to reach out to institutions to collaborate and be part of this. You can scan the QR code for more if you like. But again, this is all part of a multi-year effort so that folks can understand planetary defense and asteroids and asteroid science a bit better. So that's the end of what I have. I don't know if I have time for questions. Hopefully I do. And thank you.
Thank you, Andy. Can you hear me?
Yes.
Okay. Fascinating talk. Thank you so much. Every year that we hear you, we learn a few new things and also about the upcoming plans. Ken, do we have a few minutes for a question or two?
Can you hear me?
Yes.
Yes.
Yeah, a few minutes, okay. Professor Lubin is waiting though, so maybe a few minutes.
Okay. So are there any questions? What kind of math is needed to perform well in your job type? It's a question from a student, I assume. Andy, you can inspire
What kind of math is needed? Yeah, sure. So of course we're entering this new age of machine learning and all of those things. It's different from when I was in school back before the turn of the century. But I think what I would suggest is having a good kind of sense of ballpark figures, being able to kind of realize in your head, okay, a 20-meter asteroid is going to be this massive compared to a 300-meter asteroid. Something coming in at 10 kilometers a second. What does that mean if it's, how fast does something moving 10 kilometers a second go in a year? Being able to feeling comfortable with doing that kind of calculation roughly, not getting the exact answer, because you can always, use a spreadsheet or use something else, a calculator to do that. Um, and then writing, actually, and again, in this coming day and age, I don't know how writing will be affected, but we do a lot more writing than you might think.
Thank you. I don't see any other questions, but I have a quick one, Andy, and it is, I think that the amount of deflection that was predicted for DART prior to the event was different from what was observed. And so what would be the main takeaway from the observed difference?
Yeah, it's funny. I think if you go to the papers, we the amount that it got deflected was within the range that we had predicted. It's just that we had talked ourselves into, we had to plan for the most difficult case. And the most difficult case was the least deflection. And I think being human, in the course of doing all the planning for the hardest case, for the least deflection, we were surprised that we got a lot more, and it was much easier. So, but this beta factor that, of course, I know you know about. The papers said, well, it could be somewhere between 1 and 5. We have reasons to think it's between 1 and 5, and it's between 1 and 5. But we were planning for 1 because that was going to be the toughest case. We think that Dimorphos is much weaker than a lot of us predicted, so just physically much weaker. Um, but that was assuming a density, and now it looks like maybe the density is lower than we thought. So I think we're going to get a lot of answers from Hera that are really going to be helpful in putting those pieces together.
Great. In my mind, it tells me that if an object is discovered potentially with a collision course into the Earth, and you have enough time to do a proper characterization, that would inform any mission that you might create for either deflecting it or doing something else. So characterization becomes super important for designing a mission.
Yep, totally agree.
Okay, let's see. What time is it now? It's 9:05. Let's see, one more question here.
Dr. Miller, can you hear me?
I can.
There's a attendee here. He has a question.
Yes, I see it. Eddie, can you read the question from the chat? Oh, is this in the room or online?
In the room.
Oh, in the room. Okay,
Yeah,
let's take a question from the room then.
Can he actually hear me on this mic?
Yes.
Okay. Yeah, I was just curious. So like you all are looking at the deflection and what occurs after. I was just curious, like in the future, when you're trying to decide where this asteroid will end up after you've deflected it and whether you might have to deflect it again, is this something that you might model as like a strange, like bang on, bang off, like control problem, nonlinear control problem? Because I can see where you hit it, apply an impulse, it deflects, and now it's in a dynamical system of gravitational system moving around and so on, and you may have to see it again in the future. How would you plan to not see it again?
Yeah, there are some cases, and people, in fact, were talking about it with respect to Apophis specifically, that they call keyholes, where if you deflect it and you get unlucky, you can deflect it into just another impact trajectory. So some of the deflection techniques that have been suggested, some of these ones that I didn't really talk about, I just touched on, the slow push ones, the ion beam or the gravity tractor, are designed to not be, you hit it and it ends up where it ends up, but to be more controlled. And so you can say, okay, we're going to change the orbit to be what we want the orbit to be. The limitations of those, or the negatives for those, is that they tend to take a long time. And so some people envision it where you use the powerful one, the kinetic impactor or something like that, to do the big change, and then you send one of these other ones to just kind of make sure that, okay, it's not going to come back to the Earth, if it's close. I think most of the cases, and you've got Paul Chodas there in the room with you, who I think could you can find him during a break if you like. I think statistically, though, in most cases, space is just pretty big, and so you would assess after you hit it what you did. But I think in general, you would not. It's unlikely that you would put it onto a trajectory that would come back.
And I think this comes back to characterization, right? Better characterization of the object you have, including its orbit and size and mass, a better chance you will be able to deflect it properly.
Yeah.
I'm looking at the question online, and I think that I'm guessing this came from a student because he's looking into developing career in your field. And my question to you, Andy, is can students connect with you? It seems that you have inspired some of them to maybe pursue a career in the STEM and maybe focus even on planetary defense and cool topics like this. Would it be possible that students get in touch with you if they're interested to develop a career in your field?
Sure. I'm happy to take questions from students. I am not a professor. I haven't been a professor, so I am not in touch with what pedagogy is or what classes are out there or developing software or AI. But I'm certainly happy to talk to folks. And then of course the state of science is in flux right now for various reasons. But yeah, certainly happy to talk.
That is amazing. Go ahead.
Dr. Melamed, Nikki seems raised hand. Nikki.
Yes, hi. Good morning.
Okay.
Can you guys hear me?
Yes.
Okay, great. What a presentation. Thank you so very much. I'm sitting here listening to this and on a Saturday morning. This is fascinating me. My question is that how concerned should we be about potentially hazardous near Earth objects approaching from the sunward direction, given how difficult, it is to deflect? Is that still one of the biggest blind spots in planetary defense?
Yeah. So Chelyabinsk came from that direction. The Chelyabinsk impactor came from that direction. The NEO surveyor will be looking more in that direction. So that will absolutely help. The concern would be, and this is going to sound maybe a little silly, but it's only a problem if we haven't spotted it before, right? If something is coming from that direction and we've never seen it and it hits, so we were unlucky with Chelyabinsk, but 2024 YR4, which came close in late 2024, and there was the chance of a possible impact in 2032. That also kind of came from that direction. We didn't see it until it was past us. So now 2024 YR4 is also, in a sense, always going to be coming from that direction. But now that we've found it, it's not a problem anymore. So hopefully, a combination of NEO surveyor plus the fact that we have these surveys that have been going on for a very long time, so we know more and more of these objects. That those two things together mean that things will still come from that direction, but either we will spot them or we will already know that they're coming.
Thank you, Andy. I think with that, we should probably move to the next talk. Andy, wonderful to see you.
Wonderful to see you. Thanks for having me.
I hope that we will meet at the next conference, which will be in Montreal. I'm sure you'll be there.
Yep.
Thank you so much for supporting, giving an amazing and interesting talk today. Say hello to everybody from your colleagues that I'm familiar with. And we'll stay in touch and looking forward to the exciting news coming in the next few months about various space topics associated with asteroids. Yeah. So have a wonderful rest of the day. And thanks again from everyone. And thank you to the good questions. Again, I'm encouraging students who would like to pursue career in that field to connect with Andy and practically with anybody else who is going to be presenting today. We are going to have a fascinating set of talks that are inspiring to students and everyone. And this is the time to develop the next generation of planetary defenders. So get in touch with the panelists and the presenters and see if you'd like to develop a career in this field. With that, again, Andy, thank you so much. Have a great rest of the day. And now we are going to switch to Professor Phil Lubin, who is going to talk about towards operational planetary defense system, hypervelocity penetrators to pulverize threats. Phil, take it away.
Okay. Can you see a full screen?
Yeah, we can see your screen and we can hear you well.
Very good. Okay. All right. Great talk, Andrew. That was really excellent. It was a good lead into what I'm going to discuss here. So you may recall that in the last few frames before the impact of DART, there are the beautiful images that Andrew showed of the surface of the asteroid about to be hit. And as he described, it looks like a rocky field. And we'll talk about what the implications of the binding material of asteroids, and we'll also talk a little bit about comets are, which allows a very different approach. So as Andrew discussed, DART is sort of an intermediate between a very gentle push, something like ion beam deflection or work we've done in the past in laser ablation, and something much more violent, and not in a bad way, but actually in a good way that we're going to talk about, which actually leads to a possible single launcher solution for planetary defense over a vast range of threat space. So our program is a NASA study called PI for Pulverize It, that we describe as a multimodal planetary defense system. And we use hypervelocity penetrators to actually take apart asteroids. And we'll show that this is scalable over a vast range of threat space. And it's also a program which allows a true operational planetary defense program to evolve very quickly because we possess all the technology required to do it. Okay, if you're interested in the details, you can see our website, which is shown here. There'll also be a talk a little bit later today of some of my research colleagues, which will describe it in more detail. But if you're interested, or if you can't sleep at night, or if you have problems that you need to fall asleep, read our papers. We have 9 technical papers, the largest of which is 194 pages, so you can knock yourself out. There's 5 additional papers in preparation, and there's 10 popular papers that are out there, a couple of Scientific American articles, and we have about 24 colloquia and talks that we've given. We also have a YouTube channel that shows many of the simulations that I'm about to show you, and that you'll see later in the day as well. There's several thousand simulations of fairly high fidelity. Okay, so let me start my timer here. All right, so the team is a multi-institutional team, in addition to the University of California at Santa Barbara, where I and my colleagues are at. We've had a large number of undergraduates participate in the program, roughly 30, and we've had a number of high school students also participate, and actually even some in junior high that have at least talked with us, read some of our papers, and looked at it. So in addition to the University of California, there's NASA Ames, Johns Hopkins, University of New Mexico, Los Alamos, New Mexico Tech, Sandia National Lab. IBM was represented by Richard Garwin, who unfortunately passed away last year. An interesting note about him in just a moment. If you don't know who he is, you should definitely look him up online. He's an amazing individual. Also, others at Los Alamos, University of Utah, Northern New Mexico College, and then a large private space company. Okay, it's a good thing to remember, which is a nice comment by Arthur C. Clarke, the author on reactions to revolutionary ideas in any area, And I think it's something to keep in mind for those of you particular students, is that, this is to quote him, every revolutionary idea seems to involve three stages of reactions. They may be summarized by the phrases. Number one, it's completely impossible. Okay. Number two, it's possible, but not worth doing. And number three, in the end, is I said it was a good idea all along. So if you have a sense of humor, and if you look at life from a point of view of what are the revolutionary changes along the way and how do people react to them, oftentimes they say, that's not possible, it's crazy. And in the end, they say, oh yeah, I knew that was going to work all along. Good to keep in mind, particularly in this program. The one person who understood this program immediately was Richard Garwin. I called him and emailed him materials, and he got back to me 6 hours later and said, this will work. I'm giving a talk tomorrow to the National Academy and the American Federation. Can I present the material? And I said, of course. And he understood very quickly. He was quite an amazing mind. There's a nice Scientific American article that came out a couple months ago that talks a bit about our program. I want to take a look at that. If you're into videos, there's a nice YouTube that was put together on our program. We did not do this. This was done by the Kurzgesagt group called Can Humanity Stop a Planet-Killing Asteroid, which talks both about our program for smaller asteroids in the few 100-meter class, all the way up to existential threats like that, which killed the dinosaurs some 66 million years ago. What's amazing about this video, since I teach for a living as well as research, is that in 8 months, it has more than 11 million views. That's orders of magnitude above my entire career in both teaching and giving many, many hundreds of talks. Nowhere near that. Let's just think about that. 11 million is more than 1/10 of 1% of all of humanity on Earth. It's incredible. So this way of reaching people via the internet and by videos like this is just unbelievable to me, who spent years, decades, many decades in the classroom.
But what would we do
This is a
if you
great video. You got to
detected
watch this one.
even a small one, like the one that detonated in Russia, headed for New York City in 3 weeks? What would we do?
I assume you can hear this.
Bend over and what?
No, Congressman, that is, I don't, again, I have to go back to what I said before. These are very rare events. From the information that we have on asteroids that we've discovered of all sizes, we don't know of one that will threaten the population of the United States, in 3 weeks. And we are trying very diligently, as I said before, with the President's budget, to put ourselves in a position where we advance the technology such that 3 weeks will not be something that causes us to panic, because we will be able to respond. We are where we are today because, you all told us to do something, and between the administration and the Congress, the funding to do that did not. The bottom line is always, the funding did not come, and I don't care whose fault it is or if it's anybody's fault. We all know what we're facing today, and we're all sitting here today as the Congress and the administration try to figure out sequestration, something that never should have happened, nobody planned to happen, but we're facing it today. And so the answer to you is, if it's coming in 3 weeks, pray. If we find that out right now, and that's not bad.
That's
not
reality.
That's not bad policy.
Yeah.
Okay, so could you hear that, the video and the audio? Yes? Okay, so PRAY is now an official scientific response if something's coming in 3 weeks. So that's official from NASA. And I just love, Charles Bolin was a wonderful administrator of NASA. That was in 2013, sorry, just after the Chelyabinsk event. And it's correct. We're still in the same position some 13 years later. If something was coming in 3 weeks, what would you do? And in most of the techniques you're going to be hearing about today, except ours, you would not be able to do anything. In our technique, you could do something with 3 weeks of warning. Depends on the object, but I'll show you it's possible. Okay, all right, so the time between events, this is a nice plot which you may want to become familiar with. And again, if you go to our website, you'll find lots of material as well as lots of other material in other places. The plot on the left is very interesting to look at. This is the time between impacts on the vertical axis in years as a function of both the upper vertical axis is the approximate diameter of the object in meters, assuming it's coming in at about 17 kilometers per second, which is not an unreasonable closing speed, and density of roughly rockish density around 2.6 grams per cc. And the lower axis, x-axis, is in impact energy in megatons. Okay, so there's two lines on here which are important, two horizontal lines. I don't know, can you see my cursor or not? Yes, no? Okay, I'm not getting response, but I'm not sure you can. The lower horizontal.
We don't see.
You
Sorry,
can
we
or
don't see the
cannot?
cursor. No.
You cannot. Okay. So I'm
Cannot.
pointing at a line at 1 year. So if you look at the vertical axis on the left at 1 year, you will see a line that goes across. And that's every year we get hit by something which has roughly the equivalent of approximately 10 kilotons of energy per year. And most of the time it's just a big boom. Okay. It's not a terrible event. 10 kilotons sounds like a lot. It's the energy approximately of the Second World War nuclear weapons. And about once in a human lifetime, so that's the upper dashed line that's horizontal, about once every 80 to 100 years, you get roughly a megaton event. So a megaton is like that of several modern thermonuclear weapons on ICBMs. And so what evidence do we have for this? Well, if you think of the last roughly 100 years, we have Chelyabinsk, which was about half a megaton in 2013. And in 1908 in Tunguska, we had something which was estimated to be around 10 megatons. So these numbers are not unreasonable, even in the past roughly 100 years. Okay, we luckily these days have lots of microphones around and other instrumentation for looking at things that come in and hit us. And about 50 tons of material hit us every day, between 50 and 100 tons of material, mostly in the form of small meteoritic debris. But every once in a while we get whacked by something larger. So this is a plot of events. Bigger circles are more energy. The center of the circle is the impact site. So you can see the big circle in the upper portion, a little bit to the right of center, is Chelyabinsk, and then lots of other circles of events. So that big circle is about 500 kilotons, about half a megaton. And this is over the last 20 years approximately. Okay, if you look at planetary defense versus national defense, they're radically different. And the problem is that planetary defense is an area where the events are relatively infrequent. This is also a psychological issue as well as a physical issue. So most of you, assuming that you're old enough, drive cars. So approximately 1.3 million people die per year in car accidents worldwide, and about 50 million people are injured worldwide. So in a human lifetime, say 80 years, roughly 100 million people die in car accidents, and about 4 billion people, or half the Earth's population, are injured in car accidents. So I often ask in my class, how many of you have been in a car accident? So let me ask you in the room, how many of you have ever been in a car accident? Please raise your hands. I can see you on the screen here. Okay, so I see a few hands going up, more than a few. And so it's, within statistics, I would say about half of the room has been in some sort of car accident. So not unreasonable, and you're still alive, okay? So, why don't we ban cars? Because in your lifetime, 100 million people will die. If I told you that an asteroid is coming in and is going to kill 100 million people, what would your reaction be? You'd say that's terrible. But you drive a car that on average kills 100 million people in your lifetime. Why don't you care? Because the benefit of driving a car versus not outweighs your perception of threat. So you're willing to take the risk. You have a 1% chance of dying in your lifetime in a car accident. You take the risk because 99% of the time you're okay in your lifetime. But just think about it. That's the difference between national defense and planetary defense. National defense is done at a level where there's no margin for error that's assumed to be allowed, no reasonable margin. So how do we deal with things from a national defense point of view? We have multiple redundant systems of both detection and mitigation, everything from over-the-horizon defense to last moment, literally Gatling gun or CWIS or phalanx, as it's called, a close-in weapon system, which literally shreds the object coming in at the last moment. We use this in the military arena quite frequently. In fact, if you look what's happened in the Middle East recently, you'll see weapons systems like that have been deployed that at the last moment cruise missiles are coming in, that you didn't shoot them down early enough, you hit them with literally about 80 rounds per second, and this shreds the threat coming in. And a lot of our system is analogous to both an over-the-horizon mitigation as well as a last-minute or terminal defense mode. Okay. If you look at asteroid kinetic energy, the amount of energy coming in, comparison to nuclear explosive devices or nuclear weapons, I show a little chart here with some pictures of nuclear weapons and sizes of asteroids on the lower section. And on Friday the 13th in April in 2029, which is coming up soon, a couple years, mark your calendar. It's not Freddy that's coming on Friday the 13th. It's Apophis. And as Andrew mentioned, Apophis is big. If it hit the Earth, it would have a kinetic energy comparable to the entire world's nuclear arsenal. It's not going to hit the Earth this time. It does come by frequently, and it's about 350, 370 meters equivalent diameter. It's going to come close enough, as Andrew said, that you'll be able to see it if you're in the right part of the world when it flies by. It's going to come inside the geosync belt. So really close approach. Okay, near misses are relatively common. There was a 1 kilometer asteroid. There's just a couple of recent ones on January 18th of 2022. If it hit, it would have had something like roughly 100 gigaton of energy, or about 20 times the world's total nuclear arsenal. Comet Neowise, which is the basis for the movie Don't Look Up, was a sun-grazing comet. There was a question asked about the sun recently. And it was discovered 4 months before it flew by the Earth. In the movie, they give 6 months from detection to hit. The movie is based on that. The science team was the group that actually found the comet, which is now called Comet Neowise. It's technically known as C/2020 F3. Okay, and then on Friday the 13th, in April 2029, a big one will come by, which is Apophis. Okay. All right, there's lots of evidence for mass extinctions in the past. If you study the geologic and biological record, you'll see a number of times in which large fractions of life has been extinguished. Some of those are likely due to external things hitting us. And we know that the KT event, the Cretaceous Tertiary event, which we refer to as the dinosaur extinction, was 66 million years ago. And there's a very interesting layer of clay, which is relatively worldwide in its presence if you do core sampling or do geologic analysis. That was the basis for the Alvarez, Louis, and his son did work on looking at what was in that clay layer, which is well known long before they were looking at it. But they were curious what was in it. So they did a radioactive isotope. They did an isotope analysis up at Lawrence Berkeley Lab, where Glenn Seaborg had a nuclear physics lab, and they discovered, to their surprise, that there's a very strong amount of heavy elements in there, namely iridium, which was consistent with the Earth being hit by a 10-kilometer diameter asteroid some 66 million years ago. Then the question is, where is the crater? Well, 3/4 of the Earth is covered by water, so it's most likely in the ocean rather than on land, just statistically. But still, we wanted to find it, and at the time of this work, there was no such crater known. We now are pretty sure this crater is, as shown in the lower left, in the Yucatan Peninsula in Mexico, mostly underwater. But it's a quite large crater when you look at it in perspective from both underwater soundings as well as a bit of land work, and you see that there's something which is of order 100 kilometers in diameter, which is consistent with a crater from a 10-kilometer asteroid hit. Okay, so pi is a very different way of defending the Earth against both asteroids and comets. Very different from what was described by Andrew, which is to sort of bump it off course. We're not interested in bumping it off course in general. We're interested in destroying it. So much more like the terminal defense in shredding a cruise missile coming in, we intend to shred the threat so it's no longer a threat. In general, when people first look at this and say, that's terrible, you're going to take one object and make it into, potentially millions of objects. That's horrible. We said, no, the physics doesn't work that way. It works for reasons which I'll describe, which is basically something you're very familiar with. Namely, it's quite difficult to come through the Earth's atmosphere in a terminal mode. You don't want to do terminal defense, but if you had to, this is the technique which will work. It's difficult to get through the Earth's atmosphere, as we know from the tragedies of entering the Earth's atmosphere from re-entry vehicles that have humans in it. It's quite difficult. It seems like it's not much, but coming in at hypervelocity speeds, it is quite difficult to get through. Okay, so we'll talk about threats from roughly 20-meter scale, like Chelyabinsk, all the way up to existential threats. And again, if you're interested in the details, look at our many papers or look at the videos online. Generally, you do not want to have a terminal defense mode. You want to catch it early enough so that we would fragment it into pieces and the pieces miss the Earth. So we don't want to play chicken at the last moment, but if you were having to be in that case of, as the congressional testimony, 3 weeks from now, we're going to be hit, what do we do? Deflection's not an option in general. This is an option. It also leads to a single launcher solution that we could deploy essentially today if we wanted to. It's really a question of will versus not. Okay, so in the terminal mode, you basically, well, there's two modes. You basically break the object apart into pieces. And how do you do that? Well, it's very similar to what you do in national defense. If you hit an object or an object hits you in this case is a penetrator. For us, we make them out of tungsten, but you can make them out of Diet Coke if you wanted to. Tungsten works really well. It's simple. It's not radioactive. It's inert. And you have penetrators that you deploy, and you just put them in front of the object. It's kind of like DART, but having a bunch of penetrators. And the penetrators basically shred the object into little pieces. And we have lots of simulations showing how this works. In the terminal mode, those little pieces enter the Earth's atmosphere. They break up, burn up in the atmosphere, create a shock wave and some light, and that's the whole basis for the program. What people misunderstood at first is you're going to make a mess. No, you don't. Just like having a bulletproof vest on, you'd much rather be hit by a set of pellets rather than one single object hitting you. The same thing for your glass windshield. You'd much rather be hit by a kilogram of sand spread out over the windshield than by a 1 kilogram rock if you're going down the freeway. Just think about it. It's very logical. We didn't understand why people didn't get it, but once you go through the physics, it's quite trivial. Okay, this one system allows you to have a very wide dynamic range in both threat and in time, response time. So in short response times, which we call the terminal mode, you'd rather not, but if you had to, you shred it and it enters the Earth's atmosphere. The Earth's atmosphere is basically a shield or beam dump, as we would say in physics, and the objects burn up and create a series of shock waves, which are decorrelated when they get to the ground. That's the key to why it works in the terminal defense mode. If you have more time, you break it up into pieces. They can still hit the Earth if you want, if you need to. And you can literally survive a 500-meter being broken up into pieces a month ahead of time, or even 100-meter days ahead of time. So this is an incredibly effective planetary defense system. For existential threats or very long warning times, you break it up and the pieces miss the Earth. And then there's a nuclear mode where you use a nuclear device to break up very large objects. Okay. If you are in the terminal mode and you study the shockwave generation by objects, you find that below about 10 to 15 meters in diameter, the Earth's atmosphere is sufficiently difficult to get through that they're basically not a problem. You'll have a big boom, and you might break some windows if they're in the 10 to 15 meter range, but they won't do much else. Okay. So this is the key as to why it works. You know it works because if you look at Chelyabinsk, which is around 20 meters in diameter, you broke some windows, and that was unfortunate, but luckily no one was killed. They could have been, but luckily they weren't. You had a lot of windows blown out. That was 20 meters. Had that been 10 meters, you still would have had a big boom, and you might have cracked some windows, but that would have been it. Okay, asteroid disassembly. So this is the key, is just like you saw in the picture that Andrew showed. In general, I'll show you asteroid rotation curves. Asteroids are rubble piles, particularly large asteroids. And a rubble pile, if you look at the gravitational binding energy of a rubble pile, it scales like the 5th power of the diameter, as you can see on the plot on the right. Don't have to remember anything, just read our papers. The total amount of energy required to disassemble even a 1 kilometer diameter rubble pile is quite small by comparison to things that we have at our disposal. The question is coupling that energy effectively to blow it apart. And that's what our simulations have shown. On the left, lower left, you'll see an OSIRIS-REx, very similar to what was shown by Andrew, pictures of an asteroid. This was Bennu. And you can see it looks like rubble. And in general, they are rubble. They're gravitationally bound rubble piles for large asteroids. We know that from the rotation curves of asteroids. So how does it work and why does it work? If you imagine that an asteroid is coming in toward you, or a comet, we'll focus on asteroids, and you get in front of it with an object. So you're now being hit by something rather than you hitting it, but it's a relative point of view. So on the lower left, at t equals 0, I show a little purple thing, which in our case is a tungsten rod. And it is closing with the speed of v. When it enters the asteroid, it vaporizes very quickly in less than 1,000th of a second. The tungsten vaporizes. It also vaporizes material in the asteroid, creates a plasma and gas cloud, and a huge shock wave is passed through the system, which breaks up any remaining large things, and it basically blow it apart. There's a gas engine inside, which is this expanding gas and plasma cloud formed by the vaporization of both the penetrator, in this case tungsten, and the object partially vaporizing from the penetrator kinetic energy. So you also get a very high beta if you're interested in deflection modes, and I'll show you a beta 50 in a little bit from a simulation. But in general, we just blow it apart. And then the fragments either miss the Earth if you have enough time, or in a terminal mode, they enter the Earth's atmosphere and burn up. Okay, the reason it works in the terminal mode is because the shock waves, which are the primary threat in this terminal mode, are decorrelated. And that's because the speed of sound is so slow compared to the entry speed of the object. Typically, objects enter the Earth's atmosphere at between Mach 20 and Mach 100. So the sound speed, on the other hand, when it decays, down to roughly Mach 1 is 0.3 kilometers per second, or Mach 1 by definition. And it's that difference which allows the shock waves to hit you in a series of booms, and the shock is very narrow in time. So it's like listening to thunder. You hear boom, 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 rather than all one gigantic boom. And it's that difference between one gigantic boom versus many small booms that saves you. That's why it works. So Chelyabinsk, for example, was roughly a half a megaton, which is similar to what's called a B-61, which is a modern thermonuclear weapon. Tunguska in 1908 was awarded 10 megatons. We're not quite sure because we didn't have all the Russian dash cams and sensors that we have now. When you get to pressure waves of order a few kilopascals, about half a psi, you start to have residential glass damage. When you get to 10 kilopascals, you start blowing down residential buildings and brick walls, unreinforced objects. The optical signature is not trivial, but in general, it's subdominant. But we also compute the optical signature. So for example, the combustion danger for dry grass is about 0.2 megajoules per square meter. It's a pulse, optical pulse. Okay, these are optical flashes. Okay, but again, the optical pulse is subdominant. So here's what happens at high altitude. Again, if terminal, and again, you don't want terminal, but if you had to, like the 3 weeks in the congressional discussion, this is your ticket to safety. When an object comes in at high altitudes, you start to see an optical signature at altitudes of about 100 kilometers or so above the surface. The object deforms because of the extreme ram pressure going through the atmosphere. It pancakes, and then it basically airbursts at altitudes of order 30 kilometers, which is the burst altitude for Chelyabinsk, for example. And then the objects that result from that burn up in the atmosphere. Some little pieces may hit the ground, but in general, there's not much. If you study detonation physics, nuclear weapon physics, you could understand shockwave physics, which I won't go into too much detail here. Again, this is all in our papers. There's two modes. One is a strong shock mode, and the other is a weak shock mode. In general, in planetary defense, for our area, you're concerned with the weak shock mode for the fragments. And that's because this distance from the detonation site is so far away that you're in what's known as the weak shock mode. Again, detail, don't worry about too much. On the other hand, there's a very interesting effect of the shock speed. The shock wave in the atmosphere, again, if terminal, starts at extremely high speeds, essentially the entry speed of the object, and then decays very quickly down to Mach 1. So this is showing the Mach number of the shock wave as a function of distance from the center of the shock wave. And again, the shocks in our case are starting at about 30 kilometer altitude approximately. So they've decayed essentially to Mach 1 by the time they hit the ground. Okay, we also study optical signatures. We propagate through the atmosphere with atmospheric models of what's in our atmosphere. And we show that in general, that's not a problem if you're doing your job properly. And for reference, about 10% of the energy goes into the optical pulse. So non-trivial, but it's not zero, but it's not the dominant thing that you worry about. You worry about the shock waves mostly. This is just atmospheric transmission. If you're interested in the mathematics of it, see our papers. You might worry about dust production. Are you going to cause a nuclear winter scenario if you have all this dust in the atmosphere? Again, if terminal. Okay, and the answer is basically no. And we compare it to things such as volcano eruptions. We have a paper that we're working on nitrous oxide production and O3 destruction, which is actually seen correlated with atmospheric events from boloids. So no, you don't get a nuclear winter scenario. Okay, but in general, what you want is mitigated far enough away so the fragments miss the Earth. So you'll hear more about this in other talks this afternoon. So if long warning, fragments miss the Earth. If short warning, like the 3 weeks we heard about in Congress, then the fragments just burn up in the Earth's atmosphere. Not a problem. Chelyabinsk, you've heard about, we have lots of Russian dash cams. You can find all these beautiful movies online. Came in at about 20 kilometers per second approximately had a kinetic energy of roughly half a megaton, which, for reference, is about 25 times larger than the nuclear weapons that were used, unfortunately, in World War II. It's about 2 modern ICBM reentry vehicle warheads. But an additional 90 kilotons went into the fireball. That's interesting. 90 kilotons of energy went into optical and infrared radiation. So some people actually got sunburned from the event, and some people had temporary retinal damage or like snow blindness from the event. Tunguska happened in 1908 in a very remote area. As far as we know, no one was killed, although it's hard to tell for sure. The picture on the lower right is a picture from a survey taken a number of years later because it was very remote, so there was really not a good way to get out there. Estimated yield is somewhere between 3 and 30 megatons, and people argue about this. And anyway, it's the energy in equivalent ICBM warheads is between 10 and 100 modern ICBM warheads. Okay, a lot of the blowdown of the trees that you see here is due to both the very high winds generated and the shock pressure of the shock wave hitting them and the winds. Okay, so I'm just going to blow through, literally, some worst case late time or short warning time scenarios. This is the congressional couple weeks scenario where you have no other result to mitigate than to break it up, and then the fragments hit the Earth. Okay, so if you look at this plot shows a 100-meter asteroid coming in. I do a 97-meter on fragment because 100-meter actually at this speed will hit the ground, so I don't want to do a ground hit. You can see if you don't do anything, which is the green, so pressure on the vertical axis, distance away from ground zero, which is right under the object. On the horizontal axis, you can see the green, which is unfragmented, i.e. you did nothing, versus breaking up this 100-meter object into 1,000 pieces in black 1 day prior. You intercepted it 1 day before it hit Earth, not even 3 weeks, like in the congressional question. Okay, then I do 4 days and we do 10 days. And you can see what's happening is logical. You're spreading out the effect of one big rock hitting your windshield into a bunch of little pebbles or sand grains hitting your windshield, and obviously much less acoustical damage. So this is the peak pressure in the shock wave at the ground. And you notice on the vertical axis, if you go to the 10 to the 3, which is 1,000, which you just start to worry about a little bit of glass breakage, versus 10 to the 4, we start blowing down residential buildings, that you stay conveniently in the regime where you might get some glass breakage, but that's it, compared to the unmitigated case where you're going to do tremendous damage. This would have an equivalent kinetic energy around 100 megatons or so. So a bad day versus a light show. So watch the Kurzgesagt video and you'll see a nice animation of it. Here's a 50-meter in 1,000 fragments. The green dot is you, and you'll hear a blast wave now. You hear a blast wave as you raise your hand, so I can hear it. Like thunder, many thunder events, and those series of blast waves do almost no damage. You might break some windows. You cover your ears, you just stay inside in general, and everything's fine. This is the same event, but now we have on the right the real-time pressure for doing nothing, just letting the 50-meter hit. And on the left is breaking up into pieces. Okay. This is Apophis coming in on an intercept, which is not the one coming in 2029. This is a different phase. So this is if you did have to intercept it in some crazy scenario, and this is not what you want to do, but this is 20 days prior to impact, we break it up, and then the fragments hit the Earth's atmosphere. You're fine. You break some windows, but you're fine. This is the difference between catastrophe and inconvenience of replacing your single pane windows with modern double pane windows. Okay. So the glass business, loves it because they get to replace lots of windows, but nobody dies. Okay. All right. This is a 500 meter, same thing. You don't want to do it, but if you had to, this is 60 days before impact. We break it up. Same thing. You might break some windows, but nobody dies. Versus if it hit, a lot of people would die if it was in anywhere near a populated area. Okay, these are what are known as the shockwave caustics. Because shockwaves, just like, let me go back. Okay, let me show that again. If you look at the shockwaves where they overlap, you get what's called a caustic. It's like looking at the bottom of a pool when you have the ripples at the surface bending the light. You see caustics. The caustics are absolutely beautiful to look at in simulations. This was so beautiful that one of our colleagues, Mark Boslow, showed it at the Starmus event, which is kind of like science plus, rock music in Europe. And it's beautiful. It's just incredibly beautiful. So you might want to take a look at it. This is a 35 meter, about a 2 megaton yield if it were to hit at 20 kilometers per second. Intercepted 1 hour prior to impact, 1 hour, and you're still fine. Okay, here's some simulations. You'll hear a lot more about this from my colleagues later on. We model the asteroid in this case in a fairly complex way using the equations of state, so density versus pressure, for a variety of materials from relatively low strength to very high strength. So we kind of go to an excess and look at things which are really strong, like solid granite, things which are the strength of stainless steel, which is to some extent, I think, overly conservative. But what you'll see is we still succeed. So this is a 20 meter being hit by a single 100 kilogram, about the size of your arm, tungsten rod, one tungsten rod, hitting a 20 meter, which is roughly the size of the Chelyabinsk event. And then you can see the time in microseconds in the upper left. The object is hit, it's vaporized, it's blowing material out. So this is a great rocket engine to have high beta. And this whole object will come apart. You destroy it. You break up all the material in it from the shock wave that's generated, and the whole thing is blown apart by this massive plasma gas engine, which is basically an adiabatic expansion engine inside. So absolutely beautiful. Look at our simulations. They're really incredibly beautiful. The simulation is done on a supercomputer using what's called AIAA 3D, which is a Lawrence Livermore extreme equation of state simulation code. This same thing, but a 50 meter, again, a single 100 kilogram penetrator. For reference, the mass of the DART mission was around approximately 600 kilograms. This is a single 100 kilogram penetrator, the size of your arm, blows it apart. Okay, lots of statistics, won't bother. Basically, you break it into pieces which are, even though you start with pieces which are big, you start with pieces which may be 5-10 meters, rocks inside of it, solid. You break it up into pieces because of the shock wave, and the pieces are generally less than a meter. But even if they're 5-10 meters, you're still fine. And it doesn't come back, by the way. It doesn't recombine gravitationally. You blow it apart so hard that it does not recombine. You significantly exceed the escape speed. You can do other things. You might want to blow it apart and deflect it sideways. You might want to blow it apart and have a very high beta. Lots of things are possible here. Here's a Falcon 9 versus a 100-meter asteroid. Passive, purely passive, no nuclear, no conventional explosives. The threat is destroyed. Again, you start with big rocks inside. The shock wave pulverizes them into pieces. In this case, if you hit it, this is again a single Falcon 9, which has a positive C3 so it can escape the Earth, which is what DART was launched on, by the way, carrying a 2.5 metric ton single tungsten, or you could have an array of tungsten rods. Threat is destroyed. Here's a 500 meter with a 10 ton. So this is something like a Falcon Heavy or a small SLS, if you want to think of such a thing, hitting a 500-meter diameter. You get a huge beta greater than 50 because of the blowout of material, kind of like what Andrew showed you for the DART mission, but on massive amounts of steroids. So wouldn't, if you had to, yes, you could do this. And we have launch vehicles that are quite capable. Remember the SLS, the one that launched Artemis recently, is capable of carrying a order 20 plus tons to escape. So we already have launch vehicles that can do this. Actually, can carry even more than that necessary. And if you go to something like Starship, which is coming along, that can carry more than 100 tons with in-flight, in-orbit refueling. Okay, here's shock damage. You can see the shock wave propagating through the material and just fractures it into small pieces. This is a 500 meter, again, being hit by a 10 ton. This material failure is almost 100%. Nuclear penetrator option. Okay, you'd rather not do this, but if you had to, nuclear weapons could be useful. And, maybe instead of we having to worry about nuclear weapons killing each other, which is unfortunately what we do worry about, we can use them for planetary defense. So this is a combination of sequential penetrators that are passive to drill a hole, and then you bring in a nuclear weapon and detonate it. I'll also show you some simulations. Perhaps later, my colleagues will show you some simulations where you look at survival of a nuclear weapon on a single penetrator. Here, we look at the option of bringing in passive penetrators, hole drilling, and then detonate inside. So for those of you that may or may not work or think about nuclear weapons, modern nuclear weapons have about 2 to 4 kilotons per kilogram of what's called the physics package, which is the weapon itself. Okay, so 2 to 4 megatons per ton, per metric ton. Fission devices are about 30 to 70 tons per kilogram. Thermonuclear is where I quoted the number 2 to 4 kilotons per kilogram. Very useful thermonuclear weapons for very large threats, particularly exponential threats. We also look at activation of material in extreme scenarios where you might have to have a terminal mode and you worry about the radioactive materials being generated. It's actually quite reasonable. We'll have a paper coming out soon that goes into great detail on that. I want to show you a movie of 100 kiloton that was put about approximately 100 meters deep in the ground. This was detonated on July 6, 1962. It's called the Stor-Occidental test. So this is a single 100 kiloton, which is not a very large thermonuclear weapon. Sorry, it's 194 meters deep. Sorry about that. The crater formed is about a 400 meter diameter crater, 100 meters deep crater, and the dome lifted up 90 meters high. So this is going to work if you had to do it. And if you look at our paper called Don't Forget to Look Up, you'll see the details of why this works against existential threats. But here's an example, even under 1G of gravity from the Earth versus a 10-kilometer diameter asteroid has extremely small gravitational binding compared to the Earth. So it'll work. You can see an example before your eyes here as to why it'll work. You'd rather not use nuclear weapons, yes, but if you had to, they're useful. Here's sequential penetrators, 5 of them going in one after the other, 1 meter apart. So about 50 microsecond time spacing between the penetrators. And you can sequentially drill holes that are quite deep. And then if you wanted to, you could then bring a nuclear weapon in and it would survive coming in and detonate for much better internal coupling. The deeper you go inside versus a surface burst, which is relatively ineffective by comparison to a deep buried burst, you have much better coupling of the energy of the weapon into the material. The same is true for conventional explosives, by the way. We have a mode where we use penetrators that you have conventional explosives. Okay, so this is just 2 penetrators coming in one after the other, so you can see a little more detail. You can see the beautiful turbulence. It's actually simulations are incredible. So just check out our website. We do lots of these. You'll see more this afternoon. These penetrators are 1 meter apart. They're 1 meter long each, and they have a 50 microsecond spacing between penetrators. Okay. Sometimes, if you look at some of the comments in our Kurzgesagt video, people say, what about the asteroids rotating? Yes, we've worked on that too. So all asteroids rotate, just depends on your point of view. And so here's 6,000 asteroids that I show the rotation period on the vertical axis versus the diameter on the horizontal axis. Above the red line, which is the gravitational self-binding or rubble pile line, which is about 2.2 hours of rotation time. It takes 2.2 hours to rotate once. That's independent of diameter, by the way. Curiously enough, it's just a simple physics problem to prove that. So above that line, you're gravity dominated, it's a rubble pile. Below that line, you're cohesion dominated. So what you see is at small diameters, in particular, you have significant cohesive binding. So it's like trying to pull a rock out of a sand pile is easy. Trying to pull a rock apart itself is very hard. In one case, you have very low cohesion to the sand. In the other case, you have extremely high cohesion to the material itself. Okay, so we take this into account, and basically the answer is sequential penetrators can hit the same hole within a very small margin if you have a guidance system on them. And we've had discussions with some of our colleagues who do guidance systems, and they say this is much easier than doing terrestrial missile defense systems because the objects are big. If you're interested, you can see our paper, which is on our website. Just go to our website, it's all there. This is an example of something that you wouldn't use as a penetrator, but it's an example of something that would, it or something like it is very useful from the nuclear regime. This is a B-61 physics package, which had a yield of about 350 kilotons. This particular one was used for Earth penetrators, which was canceled in 1992, but B-61 weapons are part of the current stockpile. So you would use this after you penetrate with passive devices to drill a hole. If you study nuclear, the nuclear physics of weapons, basically the weapon is dominated by low energy X-rays. Outside the weapon, get about 1% of the energy coming out in gammas and 1% coming out in neutrons. More than 80% is typically coming out in low energy KeV range X-rays. Those X-rays vaporize the rock inside the material. And then just like in the case of chemical explosives inside of rock, it takes about 30 tons of TNT equivalent per cubic meter of rock. You vaporize, you form a high pressure and a shock wave as well, a high pressure gas, and then you blow the thing apart. So if you're interested in the details, I'll show you a diagram here. You can look at a nice paper that was written in 1974. You can also look at a paper that we've written that works out the physics of it. The equivalent radius of vaporization is about 2 meters times the yield in kilotons to the 1/3 power, if you're interested in the details. Here's some demonstrations of 50 tons on the left of conventional explosives, and then we have a mode where we use conventional explosives on the right, 100 kiloton, just for reference, a thermonuclear explosive. Okay, more of the Bruce Willis style. And this is just an example. You wouldn't do this on a 20 meter, obviously, because you can do that purely passively. Okay, this is a nuclear explosive in a 100-meter target, which again, I showed you can do that passively well, but here's a demonstration of using a 1 kiloton, which is a small tactical nuclear weapon, with sequential penetrators to bore in deep and then blow it apart. Here's a 225-meter, so more like the DART target, 100 kilotons initiated at 10-meter depth. And again, you blow the thing apart. Shockwave models. So one of the fun things about this program is we get to work with people that blow up big things. So this is 10 tons of ANFO, which is ammonium nitrate fuel oil, detonated in October 2024. We were doing some shockwave studies. And if you look carefully, particularly at the upper left of the explosion, you'll see the shockwave propagating outward in distortions of the atmosphere. So just kind of watch it. Now you can see it propagating outward. So this was to calibrate our models and cross-check, and our models worked incredibly well. That was a 10-ton. This is a 1-ton. And here's the shockwave shown on the right quantitatively using both devices that we built in our lab to measure the pressure and much nicer devices that were provided by our colleagues in New Mexico. So we came very, very close to predicting what was measured based on our shockwave models. Okay, you'll hear more about this in the afternoon, but we started to do mission modeling, and I know we're coming down here. I'm keeping track with the timer, almost done. One thing to keep in mind is launch vehicles. So what launch vehicle would you use? Well, this shows the payload mass in metric tons on the vertical axis versus what's called the C3 or characteristic energy, which is in units of kilometers per second quantity squared for things from all the way like a small reusable Falcon 9 to an expendable Falcon 9. So it costs you a little more for planetary defense if you want to use an expendable, but it's probably worth it. To a Falcon Heavy, to an Atlas, to a Delta IV, to an SLS Space Launch System. So we possess the technology already to build an operational planetary defense program. And what we recommend is starting with something like a Falcon 9. We happen to live in Santa Barbara, very close to the Vandenberg Space Force Base, where most of the Falcon 9s are launched from. So that would be a good starting point. Okay, almost done here. If you wanted to really think about things more creatively, you might realize that the reason we use liquid-fueled rockets on Earth and not solid-fueled rockets on Earth is because the Earth gravitational well is very large. Let's say you wanted to have a system deployed in space or on the moon. I think you would face a lot of political blowback for putting it on the moon, but you might think about it. We took a Minuteman III design, took off the upper stage, the third stage, and you can see that it easily escapes the moon and carries a fairly heavy payload with it. So the moon might be an interesting place as a forward base of operations for planetary defense, both for detection as well as for launch. Again, I think there's a lot of politics here, so we're not recommending that to begin with. Okay, what we are recommending is a single launcher solution for planetary defense that could be deployed now. And I think a Falcon 9 is a very good start. It's a known entity. There's a lot of them launched. They're going to push to about one per day on average. They're not quite there yet. And you just basically have one on standby. So you have an at-the-ready single launcher solution for virtually any threat. And if you allow nuclear weapons on a Falcon 9, you can take on even extremely large threats. Okay, just a thought already exists. It's a solution for single mode, for single launcher planetary defense right now. Okay, I'll kind of blow by this one. Here's an example of Falcon 9 versus 100 meter. I already showed that before. You can do it purely passively. Okay, method summary. This works incredibly well. Just read our papers if you can stand it. These plots are all in the paper. This is showing terminal mode defense if you had to do it in days on the vertical axis for the plot on the right versus diameter. And you could see that you could take things apart and survive. This is, again, a terminal threat mode. Don't want to do it, but if you had to, this system allows everything from terminal mode to what we call over-the-horizon threat mitigation. Okay, we're looking at demonstration concepts. So this is a counter-rotating demonstration where you'd have perhaps a thin inflatable sphere like the Echo program, keep it at low altitude so you wouldn't create much space debris, and hit it with something like a CubeSat just to show that you can do the guidance and control properly. Counter-rotating, you have about 15 to 16 kilometer per second closing speed. Okay, conclusions. It works incredibly well. It allows for rapid response if needed. It provides much less launch mass off the pad for long-term threats. That's something to keep in mind. Why is this useful? Well, it allows for terminal mode. Deflection is not. an option for terminal mode. This allows terminal mode, but the same system without modification also allows for mitigation with long-term warning and requires much less launch mass off the pad. You're using energy transfer, not momentum transfer. DART used momentum transfer. We use energy transfer. That's the key difference. NED penetrators are an option for extremely large threat mitigation, and you have a path to a single launcher solution with an at-the-ready capability. So I will stop there, and if there's any questions, happy to answer.
I have a quick question. Have you modeled something like 3i Atlas? So it'd be something that would be in a hyperbolic trajectory, not necessarily predictable in terms of impact, but say, had it been in a impact trajectory with Earth, I read somewhere where we'd have had something like 4 months from discovery to impact, if had it been in a Earth trajectory. So have you modeled something like that for intercept or deflection or destruction, or how would you approach that?
Sure.
Who is speaking? Who is speaking?
I think it was Adrian.
I'm sorry, my name's Adrian. I'm one of the people that's listening in.
Okay, go ahead.
Yeah, good question, Adrian. So by modeling, we interpret modeling in a variety of ways. So let me just lead you through a couple of ways in which we interpret modeling. One is, can we destroy the threat, such as a 3i Atlas? And what would it take to destroy a threat? Now, 3i Atlas was a big thing, right? It's not, not a small thing. And so for something like that, it becomes more of an existential threat type scenario, which we do discuss in our papers. What you would do, so that's several months ahead of time. It's much like Comet Neowise, which is the basis for the movie Don't Look Up, which we have a paper on. If it were coming in and going to hit you, with 4 months of warning, we show scenarios where you could do that. Just read our paper. Don't forget to look up. In terms of the precise modeling of the launch vehicle to the object, no, we have not looked at the orbit specifically for 3i Atlas, but we have shown that we can get the mitigation part of it. In the case of 3i Atlas, you would use combination of passive penetrators plus nuclear devices. We've shown that that's viable with current launch vehicles. But in terms of, the specific launch on this date to intercept on that date for that particular object, no. We are working on mission scenarios for precisely that, for typically different objects rather than existential threat objects. But we do show for some of the equivalent of that which killed the dinosaurs that we can take it on with, say 6 months of warning. It's not something you want to ever be in the place that you have to do, but if you had to do it, you could do it. You'd rather not be in that place. You can also watch the movie, the Kurskazak movie talks about existential threats as well.
And what about composition, rubble pile versus dirty snowball? What differences would you see there?
So for the existential threats, which you're focusing on, which is good. I mean, these are great questions. Like how do you save humanity going the way of the dinosaurs? The composition is important in the fine details of what happens, but it's like asking, can you tell me precisely what happens to my house if I use a nuclear weapon inside versus, a ton of chemical explosives? In the end, the answer is they both blow up the house. Okay. And so there comes a point where it's simply overkill. I hate to use the term, but so whether it's a dirty snowball or whether it's a rubble pile, and there's no evidence for any very, very large objects that are not rubble piles in the sense of rotation curves of what we've seen, except for, if you had a core of a planet, maybe, okay, but that's more of a science fiction thing. So I would say no. The general question of, yes, no, can you do it, doesn't depend on whether it's a rubble pile asteroid versus a dirty snowball. What does become an interesting issue is the geometry of the object. Suppose you have some crazy geometry where it had, balls plus, thin interconnects plus balls plus thin interconnects. So, maybe something that was sent our way by some extraterrestrial civilization to harass us. Then you'd want to hit the balls separately from the interconnects. But that's a very hypothetical situation. So, great, great questions. I like the question.
Great,
Thank you.
thank
I
you.
think we need to move forward in the agenda. I think that for me, probably the couple of takeaways is that I think there were some comments earlier that we definitely want to strive to discover those objects early and do any operational in deep space rather than in near Earth space. This is a very last resort type of approach. The other thing takeaway for me is that it's the question of immediacy. So like the video clip in the beginning that says, okay, we have 3 weeks. What do we do? Well, how often do you have a situation where you have 3 weeks, right? And I think this is the driver behind doing something now versus waiting for those 3 weeks to appear. And so my quick question to you, maybe 1 minute, Phil, is what would be a sensible approach to create a reasonable readiness for those situations, right? Given the lack of immediacy or perceived lack of immediacy.
Yeah. So unfortunately, one of the areas that we are misunderstood in and get painted into a corner is that we're only a terminal defense mode system. That is not true. We keep telling everybody who asks us, you're only interested in things, that are last minute. That is not true at all. And so in our papers, we talk about this in detail, but I think it's blown over by most people. This system has much less mass off the launch pad to mitigate a threat, period. So if you want to mitigate a threat, this is extremely useful because you don't require the massive amount of material that you might have in a deflection mission. We've also studied laser ablation. We have chapters and books on laser ablation, which is very much like ion beam deflection. We did studies with JPL on comparing various techniques, ion beam deflection versus laser. So what we're proposing is you can right now have an at-the-ready planetary defense system if you want it. It's a question of will, not way. And so what I would want to leave people with is that this is not a system only for terminal mode. This is a system for any mode. And of course, we want to detect things and mitigate them far away from the Earth so that whatever fragments are generated miss the Earth completely. But that is a good point because we are often misunderstood in that, no matter what we say.
Okay, and there is John who is really want to ask a quick question. So Phil, not more than 1 minute, please.
Yeah, okay, fine. I'll keep it quick.
Thank you. My question was for that terminal defense scenario you were talking about. You talked a lot with various models about showing that this object is essentially obliterated. My question is, what does obliterated mean? What's that definition? Is that all particles or 99.9% of particles are beneath that 20 meters? Do you have a threshold? Are you so confident that we are so overkill here that everything is just going to be powder? What does obliteration mean?
Yeah, so obliteration is not that it is completely obliterated. Oops. Okay, I don't know if can you still hear me? Yes.
We can hear you. Yeah.
Okay, fine. So obliteration is not that you are completely obliterated. Obliteration is what I showed in a plot here. This one. Okay, obliteration is here's a distribution function in diameter in blue. Can you see a plot?
Yeah.
Yes.
Okay, so look at the blue plot, which I guess my cursor doesn't show up here, but the horizontal axis is multiple things, but one of them is in meters. So the blue represents the meter diameter of the material left over after you, quote, obliterate it. You start with things which are quite big, and then shock wave, you quote obliterate it, but obliteration does not mean literal obliteration. Okay, this is a distribution function, and you can see most of the things, the fragments left over, are below a meter. But it doesn't. Again, if you're in the terminal mode, which again we don't want to be in, you can take things all the way up to 10 meters, and it's still relatively harmless. Okay, if you're far away from the Earth, it doesn't matter. You've blown the thing apart. It doesn't matter where you've blown it apart with 50-meter things or 1 centimeter things. They miss the Earth. So that's the key. Does that make sense?
Yes, I think so. Thank you. And that's it makes sense. You would see some kind of statistical distribution like that. You wouldn't have that hard threshold where absolutely 100% will necessarily be below a threshold. But so that makes sense to see. Thank you.
Yeah.
Thank you. Phil, would it be more accurate to characterize it as fragmentation rather than obliteration? And those fragments are going to hit the atmosphere with much larger surface area and cause them to burn out much at a higher altitude and more completely than a single object penetrating down.
Yeah. I'll keep it really quick. First of all, we don't usually use the word obliteration, but we talk about pulverizing things, which can mean different things too. But it's not simply that they burn up higher in the atmosphere. This is another issue. It is true that small things burn up higher in the atmosphere. It is the spatial spread and the temporal spread between the sphere of material coming in that causes the shock waves at the Earth to be decorrelated. So it's both that they burn up at higher altitudes. Yes, that helps a little bit, but it's actually the spatial spread and the temporal spread which allows a series of shock waves. Because a shock, like a thunderclap, is a very short pulse, and then when the next one comes in, they don't overlap in general in time very much.
Yeah, decorrelated. Phil, thank you very much. An amazing talk, super interesting. One last question for me is that if any of those young professionals or students would like to contact you with questions and perhaps even attempt to pursue a career in the area that you are doing the research on, would this be okay?
Absolutely. Yeah. We have lots of undergraduates and high school students, and one of the things they love to do is blow things up. Unfortunately, the university does not allow us to blow things up on campus. I wish they would. But sure, have them contact me. Yeah, you're welcome.
Thank you. Much appreciated. All the best to you. See you at the next presentation. And again, those young professionals and students that would like to learn more about any of the methods presented today, please contact the presenters. They seem to be very happy to give you additional insight, advice, and technical information. So thank you, Phil. All the best to you. And I think now we are going to move to the next talk, which will be by Brent Barbie and Adrian Rudolph, and that's going to be about asteroid disruption for planetary defense and the TERP Raptor mission to Apophis. So hopefully Brent or Adrian or both are online now.
Dr. Melamed?
Yeah?
Yeah, actually.
Yes, hello, Nahum. Can you hear me?
Yes, Brent, I can hear you very well.
Yeah, Brent,
okay, great. Are you able to see my screen share?
Yes, we can see the first slide here.
Okay.
I think Ken wants to say something. Ken, do you have any comment?
Actually, there are actually more questions for Professor Lubin's presentation. The professor will be back in the afternoon for the panel session. So if people have more questions, you can ask him in the panel session in the afternoon. Professor will be back.
Okay, excellent. So hold your questions for the afternoon. And also, if you would like to make contact with Professor Lubin, I'm sure Ken provide you the contact information. Professor Lubin is very happy to answer questions from anyone who is interested in what he described. So feel free to do that either this afternoon or offline. With that, Brent, so Brent is my colleague in organizing the planetary defense conferences that are held every other year at a different location. The next conference will be held in Montreal, Canada. We are actively working on organizing it now, and Brent is the lead organizer of the conferences. I'm happy to support you, Brent, with all of your activities. It's fun working with you. But Brent has a specific story to tell about a special event that will happen in 2029, and that is the passage of asteroid Apophis and what we can do to observe that passage. So, Brent, thank you for presenting today. Take it away.
Thank you, Nahum. So our presentation is going to come in two parts. I'm going to start off by talking about a topic similar to what Phil was discussing, which is asteroid disruption. And then Adrian is going to talk about our mission concept for interacting with Apophis during its 2029 Earth encounter. So you should be able to see my slides. Make sure that's showing it properly. All right, I'm going to put this into presentation mode.
We can see it clearly, Brent.
And then Nahum, can you verify that the slides are still showing up properly?
Brent, we can see your slide very quickly.
Yes.
You can start the presentation.
Okay, perfect. Thanks. All right. Okay, so today I'm going to be talking to you about asteroid disruption for planetary defense, which we've already heard a different perspective about. I won't spend too much time on the preliminaries. We all know that we live in a cosmic shooting gallery. There are many near-Earth asteroids out there, including many that we haven't found yet that could pose impact risks to our planet. At present, we've discovered over 40,000 near-Earth asteroids, as you can see in the chart on the lower right-hand side, available on the Center for Near-Earth Object Studies website. The URL is given there in the graphic. And also on that website, you can see a plot showing explosions of small asteroids in our atmosphere, including the large red data marker there on the plot, which corresponds to the Chelyabinsk impact in February of 2013, which we heard about earlier today. So we get hit by relatively small objects fairly often. Fortunately for us, the size frequency distribution of the asteroids follows a power law, which means that the small objects are exponentially more numerous than the larger objects. And so that simple fact, and combined with the fact that space is absolutely enormous, means that impacts by large objects are rare, while impacts by very small objects are relatively frequent. And of course, we have annual meteor showers caused by the impacts of objects that are the size of sand grains or small pebbles that happen regularly throughout the year, every year. So this plot on the right-hand side is from our National Strategy and Action Plan for Near-Earth Object Preparedness, and it shows the predicted rate of discovery of potentially hazardous asteroids going into the future. The large increases in discovery rates that begin just before 2028 are modeled based on the predicted performance of the INEO Surveyor telescope, which is on track to launch no earlier than the latter part of 2027, and the beginning of full-scale operations by the Rubin Observatory, which will hopefully happen later this year. At present, only about 45% of the near-Earth objects 140 meters and larger have been discovered. And so there's a large number of objects out there that we haven't found yet that could potentially cause serious damage at local or regional levels. We believe we found most of the objects that are on the order of a kilometer in size or larger. Those are the size of objects that we think could cause direct global effects leading up to potentially extinction level events. But those statistics are specific to near-Earth asteroids. There's also long period and single apparition comets and interstellar objects, and our understanding of those populations is much less complete. And so we do have to be prepared for the very unlikely but non-zero possibility of a comet or an interstellar object coming towards our planet with relatively little warning. And so, as was alluded to in the previous talk, if you develop systems that are capable of handling short warning times, which you need to have if you're presented with a short warning time situation and you can't rule out the possibility that you will be presented with a short warning time situation, even with the NEO Surveyor telescope and even with LSST and other next generation surveys. There's simply no way to have a 100% perfect detection system, and there's no way to completely rule out the possibility of having to deal with a short warning impact threat. But that being said, if you develop a system that can handle a short warning threat, then that means that you can use that system in most cases to handle longer term warnings as well. So it's a good design philosophy. On this plot here, which was presented at the 2025 Planetary Defense Conference last year, this plot shows warning time on the horizontal axis and asteroid size on the vertical axis. So this is, in some senses a simplification, but it's a useful one, presented by Chodas et al. I believe Paul's going to be participating in this conference today. And so what you can see is that starting at the upper left, nuclear robust disruption, where we use a single nuclear explosive device in standoff mode, is currently thought to be effective against asteroids about up to 150 meters in size, depending on some variance in strength and composition and things like that. If you want to use a kinetic impactor for robust disruption using a single kinetic impactor, we think that that's our current thinking is that's effective against asteroids up to about 80 meters in size, again, depending on some important assumptions about strength and composition. Now, robust disruption is a great thing to have in your tool belt if you're trying to prevent near-Earth objects from impacting the Earth, especially when warning time is short, for a variety of reasons, not the least of which is that during a short warning time scenario, the strength of the impulse you would need to push the asteroid off course and deflect it as a whole intact object is likely to be a much larger impulse than the object can tolerate. And so you're going to be in a you're going to need robust disruption whether you want to do it or not. So that's one way to think about it. The smallest size asteroid that our current national guiding documents would have us take action against is about 50 meters in size. And we're making the case here that the largest object that we believe, based on our modeling, would be able to be robustly disrupted with a nuclear system is on the order of 150 meters in size. And there are a very large number of near-Earth objects between 50 and 150 meters in size that have not been found yet. And so we're well motivated to have short warning planetary defense systems brought up to being at operational readiness. So let's talk a little bit more about what robust disruption means. Essentially, it means blowing up the asteroid, but we can get a little bit more technical about that. So when we say robust disruption, we mean several things. First, the near-Earth object is forcefully broken up by either a kinetic impactor or a nuclear explosive device into many fragments that are all small and widely scattered. Furthermore, we'd like to design this so that the largest of the remaining fragments is no larger than about 10 meters, so that the atmosphere could easily absorb some of those. And then we want to do the robust disruption far enough in advance of the Earth encounter date so that there's time for the debris to spread out and the vast majority of the fragments will miss the Earth. And then related to that, we want to have some confidence that the resulting transient micrometeoroid flux through the Earth-Moon system will not pose any intolerable threats to space assets in Earth orbit, lunar orbit, on the lunar surface, or anywhere in cislunar space. So there's a lot of modeling work that has yet to be done to sort all of this out, but these are the goals for a robust disruption. This is the way we would like to design these systems, in the way that we would like to design the missions that would deliver these systems to asteroids. On this chart here, I show where we are currently with the modeling. So our research group involves a collaboration between the NASA Goddard Space Flight Center and the Lawrence Livermore National Laboratory, Los Alamos National Laboratory, and Sandia National Laboratory. So we all collaborate together on this problem. And the graphics shown on this slide are taken from a talk we gave at AGU. This paper was led by Katie Kumamoto at Lawrence Livermore. And one of our co-authors, Jason Pearl, is also with us at this conference today. And similar results to these were presented a few months later at the Planetary Defense Conference in 2025 last year. And so one of the things to be aware of is that there's currently not a consensus in the modeling community regarding how robust disruption of asteroids works. There's not a agreement on the resolution at which you need to run these kinds of hydrocode models. And if you run the models at lower resolutions, you can run them out to longer simulation times, and you can see a lot more evolution of a fragment field. But when you run at lower resolution, you have to have some way of having confidence that the results are physical, that they are real, and that they mean what you think that they mean. On the other hand, if you use a very fine resolution, which is what it was done for the array of test cases shown here, it's very difficult to run those models out to long simulation time. So you can't really see the evolution of the fragment fields. And so you have to come up with some heuristics that you can use to gauge, okay, is this object really undergoing what we would consider be a robust disruption, or is it not disrupting, or is it somewhere in between? And so we took the approach here of using higher resolution modeling, for which we have more confidence that the physics are real. But as a consequence, we had to tolerate the fact that we couldn't run these models out to very long times. And so what we looked at is, for example, on the left-hand side, we want to see that the expansion of the object, even at short times, is exceeding the object's initial size. That's one example of metrics that we looked at to assess, whether the object is really undergoing robust disruption or not. And then on the right-hand side, you can see a plot that summarizes all the results across a fairly large number of test cases. And we looked at various metrics, using energy methods to make, to run a simple equation that tries to predict, will the object be robustly disrupted or not disrupted? And we also looked at a different metric that isn't really based on energy so much, but it's a comparison of the delta V imparted to the object by the kinetic impactor to the object's surface escape velocity. And so we found that this metric, the ratio of imparted delta V or effective imparted delta V to surface escape velocity, provided the most predictive power regarding whether the object was going to disrupt or be somewhere in the middle or not disrupt. Whereas the energy methods did not provide us with a good, consistent predictive capability across all these cases. So this is where we currently sit with our heuristics, as we prefer this delta V to V escape heuristic. And in particular, we found that if you want to have confidence that you are indeed robustly disrupting the object, you want the effective imparted delta V to the object to be at least 10 times the surface escape velocity in order to have a robust disruption. Conversely, if you want to have a deflection where you strike the object and you deflect its orbit, but you keep it as an intact whole object, maybe with a little bit of debris, but nothing consequential, then you want the imparted delta V to be no greater than 10% of the surface escape velocity. So these heuristics are summarized with the two equations on this chart. And additionally, there's some other work that's been done by some other research groups in the past, which we're currently in the process of trying to update and do a much deeper dive into, that suggests that if you want to have enough time for the debris to spread out, you want to do the robust disruption at least 3 months before the Earth encounter. So if you take the equation for how much delta V is imparted to an object by a kinetic impactor, which is on the upper right, and you combine that with the heuristics that I've talked about a few minutes ago, you can derive an equation that tells you the size of the largest object that should be robustly disruptible by a kinetic impactor. And that's the equation in the center of this page. It didn't format quite correctly. There's a missing square bracket on the right-hand side to the 1/8 power. So this entire equation is raised to the 1/8 power. So you have to make some assumptions here. One is the delta V to V escape minimum acceptable ratio, which we've set to 10. But of course, you also have to make some assumptions about what beta is going to be. And there's no consensus in the modeling community about that either. That's still an open question that needs a lot more work. But one way to approach that is to make some conservative assumptions about beta. For instance, that beta might be 2, for example, as opposed to some larger number. And if you make those kinds of more conservative assumptions, then what you find is that if you limit your considerations of launch vehicles to a Falcon Heavy expendable, which is a reasonable thing because it's not like we have an SLS rocket sitting around and there's no way we'd be able to get an SLS rocket going on short notice. I think our most realistic chance there would be a Falcon Heavy expendable that would be the maximum capability that I would assume for a situation like this. And so if you assume that and a conservative beta, then the largest size asteroids that you're really going to be able to robustly disrupt with a kinetic impact are top out at maybe 80 to 90 meters in size, something like that. And then if you're doing nuclear robust disruption, as I said before, in standoff mode, and that's an important point because, there's ongoing research looking at other ways of, having the nuclear device interact with the asteroid. But if you focus on standoff mode, which has a lot of benefits because you don't have to worry about trying to touch the asteroid and all the difficulties that can go along with that, then you can make estimates of the robust disruption capabilities using an analytical model for the delta V imparted to the asteroid by the standoff nuclear detonation, an example of which is shown in the right-hand panel. This was presented by Manigan and Berkey of Lawrence Livermore at the 2025 Planetary Defense Conference last year. And so if you combine this analytical model with the heuristics that I mentioned previously, then you can calculate what's the smallest NED I could get away with to robustly disrupt an asteroid, at least as a first order starting point that you would then feed into a higher fidelity analysis pipeline. And so in this numerical example that I'm showing here, the 67 meter size asteroid 2024 YR4, which we had previously thought might hit the Earth, and then after that thought it might hit the Moon, but then that's been ruled out as well. If we look at an exemplar model for that object, about 67 meters and a density of about 3 grams per cubic centimeter, it could be robustly disrupted by using at least a 200 kiloton NED at a height of burst above the asteroid surface of about 46 meters, according to this model. Now, if you're coming in at hypervelocity speeds, you're approaching at 5, 10, 15 kilometers per second, then successfully performing a detonation with such a narrow window of time, because you're coming in really fast at the asteroid, that's difficult. And so in a situation like this, we would probably just deploy a larger NED, like maybe a 1 megaton NED, because that generally won't have any problem, fitting on a spacecraft, again, assuming Falcon Heavy launch capabilities. And then in that case, then you can tolerate a higher height of burst. So you can detonate further away from the asteroid and get the same result. And being able to detonate further from the asteroid makes the mission design more robust, because then you have a larger amount of time available to detect that you're the correct distance for detonation, and then carry out the detonation itself. So I'll close just by pointing out that we've published a couple of journal papers recently. The research group that I mentioned before, you can see everybody's names listed here. We have one paper in the Journal of the Astronautical Sciences all about mission design for dealing with that asteroid 2024 YR4 to show what are some approaches we could have taken to mitigating that asteroid if we had needed to. And then additionally, the second paper is our analysis of the 2025 Planetary Defense Conference hypothetical asteroid impact scenario, in which we go into a lot of detail about how we do the modeling and the trajectory, the spacecraft mission trajectory optimization for these engagements, and the workflows that we go through and the analysis pipelines that we use to design these kinds of planetary defense missions. So Nahum, I'm not sure how you'd like to run it. I'm happy to take a few questions, or we can, you can just move on to Adrian's Turb-Raptor presentation, and we can do questions after that.
Yeah, let's take 5 minutes for questions, because these are two slightly different topics. So we have about 5 minutes for questions for Brent, and then we will move on to Adrian. Are there any questions for Brent?
Yeah, Mr. Helton online, click raise hand.
Yes. Can you hear me okay?
Yes.
Yeah, we can hear you.
Yeah, I question whether this is a good thing to do or not. By disrupting the asteroid, I think what you're doing is just spreading the asteroid material around so that a small part of it won't hurt the Earth. But what you're really doing is putting a lot of stuff into the lunar, cislunar and Mars areas where we are going to be populating that with humans in the next several decades. And so I question whether having an asteroid disruption strategy is a good idea in terms of cleaning up the inner solar system.
So, Mike, I'm going to challenge you on that. There's a 2021 paper published by Patrick King, who's now at the Johns Hopkins Applied Physics Laboratory. And he performed simulations showing how the debris spread out using orbital physics that contradict what you're saying. In other words, it shows that the amount of debris is actually very small. It passes through the Earth-Moon system quickly, and it is no more consequential than annual meteor showers, provided that we hit the asteroid hard enough to indeed robustly disrupt it. That's really the key. So I disagree. I think that this is a good modality for preventing asteroids from impacting the Earth. That being said, if we find the asteroids far enough in advance, then we can deflect it as a whole object with a very small delta V. So the key is to find the asteroids very far in advance. And then if we do that, then we have the option of deflecting it as a whole intact object. But if we discover the asteroid too late in the game, the asteroids simply can't tolerate the deflection impulse. And gentle systems like ion beam deflection necessitate rendezvous with the asteroid. And depending on how challenging the asteroid's orbit is, you might not have that luxury. So we are compelled to operationalize systems like the ones I'm describing that would give us high confidence that we could violently destroy the asteroid and spread the debris out sufficiently so that we would not cause intolerable transient micrometeoroid fluxes in cislunar space.
Well, I agree with you, Brent, on those points. I'm talking about the case where you would disrupt an asteroid and not terminate the asteroid. That is, all the debris would be scattered around the NEO area, near Earth object area.
That's not how it works. If you hit the asteroid hard enough to break it up in a way that meets our definition of a robust disruption, the debris is all moving at fairly high velocities, relatively speaking, away from the original object's center of mass. And that causes the debris to spread out sufficiently to be the way that I described it.
Right, but you're talking about having the debris in termination on the Earth, and that's okay. I'm talking about having all the debris scattered around the Earth, Moon, Mars systems.
Yeah, but that's not how it works. If the asteroid's coming in at the Earth and you destroy it like 3 months before it would encounter the Earth-Moon system at minimum, or further in advance if you can manage it, that debris all spreads out a lot.
Brent, could this be described as a basic management of risks in which you replace some smaller risk or higher risk with a smaller risk?
That's one way to think about it. I mean, again, when the debris spreads out, some of it, especially the small to medium-sized particles, because there's a lot of them, some of those may pass through cislunar space. Some of them even may pass through regions near Earth where we have satellites orbiting. So we want to, and this is part of our current research program, we want to develop models that will allow us to make reliable predictions of statistical predictions of how much additional micrometeoroid flux might pass through those important orbital regions, so that we can do what you said, Nahum. We can say, okay, well, there's maybe a slightly elevated risk of some micrometeoroid flux on satellites, and then that gets compared against the risks of the Earth impact from the original object. So that's a good way to think about it.
Exactly.
Well, thank you, Brent.
Thank you. So, Brent, thank you for the excellent talk. I want to mention that Brent is a professor at Maryland, what is it, Maryland University?
Yeah, I'm full-time at the NASA Goddard Space Flight Center, but I also serve as an adjunct professor at the University of Maryland.
University of Maryland. And being a professor at the University of Maryland, Brent, you may have, I'm not sure if you attended from the beginning, but we have some young professionals and students in the audience, and some of them expressed interest in developing career in the planetary defense STEM area. Would it be okay if people who are interested to get more information about your approach and technique and about maybe even career options or academic options, would it be okay for them to contact you and get some advice from you on that?
Yeah, sure. That'd be fine.
Excellent. So Ken, if there is any interest by any of the attendees to contact any of the presenters, this will be the opportunity to make the contact.
Yes, we do. Brian here has a question. Is okay? Or you
one
want
more
to...
question? Okay. Mm-hmm.
Hi, this is Brian. This is kind of sci-fi, and I'm pretty much a layman. But I was wondering, is it worth it to are these populations of asteroids that we're seeing coming from particular directions? Would it be worth it to I don't know, stick one of these new mini nuclear reactors and some radars on some of these things and let them go out and start mapping those asteroids out there? I know the volumes of space is huge out there, but maybe that could get us some long-range detection or something like that, and just let them piggyback out on an asteroid like Apophis and start mapping.
Yeah. So that's a good idea. Radars, it's tough to do that with radar because radar only works out to relatively short distances because it's severely power limited. Radar is great for if you've already found the asteroid and you want to target that asteroid with radar if it's coming close enough to the Earth for a system like Goldstone to get a good return signal from it, and then you can use that to get a precise range estimate for how far away the asteroid is, which reduces our uncertainty in what the asteroid's orbit around the sun is. Or you can even get resolved radar imagery that will tell us something about the asteroid's surface characteristics or even its shape and so on. And as Russell pointed out in the chat, there's a 1 over r squared power loss for the radar signal going out to the asteroid, and then 1 over r squared radar loss for the return signal bouncing back to the receiver. So it's 1 over r to the 4th. So you can't really go very far out with radar. We've done a number of studies over the years, really over the past couple of decades, just to answer the question, what's the best detection system we could build to find the asteroid, as many asteroids as possible, as quickly as possible, so that we would get that long warning time that you spoke of. And those studies have all converged on the design that NASA is building right now, which is called the INEOS Surveyor Telescope. It's a half-meter thermal infrared space telescope that's under construction now that will launch no earlier than the fall of 2027. As far as I know, it's currently on schedule. In that system, you can see the plot that I have here on the screen on the right-hand side. That plot shows a simulation estimating what the asteroid discovery performance will be for INEOS Surveyor in combination with a new ground-based telescope that's in the process of coming online called the Rubin Observatory. And so you can see on that plot how the vertical axis is the percentage of completion of our discovery of all the undiscovered asteroids, and you can see that as the years go forward, those two new telescope systems will dramatically increase our asteroid discovery rate. And so those are going to be our best bets for finding the asteroids before they find us.
I have a quick question. A significant number of asteroids appear to have orbital satellites of their own. So how do you deal with a situation where you might have a main asteroid that you might want to destroy or whatever, and then you still have the satellite that orbits it continue on that same trajectory?
Yeah, our research group actually, just recently did our very first study of exactly that question. And so we did some preliminary modeling of cases where you can position the nuclear device in between the primary and secondary bodies in the binary asteroid system. And depending on how large the objects are, you can destroy them both simultaneously, or you can destroy one whilst deflecting the other away from Earth impact. And then we also looked at, all the different directions in which you could apply the deflection, the directions in which you could apply the deflecting impulse, and what happens to the binary asteroid system. Under what conditions does it decouple and the two objects then move away independently? And then of those situations, what's the right directionality for that so that the objects miss the Earth rather than hit? So that's all hot off the press. I just ran those simulations a few weeks ago, so it was too soon to put it into this talk. But we are looking at it, and we'll probably publish some journal papers about it in the months and years to come.
Thank you. Brent, can I invite you to give a talk about that next year?
Yeah, sure.
So we will get more information about those binary objects and how we could disrupt them in a way that's useful. I think that by next year, Brent will have more results that could be presentable. And so I'm already inviting you to give another talk next year, Brent.
Yeah. Okay, sounds good. Thanks, Nahum.
Thank you so much. And with that, I suggest we move forward to Adrian, who's going to give a really, really cool talk about their mission to Apophis. This is a really cool student project that is managed by the students and guided by Brent. So Adrian, take it away.
Okay, I can do that. Wrong screen. Can you see this all right?
Yep, loud and clear.
Okay, perfect. Hello, everyone. It is great to be here. Thanks, Nahum, for inviting me to talk again this year. So first of all, I love the discussion between deflection and disruption, and late time terminal disruption, and how fragments can, move through the Earth-Moon system. Mapping the trajectories of those fragments is part of my research, but when I'm not doing my research, I'm also working on a CubeSat mission called TurboRaptor. And with the deflection and disruption thing, I can tell you that it doesn't really matter, because either way you need to know the mass of an asteroid in order to be able to do deflection or disruption, which is what I'm going to talk to you about today. And hopefully this will move forward. There we go. Okay. So asteroid mass is the most important physical property that we can measure for planetary defense. If you want to understand how to deflect an asteroid off of its trajectory, you need to understand how massive it is, so you can design your impactor to impact the asteroid in such a way that it will actually move it. And then if you want to disrupt an asteroid, you also need to know the same thing. What is it? What kind of energy, what kind of impact is it going to take to completely blow an asteroid apart? And so, it's not like we can just, we've done the DART mission, but it's not like we can just go out every day and get mass measurements of asteroids and chuck them into our models, which would be really nice. So there's one particular exciting event that's going to be coming in a few years. I think Professor Lubin had touched on it a little bit. But essentially, knowing the mass of an asteroid, or masses of asteroids in a population, it's very important for our modeling purposes, so that way not only can we understand how to deflect or disrupt an asteroid, but what happens afterwards. So if we disrupt an asteroid and the fragments are still moving through the Earth-Moon system where they're projected to, you need to know the mass in order to calculate the kinetic energies of those fragments. So I have an image of the Chelyabinsk impact over here, which I believe came from everybody always touches on this, but I believe it came from the sunward direction, and so we didn't really see it coming. And Chelyabinsk was an important event because a lot of people were watching this giant fireball go across the sky, and people had their noses pressed up against window panes and glass, and they were looking out windows of cars. And when this thing finally burst in the air, it created a wave that took out all of the glass. It shattered all the glass, and so people got hurt from that. So had we, first of all, had more time, and second of all, had a better estimate of its mass and its kinetic energy as it was coming through the atmosphere, maybe we could have given people a better warning, like, hey, don't put your nose up against the glass and look outside, because that can be very dangerous. So asteroid mass is very important. That's the main takeaway from this, and it's also incredibly hard to measure during a high-speed flyby. So we can rendezvous with asteroids and stay there for days, weeks, and kind of dance around, move around the asteroid and figure out how the spacecraft is affected by the asteroid's gravity, and you can get a mass measurement that way. But in the case of a terminal situation where you have an asteroid that's on an impact trajectory and you may not have very long to do something about it, you might just need to send a spacecraft out really fast to do something about it, or to learn about it, to perform reconnaissance. And doing this during a high-speed flyby is incredibly difficult. So there was a previous study that looked at measuring the mass of an asteroid with a flyby, and how it works is in general, a spacecraft will travel past the asteroid at a certain distance, and because that asteroid has gravity, it has mass, it will bend the trajectory of that spacecraft or that object, whatever is flying past it. So there was a previous NIAC study that looked at using a spacecraft and multiple small probes or widgets that would be deployed or released from the spacecraft, and they would all just kind of fly past the asteroid. And using optical instruments and maybe catching one or two, maybe a couple of the objects, they might be able to get some kind of estimate on the bend in their trajectory, and be able to further get an estimate on the mass of the asteroid. So by the same authors that did this study, there was a more recent one that came out where they explored, instead of using a bunch of widgets and probes and optical instruments, can we actually use a laser-based ranging system between two spacecraft? So they found that the optical detection times were late, and the knowledge on the trajectory of the targets is a lot slower. So using light is a lot faster. Using laser ranging might be a lot faster. And so that was something that we decided to explore for our Terpraptor mission. But I'll get to that in a minute. So we've talked about Apophis a little bit, I think, in the last couple of hours. But I really want to hit this home because Apophis is my favorite asteroid, and this event is really freaking cool. So Apophis is going to be making this extraordinary close approach to Earth on Friday the 13th of April of 2029. And it's going to fly past the Earth really, really close. It's even going to get somewhat close to the moon, according to this this graphic. And this happens once, maybe every 7,500 years. Maybe every 10,000 years. Who knows? We can't tell it that perfectly. But your great whatever grandkids and their great-grandkids and their great-grandkids and so on and so forth will not see something like this again for a very, very long time. And space is enormous. Space is huge. So the fact that something this big is going to be getting this close to us and not hitting us should blow your mind. It is positively insane. Okay, I'll step off my soapbox now. So Apophis, since it'll be getting so close to Earth, it'll be experiencing effects from Earth's gravity field. So scientists are suspecting that it might alter obviously it's going to alter the trajectory of Apophis, but its rotation, it might move some of the surface material around. And so the European Space Agency right now is putting together a mission called Ramses. which some of you may have already heard of, and they are planning to rendezvous with Apophis a couple of months before its closest approach and fly with it throughout its approach with Earth, getting all kinds of data and imagery and whatnot. And then NASA will be reusing their OSIRIS-REx mission, which brought back samples from Bennu, asteroid Bennu, and they will be going to Apophis a couple of months after its closest approach. So we're trying to get as much data on this asteroid as possible because it is coming to our backyard and giving us a chance to actually visit. And one of the things that I like to say is that it's like a day at the zoo. It's like going to the zoo and getting to stand behind the fence and look at the bear or the lion or the giant thing that wants to eat you, but it's not going to because it's far enough away from you. So Apophis is roughly 350 meters in size, 340, 370, whatever. It's roughly in that range. It's about the size of the Eiffel Tower. It'll be passing within 32,000 kilometers of Earth's surface, as you can see in the GIF here. All the little blue dots, that is our geosynchronous orbit belt where a lot of our very important satellites are at, where they orbit. And Apophis is going to be coming uncomfortably close to some of them, I suspect. But the asteroid will be naked eye visible for many people at night across Europe, Africa, and West Asia. So in April of 2029, if any of you don't currently have something to do, or if you're planning a family vacation somewhere, I would suggest going to one of these places. Go to Spain, go to Madrid, go to Cairo in Egypt, go to France, somewhere over there so you can actually see this thing, because it will look like a kind of like a bright star moving across the sky. And like I said, it's incredibly rare. So please make your vacation plans now and go see it. So as of right now, this is what we think Apophis might look like. The left is a picture from a paper, and they roughly think that Apophis might be kind of like a peanut in shape. The right is some of our radar data on Apophis. We don't perfectly know what it looks like, which is, of course, why we want to go and study it so much. And yeah, I keep mentioning this, but Earth is dodging this giant bullet, and if it, it's not going to hit, but if it were, it would be a very bad day for a lot of people. It's roughly the equivalent to 50,000 World War II atomic bombs. So you can use your imaginations to think of what kind of destruction that could cause. And while that is missing us, we may not be so lucky one day, which is why Apophis is a wonderful opportunity to study an asteroid of this type. So there are also lots of guiding documents that tell us why, or what the need is for studying near-Earth objects and potentially hazardous asteroids, especially reconnaissance capabilities. So at the White House level, at the NASA level, even just broadly across the scientific community, the 2023 Decadal Survey, for example, states that our highest priority after NEO Surveyor goes up should be a rapid response flyby reconnaissance mission to a challenging near-Earth object. And that is pretty much what we intend to do with TURP Raptor. So for those of you that have not heard of this, TURP Raptor has been in development for almost 2 years now. It started as a CubeSat space mission project in Professor Barbie's near-Earth object class. And over time, it has turned into a real mission. We're planning to send a 12U CubeSat out to Apophis a few months before its closest approach with Earth. So we would be getting there in December of 2028. Whereas Ramses would, I think rendezvousing in February. I could have that wrong, but roughly. So we would, in that case, be the first to Apophis We've undergone many design iterations, and I'm really excited to talk about the mission today. So our science objectives, there's two main objectives, but we are responsive to the decadal survey and the NASA's SBAG, Apophis Specific Action Team report. So we want to understand the global shape. We want to get a shape model of Apophis. How big is it? What's the diameter? What is happening on the surface? What does the regolith look like? What is the distribution of boulders and distribution of craters? And with that, we also want to get a mass measurement of the asteroid. So here's what we plan to do. In June of 2028, we would launch with a host spacecraft out to, I believe, 0.37 AU away from Earth. We would launch with a host spacecraft, and it would be roughly a 6-month journey out to Apophis. And a few weeks before we get to Apophis, we would deploy and commission and do some basic cleanup maneuvers before we fly by. And then together, the host spacecraft and our CubeSat would fly on either side of the asteroid at roughly 1.8 kilometers per second. And our CubeSat, it will have an imager on board, so we can get images of the surface and be able to get our shape model of Apophis. But we'll also carry retroreflectors. So I mentioned earlier the study that looked at laser ranging between two spacecraft, and that's exactly what we intend to do. The host spacecraft will host a LiDAR on board, and they will use that to bounce the laser signal off of our CubeSat. So our CubeSat is essentially the widget or the probe in this case. They will be measuring the bend in our CubeSat's trajectory in order to estimate the mass of Apophis. So the other spacecraft will also have some other imagers and spectrometers on board. But we believe that this laser ranging technique should yield a 7 times improvement over using just cameras and this OpGrav technique that I had very first talked about, which is incredibly cool that we can do that. So we won't technically be able to tell the mass of Apophis perfectly because in science that's really difficult to do, and so of course we'll be able to get our shape model, but the point that we're trying to get across is to that we want to reduce the uncertainty in the mass. So the OSIRIS Apex team put out a paper that explained what the uncertainty in the density and the mass or the gravitational parameter of Apophis would be before any in-space measurements, so just getting measurements from the ground. And then over on the right, we talk about, or we have listed what we think the uncertainty would be after a flyby. So if we, based on our preliminary analysis, if we can perform the flyby correctly and get our laser ranging technique to work, we should be able to take the bulk density of the asteroid's uncertainty from 73% down to around 20%. And then the gravitational parameter, which is based on mass, down from 89% to 15%. And that, again, that's just a preliminary analysis, but that just comes to show the difference in the measurements that we currently have of Apophis and what this new technique can demonstrate. And then also, knowing more about the density and the mass, we can reduce the uncertainty in the porosity of the asteroid as well. So if, we work with the national labs to put together all these models on what happens when you disrupt or blow up an asteroid. If your uncertainty in these parameters goes down, then your models tend to be more accurate. So just revisiting why knowing asteroid mass is important. The heavier or bigger an asteroid is, it takes a lot more oomph to deflect it off its trajectory and a lot more explosive force to break it apart. So just keep this in mind. And then I had mentioned Ramses and Apex earlier, but we fully intend to cooperate and collaborate with these missions and provide any data that we can. About a month ago, we had talked with someone from the Osiris Apex team, and they told us how valuable the combination of a shape model and an asteroid mass measurement would be to helping them refine parts of their own mission. So we would love to, and any data that we get, we would love to share, of course, with the public and with the other missions as well. So just, this is our mission progress. This is our CubeSat. As I said, outfitted with retroreflectors. It'll have an imager on board. We will not be doing any comms with Earth, so we'll be relaying those through our host spacecraft. We have identified a host, a mission partner, which is very exciting. We have grown our team quite a bit in the last year, and we have an official endorsement from the University of Maryland, from our own president, a president of the university. And we've been very fortunate to work with NASA Goddard and Wallops and the Aerospace Corporation to rapidly mature our design. We've crowdfunded quite a bit in the last month, and we also now have workspace to build our spacecraft at NASA Goddard, which is incredibly exciting. And we also have funds, so we're going to be procuring parts very soon, within the next month or so, at least putting in orders for those, and we're going to Apophis. So yeah, if you guys have any questions, please feel free to either ask them now or you can email me. I'm happy to talk about anything young professional related. I'm happy to talk about Apophis. I'm happy to talk about my research. So thanks for listening.
I will just comment that this is an amazing student project, that anyone who is interested in the topic and would like to develop his career along the planetary defense community, feel free to approach Adrian and Brent about the project. You can learn a lot from the path that Adrian has taken. Really an amazing project, and amazing information that's going to flow down in just about 2 or 3 years. We are kind of falling behind. Do we have any question, maybe room for one question, either online or from the audience? And if not, I don't see any questions popping up. So Adrian, amazing talk. Good luck with the mission to you and to Brent. Thank you for presenting.
I'm sorry. I think Mr. Breza raised hand.
Oh, okay. Yeah. So
can you hear me?
Yes.
Yeah. So my question is, and I've been thinking about this a lot lately, and I think other people are. It sounds like the Apophis asteroid is, they clarified online, that's a S-type asteroid, which has a lot of value in it. And so I'm looking at all of these bigger or larger asteroids having value to somebody in the future or an entity in the future. So is there, I know it's a quick time to try to pull it around and actually turn that in to, instead of just watching it, let's bring it either to an orbit where we can start mining it and making use of that. And to go a little bit farther with this, there seems to be funding issues with planetary defense. Why don't we offer an asteroid mining rights platform where people can purchase, or entities can purchase, the asteroids and therefore fund planetary defense? So that's more of a comment at the end there.
Okay, so your first question was, why
type
can't
of
we?
asteroid.
Is there any entities that would like to capture Apophis and take it on as their own and start mining it, since it is going to be so close?
Sure, that's a great question. So Apophis is a stony asteroid. They think it's got a mixture of olivine and nickel and iron. But I can tell you that the companies that I've interacted with that are interested in asteroid mining are interested in platinum group metals as well as water or ice. So being able to use those materials for either just bringing them back to sell and make money, or to be able to use for in-space propulsion. So Apophis is, as far as I know, not the best target for mining, at least in the case that you're talking about. It would be great if we could bring a sample back like we did with Bennu, but that's not the mining that you're referring to. But then your other comment would probably be better answered by maybe Brent, actually. I probably can't speak too much to that.
Okay. And then what does the TERP Raptor acronym stand for? Thank you.
Sure. So it stands for Terrapin, because we're the Terps, we're the turtles at Maryland. The Terrapin Engineered Rideshare Probe for Rapid Apophis Profiling, Tracking, Observing, and Reconnaissance. It's a mouthful.
I grew up in Maryland, so go Maryland.
Go Terps, go Maryland.
Yeah, I think this is an acronym that's going to be popularized very soon, and certainly in 2029, everybody is going to know what it means. So, wonderful presentation, Adrian. Good to see you again. Hopefully, we'll see you soon at one of the conferences or events.
Is this better?
Barely. Either you kind of put the microphone into your mouth. I don't know if it's possible there to do that. But yeah. Okay. Sounds like we have to try to sharpen our ears to hear Joe. Sounds like talks from the room are going to be potentially problematic.
Now, can you hear me better?
Yes, we can hear you better. A bit of a, yeah, we can hear you better.
Okay. Even better?
Try to speak close to the microphone as you can, Joe. But yeah, continue.
Okay. It occurs to me that small satellites are getting better and better, more and more capable. But there's a unique opportunity with asteroids, particularly near-Earth objects, that you can't do with any other kind of spacecraft. How do I get the next? Okay. Planetary missions are, oops, there, okay. Planetary missions are, the requirements on them, okay, great. The requirements on them depend on the planet, the temperature, the pressure, the radiation, the distance, all that drives everything. And so as a result, you have to do a custom design. The sensors are custom, the rides are custom, the team is usually custom. And so we end up with launches less than once a year. Okay. NEOs and other asteroids and comets, they're not unique in any way, shape, or form like planets are. Okay? There are thousands of them just in the NEO category. And we can take advantage of that. We can actually justify a production line of satellites. And the more we plan to do, the more we can spend on shrinking them so that they don't cost so much to launch. So, NEOs are also distinct from planets because they're not just potential resources, but threats. Planets aren't threats to us, okay? Small satellites of one design can usually start one of many different NEOs. Okay. Now let's see, I've lost the image. Okay. So the idea is forget about one-of-a-kind custom missions and do what we're so good at, and what Henry Ford and other people have figured out how to do, which is production lines. And there's another factor, which is if you're interested particularly in NEOs, as well as named out asteroids, we're going to be finding a lot more of those in the next 10 years because of the legacy survey of space and time, whatever it's called, the Rubin telescope survey that's finding lots of stuff. The rate at which it's going to go find new things is going to decay over the next 10 years. But it's going gangbusters, okay? And then it will grow probably even faster when we get the NEO Surveyor launched, perhaps late next year. They're going to tell us a whole bunch more places to go, okay? So we don't need to get ready to fly stuff right now. Just the Apophis study, the TERP study, that's a one-of-a-kind thing like a Planet mission. So it's a unique opportunity to use it, okay? It's kind of like the Grand Tour in the late 70s that you took advantage of the alignment of the outer planets to have one spacecraft do all of them. NEOs are going to be different. If you don't catch one, you can catch the next one. The key thing is you want to get statistically good data. You want to get data on hundreds of them, okay? So this slide presentation first started out as cheaper by the dozen. I now think cheaper by the gross. Maybe you'll fly a couple dozen on one mission, and every year or so you'll fly a couple dozen more with slight refinements of the software and hardware. So let's think about this as a statistically important thing to do, to learn about. What can you learn about NEOs that you can see from the ground that you can understand better because you've seen it up close in other statistically significant numbers, okay? We don't know albedo to better than a factor of 2.5 or so. That means mass, we don't know better than a factor of 4. Okay? We can improve on that. We can figure out what are the correlations between the spectrum that tells us what the albedo might be, et cetera. Not, 3 digits, but to the first significant digit. Okay? So let's see. Okay. What will drive the design for an array of, or a production line of NEO survey satellites? They all have different orbits, so they each have a different ride. Okay, so that's expensive. You either have dedicated launches or you have a ride to escape, and then you go different directions and take advantage of multiple gravity assists. So you have to have substantial onboard capability, but you can leverage that over a year or two to get to different orbits. Sometimes the orbits will allow an affordable flyby, and others, less common, will let you actually end up with an asteroid flying by. It's not certain to me whether small thrusters, ion thrusters, will be better than small solar sails. there is an advantage in solar sails that they get easier as they get smaller, whereas ion thrusters, the constraints on the design make it harder to make good ones in smaller scales. The next thing to think about, besides the fact that everything's in different orbits and you have to figure out how to get there for each one, is downlink rate imagery, mostly, and distance drive small spacecraft design. Okay. For deep space nanosats, the comlink is king. Get used to it. I remember reading something like one of the early microsat developers, let the guy, the RF guy, be the project manager because he's going to make all the decisions anyway. Okay. So find minimum, here's a possibility to consider, an option to consider. Find the minimum viable comlink and see what you can do with that. And that leads me to what drives the comlinks, okay? When you shrink a spacecraft, let's say linearly in dimensions, in linear dimensions, if you try it by a factor of 2, the original size, well, the good news is that the weight has gone down by a factor of 8, yay. But the power has gone down by a factor of 4, and the gain of the antenna has gone down by a factor of 4 using the same frequency. And then because you've got a smaller project, you probably have a smaller antenna receiving it. So it may go down by a factor of 64 for that shrink. Okay. What gets worse is when you start thinking LEO, 400 kilometers up, right overhead, call that 1 as a signal. When you're out at the horizon, it's 10 times further away, so your signal strength is a factor of 100 less. You go to GEO, it's 10 to the 4th less. The moon, it's 10 to the 6th lower. And 1 AU is 10 to the 11th. Okay? So, again, small satellites, large distances, the commonly is gained. So, what option should we consider? RF turns out to take about a factor of 100 less energy per bit than laser quantum. Okay, big hit. RF receiving antenna area is much cheaper. Call that a factor of 100. And deployable nanosat RF antennas probably get a factor of roughly 1,000. So those factors add up to 10 million. But gain from a laser with a nanosat class aperture can give you a gain of 50 billion. Okay? You have to point the thing precisely. At 1 AU, the spot beam is not going to be the size of the Earth. It's going to be a little bit smaller. You have to aim at the spot on the Earth to make it seen. But that the gain is, well, 50 billion minus 10 million, it's a factor of 5,000 more. So it's worth considering. But the real clincher that says, hey, seriously consider a laser is the laser telescope. It has to be able to precisely point. And it's a big camera. It's a telescope. You can use it. It's not just a comlink. It's the telescope. It's the science device. Okay? So there could be some arguments for RF that swamp those, but I'm going to take the laser comlink. Okay? One of the problems is you do have to aim it precisely. Fortunately, cameras are getting tiny. You know, when you have a cell phone that has 3 or 4 cameras know that the cameras themselves are very tiny. Okay? You can put cameras in any direction you want, including the sun, on a telescope, to get yourself oriented well enough to point the main telescope at the Earth. Okay? And with enough different views, one of the problems with star tracking cameras is you need a really good lens shade to be able to see most of the sky without seeing the Earth or the moon or the sun. Okay? But if you have cameras in every direction and they are small enough that heat sinking is not a problem, you need to have the image for tracking the sun and not damage it. Small cameras can be quite good at finding the Earth, finding that, if you have a reference map of where you think you are in the solar system, you can look at the planets and triangulate and then find Earth. You can aim something accurate. Okay. The software is not going to be trivial, but it's a workable thing. The key issue is you actually not just need to know where to point, you have to be able to point. Okay? Very small reaction wheels in a heliocentric environment where you don't have to worry about the magnetic field. But the sun's magnetic field is about 150,000 strong spirits. I was surprised to find out how many lower satellites. The steel in the battery is the dominant working device. Okay, you don't have to worry about that in heliocentric orbit very much. But you use reaction wheels, and then you have sun flaps that the sun pressure has a torque that's small, but it's enough to desaturate any tiny reaction wheels. So this is a small device, but it's got a lot of requirements on it, and it's going to take a while to get right. So you can start flying this in LEO cheaply, learn what you're doing, so that by the time you get the second or third or fourth time right, it's actually justified. You've got a pretty good chance of the hardware, software, and the team making everything work. So what else can laser-comm telescopes do? Well, hyperspectral imaging data. And the lineup here shows a bunch of beam splitters that allow different parts of the spectrum to sample their wavelengths with different measures. Trying to get some thermal IR is important because if you're near a NEO and just knowing the direction of the spin is useful because that tells you something about the Okosky effect. And knowing that lets you figure out the orbit, not just 100 years, but several hundred years. But you'd really like to know quantitatively the IR on one side versus the other, fly around, get image data, get thermal imaging data, and then you can better quantify the Okosky effect that is the largest perturbation on long-term orbit predictions. The second category here, you can station heat with EOS. And the solar pressure is, if you're close enough, then you can actually get captured, but the orbit will be a perturbed one, and so you may have to do some small thrusting to handle the stable orbit with the solar pressure. And the laser beam can be 1,000 times brighter than a 100-meter NEO in the sun. And so when a NEO is far from the Earth, you can still track it from Earth if there's a laser beam aimed at Earth. And then long laser pulse trains can be allow very precise imaging, ranging, and that's useful. Okay, again, quantifying the dark cosmic effect is useful. And then also, while getting to a target, you can do flybys of other objects. And by the time we have 10 years from now, roughly 10 times as many NEOs, there will be roughly 100 times as many flyby opportunities. Okay. And so flyby opportunities, you'll be going by fast, but you have a good telescope so you can take images on the way. And you can also do things where the rate at which you're passing tells you the range. That tells you something about what the actual size of that flyby asteroid is. And you can also triangulate a nearby asteroid that Earth has uncertainties about the distance for some characteristics of it. You can, when flying by, triangulate it against the star field. And eventually, in a later group being launched together before going their separate ways, you can have a rover that can hop and try to push rocks, find out are they loose. Okay, and the satellite also serves as the conduit in both directions. So, how to fly to 100 NEOs without 100 launches? And this, I'm assuming here, it's a solar sail, but you can use ion thrusters. You can develop small enough ones that work well. Get a group ride to escape. I had shown some designs that are kind of rectangular, but they may be trapezoidal, stacked in a ring inside a plant band or something for the primary payload that's going to orbit, going to escape. And by the way, you don't want to use your high ISP or solar sailing thrust capability to spiral out to escape, because 3 months of that is worth 50 years of heliocentric orbit radiation doses. You don't want to do that. But you buy the right to escape and then go separate ways. Okay. And you can do much better than your own thrust capability by solar sails or ion thrusters if you take advantage of Earth gravity assists or Mars or Venus gravity assists. Okay? So take advantage of that. And again, if we have 10 times as many NEOs, it's going to be 10 times or maybe even 30 or 100 times easier to find good passes, gravity assist passes to amplify your own onboard capability, delta V capability. Key conclusions. NEO threats and resources each justify a broad sampling of NEOs. The things that we want to learn from threats versus resources are somewhat different, and the things that we the places, the NEOs that we may want to study for threats and resources may be different, but you're going to want to have a lot of the same sensor capabilities for both. And again, we're going to have far more reach for the NEOs to study in 10 years. We won't need to fly this next year. We can spend the next 5 or 10 years developing and testing stuff in LEO, and eventually going beyond that. The comm link is king, get used to it. Okay? Just think of the comm link as a basic thing, and then what you have to add to make it useful as a sensory, as a data collection device. And plan on LEO iterations of tests in LEO expensive rise to escape. Most of the design may be fairly easy because there's so many teams doing so many things that have similarities with this in size, etc. But designed for low mass optics that will stay precise after the shape and date of launch, that is going to be difficult. 10 years ago, stumbled across a website, later became sensitive and taken off because it was too valuable. It was lessons learned. And one of them was never put your optical bench in low after your primary load per launch. Okay. But that's an issue you have to worry about. And the key thing is nanosats aren't small, but still not growable. A software engineer can create more obscure failure modes than a mechanical engineer can in one session than that mechanical engineer can in a year. Okay. So, as Rick Cleater once said, he looked at the budget for his prior project and he realized that he should really say that we didn't develop a spacecraft, we wrote it, because most of the budget was for software. That's going to be true here. So that's it. Have a few minutes to answer questions.
Thank you, Joe. Definitely interesting concept that you've been studying for many, many years. And thank you for updating us on the concept. Ken, are there any questions either in the room or online?
Yeah, yes.
Hi, Joe.
Yes.
When you say nanosats, do you mean something like the CubeSat?
Okay. In the world of small satellites, microsat is 10 to 100 kilograms, nanosat is 1 to 10 picosats under a kilogram.
10 kilograms?
So 1 to 10 kilograms is the most common definition of nanosat. And I think that's likely to be what this ends up being. I don't think you can justify picosats because it costs too much to shrink it and you don't pay them less in launch costs. But I don't think you need to have something more than 10 kilograms. But that's subject to actual development.
So there's a lot of asteroids that fly by the Earth. So like last year in 2025, there was observed 188 of them that went sublunar within the with Earth flyby within the lunar distance, but they tend to be quite fast. And I just wonder what can you do with a nanosat, with respect to that kind of asteroids?
The technique that I have proposed for Delta V is a combination of get a ride to escape with a bunch of others, and then use some slow Delta V to align yourself for Earth assistance, okay? That's good for things that aren't particularly close by. Anything close by, not only do you have to get fast now, but you have to do it at the time it's going by, okay? So that's going to end up needing a high delta V chemical propellant. The question is, there are various companies doing small propulsion systems, and Stellar Explanations in San Luis Obispo is one. There are many others. The guy that used to be propulsion head of SpaceX started a company, I think, Impulse. And there are various others. So it's going to be a byproduct for that solution. And it's going to be just one rather than 20, maybe 2 conceivably. But that can use the same satellite, but it's going to have a unique propulsion system for its needs.
Thank you, Joe. Any other questions?
Yeah, I'll repeat your question. I looked at some work several years ago on that 3D. Also, demonstrate, for example, the Jovian system, or to go, wherever we want to go in the solar system. So, have you looked at using those low consumption trajectories? No. The thing that I focused on is the idea that a laser comm telescope is almost a complete useful spacecraft. Okay, and it can be much cheaper to launch in any direction because it's so small. Okay, and the concept of getting a ganged ride to escape and then going separate ways, that is one of several. I mean, what you need for what you want to do is different. That's different. I'm just trying to get the idea of a laser comm telescope as a useful NEO mission that ought to be much mass produced. Okay, and I'm 78. I actually gave a presentation of this in 2010 to the University of Maryland, an earlier version of this. But the fact that we've got, at the time, I don't even think the Vera Rubin was fully funded. Okay, and Neo Surveyor was just a gleam, and Rusty Schweikert's and the B612 team. Now we're actually getting real data, and so this is timely for much younger people, including perhaps undergrad and grad students, to tackle. If it's going to take another 10 years, I'm not going to be functional in 10 years. In terms of your focus, have you looked at flying arrays of these satellites to improve the interferometry, for example? No, I haven't. And one of the issues is trying to do anything precise with a small satellite. Interferometry, I was involved in a JPL analysis of a tethered interferometer, and the tether dynamics made it really ugly. Okay, small spacecraft, you have to be careful of the solar pressure torque, and all sorts of other things. But that's that's a challenge for other people to tackle. Okay, take this one widget. The telescope is the spacecraft as the best approximation you can make, and what can you do with it, and what are the different widgets? People use Model Ts for far more ways than Henry Ford ever thought. That's your job. Okay.
So, Joe, first of all, we can hear you better with the wireless mic. That's one thing to use. And I have a question along these lines of the last question. I think earlier you said that we should consider mass production of small satellites, nanosatellites that will travel, might be dedicated to specific objects, and will be scattered around the solar system. But those solar cell satellites can just could loiter in the solar system and visit multiple objects, right? They don't have to be dedicated to one.
Yes.
Flybys. How would this compare to have a dedicated satellite for each object versus maybe a smaller number of satellites that will visit much larger number of objects?
If you're doing, well, the big trade on that is what are the differences that you need for each unique object. And the advantage of NEOs is that as a first approximation, they're in a few small, there are many of a few different kinds in many different orbits. That's what causes distinctly unique challenges and opportunities. But for flybys, if you're having flybys in various parts of the solar system, you're going to see more things, especially if you go inboard of Earth. You're going to see asteroids that, well, the NEO Surveyor is going to do this. It's going to go inboard, so it's going to see the sunlit sides of things as well, and the thermal properties of the sunlit side of objects that are not easily visible from Earth distance or further from the sun. So that's really doing that, but that takes a much larger spacecraft to do well. Okay. Let me mention one other thing. When I first got involved in space, it was the early 1 year into the shuttle flight program. Okay. And there was something just invented called the gas can, getaway special canister. It's a garbage can. It could handle payloads up to 200 pounds. And as I recall, the gas can itself empty weighed more than that. Okay. CubeSats are almost the same. The Peapod weighs about as much as the CubeSats. Okay. One can do better, but the real challenge is if you're a secondary payload, the primary ride challenge is not paying for it. It's making sure that under no conditions will you mess up the primary mission. Okay. I flew 3 experiments in 1 year as Delta secondary payloads on GPS launches, government Air Force launches. NASA and the Air Force, now Space Force, are explicitly challenged to support U.S. industry. And so you can justify getting in the door to say, I'd like to fly my experiment on your rocket. I asked the guy that I was dealing with at McDonnell Douglas, because it was a Delta, about flying on a commercial mission. And he said, I would not even consider asking my customer whether he would consider that, because they pay for insurance on launch. And once you go and do something different, the premium is going to go up, maybe $1 million. Okay. And that's a lot more than the justification for flying small payloads. So the real challenge is if it's a well done, safe array of payloads that can't do any damage, then you'll be able to fly fly things, especially the second time you fly them. It may be painful the first time. But you have to make sure that your design is bulletproof from the point of view of the primary payload. So, for example, the most important thing of a separation system is not that it separates, but that it not separate prematurely. Okay. Far more important if you're a secondary payload.
Yeah. Okay, Joe, I think we need to move on. There is a hands up by Mark Henley. So let's give it just 1 minute for Mark to ask a very brief question.
Sure.
And then
Dr. Milliman, there is a gentleman here. He has a question.
Well, should I go?
Should I?
Mark and then this.
Okay.
Yeah. Hey, Joe.
Hi.
Listen, a few years ago, I presented at this mini conference some ideas about using laser reflections rather than radar to find NEOs that were, in particular toward the sun, where you don't have good telescope observations. And wondered if the system you're talking about would also naturally be able to do that. So it would be, kind of like
I don't know.
Very brief answer, please.
I think that the telescopes and lasers and laser power are far cheaper on the ground than in space. So I would think that the place to start would be doing that from Earth.
Yeah. Good idea.
Okay. Your question.
I had a question about power.
Yeah.
So this wasn't quite the focus, but ion propulsion versus something like solar sailing. One of the challenges with ion is always just enormous power needs.
Yeah.
Do you know? I mean, obviously, there's work to go on shrinking these things down. Do you know if there's if we're anywhere close to where that could be used on a small sat?
You know, in larger scales, the typical power is 20 kilowatts per Newton. Okay. If you can scale it down, it's 20 watts per millinewton. I don't know that anybody's done that, and I don't know if it's even possible to do that, but that or solar sails are the best comparison options that I know of. Okay. And if this had to fly next year, I'd say you got to do a solar sail. You can't guarantee that you'll have ion thrusters, but people are working on ion thrusters, and in particular, I think it's MIT is working on what are called ionic fluids, where you can actually get some of fragments of a fluid to be positively charged and negatively charged. You squirt them in parallel. I don't know how well that's working.
And then as a follow-on to that, you touched on it briefly, but the laser, what were the power comparisons of that? I couldn't quite tell. At the end of the day, when all those factors were multiplied together.
Okay.
Versus RF.
Laser diodes can be 45% efficient in near IR. In particular, 810 nanometer, 808 to 810 nanometer. And this was 15 years ago. Okay, it's probably better now. But you could get a half-watt output laser that would, it's just that big. And you're going to be running it at 50% or lower duty cycle. So the total power dissipation isn't a big deal, and the total power usage isn't a big deal. And you can have, the fact that you've got 5,000 times as much data per dollar potentially, it says really can try and make that work right. Okay, and I think you can get data that a 2-meter telescope on Earth that costs millions of bucks but not billions could be the receiving end, and sending stuff back. You would probably use a green laser or near IR to send back. Okay,
but in terms of just total power requirements comparing to RF,
it shouldn't be a dominant issue.
Okay, thank you.
I think we need to move forward here. These are good questions. Please feel free to interact with Joe. Sounds like the question came from the room. So you're all in the room. Feel free to network there and ask those questions. But now it's time to move to our next talk, which will be by Dr. Russell Henry Terbick about radar detection of asteroid 2024 YR4 in a planetary defense mission, which is an interesting asteroid. I think there's a bit of a story behind it. So please introduce yourself, what do you do, where you work, and take it away.
Hello. First off, can everyone hear me, and can everyone see my screen?
Yes, both.
Excellent. Okay, so my name is Russell Terbick. I'm a physicist at Sandia National Laboratories in Albuquerque, New Mexico. These days, I do a lot of work on radar development for planetary defense. So in a nutshell, if we have a very, very big asteroid and not a whole lot of waiting time, then a nuclear deflection or disruption is pretty much the way to go for getting rid of that threat. And if I know that you folks are taking a lot of new information today, and not everyone's going to remember everything they saw in every presentation. But if there's one thing I want you to take away from my talk, it is this: if you care about height of burst, then you care about radar. Um, it's pretty much as simple as that. So if you're talking about some kind of standoff, um, let's see, I've moved that thing out of my way here. If you care about some kind of nuclear standoff event where you are not coupling energy directly into the asteroid itself with some kind of ground penetrator, but you're trying to get a little bit of height of burst to kind of, effectively radiate as much solid angle as possible. And if you need to be, just to throw a number out there, 50 meters, not 30 meters and not 100 meters away from the surface, how do you know that you're actually 50 meters away? In terms of technological maturity and ease of implementation, radar is pretty much the best game in town for that particular scenario. So, yeah, essentially radar is, what tells you how far away you are from the thing that you're trying to blow up. So I call this slide Radar Basics for Smart People Who Don't Think About Radar Very Much. So you probably, maybe some of you have seen the radar range equation previously in kind of graduate level RF engineering. But basically, the ability to detect stuff is determined by both the received power, so the signal, and also system noise. And the more power you have and the less noise you have, the greater your signal to noise ratio, or SNR. That's the thing you want to maximize, so that your radar, which is detecting kind of low level, kind of zero mean voltage all the time, is able to say, "Oh, I have seen something. That's good." Here, the radar range equation, your received power, is determined by a couple of things that are under your control and a couple of things that aren't under your control. So you can determine the transmit power of your system. You could determine the wavelength, lambda, of your system. You could determine the gain of your antenna, and that's kind of it. There's some things that maybe aren't under your control. You could debate whether or not the range are between you and the thing you're trying to find, whether or not that's strictly under your control. But a thing that is not under your control is going to be the radar cross section, sigma here, which is in general a function of the incident angle of your radiation. Yeah, so it's a combination of things that you, the system designer, can set, and things that nature sets. So the way that threshold-based detection typically works, this is true for kind of radar and planetary defense. It's also true for other civilian and military applications of radar. Is that when you begin sending out pulses, you're in a transmit mode where you're sending electromagnetic radiation into space, but also the chassis, whatever it is that's doing the radiating itself, is kind of lit up like a Christmas tree, and you don't want to be receiving at the same time that you're transmitting, because then you'll be swamped by your own transmit power and you'll have a false alarm. So you'll spend and these numbers vary, about a third of the time kind of transmitting a pulse, a third of the time doing nothing at all, waiting for what we call ring down, for radiated electromagnetic energy to begin to die down, and then another third of the time listening for the reflected pulse. And the radar detects a success when it has integrated an amount of power that is greater than or equal to your threshold. That's, again, it's a thing as a system designer that you have liberty to set. The height above the target at which this happens, we call the fusing height. And yes, it is fusing with a Z. Don't ask me why. I didn't come up with that nomenclature. That goes back to the 1940s. So the actual height of burst need not be exactly as high as the fusing height, but it is bounded from above by that fusing height. So basically, as you're kind of making your approach, you fuse here, and you can burst exactly there, or there, or there, or there, and so on. But this is kind of how we go about setting up the problem. The radar cross section, this is a thing that again, is angle dependent. So for instance, if you are in the military, you're very interested in the radar cross sections of, say, particular warplanes that either friendly forces or adversary forces might have. So being able to calculate that radar cross section is a matter of vital national importance. For asteroids, it's not closely held. Anybody can go and measure these, provided you have a gigantic radio telescope like Arecibo or Goldstone at your disposal. But in terms of kind of terrain scattering, this is a thing that we use as a model here. when you're looking at a patch of terrain, not a particular boulder, but say a field of boulders, they begin to add up. What does the coherent radiation look like when you're scattering off of that boulder field, or a forest, or a frozen lake, or any kind of terrain? Usually, it tends to follow this formula where you have some kind of normal incidence where theta is equal to 0, and that tends to be the peak. And there's an exponential decay of your measured radar cross section, and therefore you receive power as that angle moves closer and closer to basically being grazing incidence, and you get basically no signal at all at that point. So the steepness of that fall off depends on terrain. It also depends on your wavelength. So for instance, if you're trying to measure the terrain scattering patterns of a coniferous pine forest, if you're working at, say, L band and you're at 1 gigahertz, you don't see the leaves, you don't see the pine needles. That radiation will go directly through this pine forest, treat it as basically a dielectric layer, and it'll reflect off the forest floor and then back up. Whereas if you're at a higher frequency, if you're at KU band, where you're talking maybe 15 gigahertz or so, at that frequency, now you do pick up on the pine needles, and so you detect the canopy of the forest rather than the forest floor. So picking your wavelength, it matters in terms of what it is that you're detecting. So I'm going to start off right now in saying that I'm going to make a model assumption that asteroid surfaces can be treated like bare desert here on Earth. I know that asteroids tend to be wildly different from each other, but you got to start somewhere, right? So I know that there are particular asteroids where I think Paul Chodas and friends at JPL do some great work with asteroid surface modeling. I know I talked with Marina Brzovic, and she's been very helpful in helping me think about this issue as well. But yeah, so you have to make an assumption to say, well, it reflects like this, and then we'll see where we go from there. A lot of people ask me, can I do this with radar? Can I do that with radar? The answer to almost any question when it comes to remote sensing of like, can I do X, Y, or Z? The answer is almost always yes, but it depends. If you know the mission you're trying to accomplish before liftoff, then you can design a custom radar that will detect exactly the thing you're trying to detect with enough advanced time to do something about it. The problem comes when you're trying to do too many things at the same time with the same radar system. You think about a spork. It's not very good as a fork and not very good as a spoon, but it can kind of sort of do both. So you want to try to avoid those trade-offs if you can help it. And so let's get into the meat of what I'm actually doing here. So in the radar group at Sandia, we do a lot of validation of flight tests to make sure that a reentry body detects ground when it's supposed to. So on this diagram on the left, what we see is HU, that's the upper end of the ranging interval. So just based on the kind of the digital signal processing, when the radar is transmitting versus when it's listening for the reflected signal, HU, that's the upper end of the ranging interval. That's the soonest you can possibly hear any received signal. As you go down and down and down further into the ranging gate, that kind of overlap, if you imagine sort of like a boxcar wave where you have 0 emitted signal, and then your waveform is sort of like a fixed frequency for a finite duration of time, a pulse width. So that's in time domain. In frequency domain, that looks like a sync function. So the further you penetrate into your ranging interval, then the greater the overlap of energy between reflected wave versus your receive width is going to look like. And so there's this kind of ideal, or this average time that we call H bar, and that's going to depend on the statistics of the situation, but that's the average height above ground at which you fuse. And so there's going to be some distribution there, which is Rayleigh-like, but it is not a Rayleigh probability density function. If you don't know what a Rayleigh function is, then don't worry about it. It won't come up again. So this model is great. This code that is called the probability of failure due to insufficient signal, or PFS. We use this at Sandia all the time. There is a problem, however, which is that we are going over a flat Earth target. Now, approximating the Earth as flat is great for a lot of missions. If the Earth has a radius of approximately 6,000 kilometers and change, if you are tens of kilometers or less above the surface, then yeah, that's a decent approximation. You're not going to pay a huge penalty for ignoring horizon effects. However, if we're talking about blowing up an asteroid that is maybe a couple hundred meters across, and if our height of burst is maybe 50 meters, that begins to be a pretty bad approximation. Part of the reason why is that as the sort of horizon of the asteroid bends away from you, that exponential die-off of the effective radar cross-section versus incident angle, that really starts to eat away at your receive power. And you don't want to be in a position where you are predicting mission success when that won't actually happen. So then what you get instead of a blinding white flash and an asteroid blown to smithereens is a very expensive kinetic impactor. What I've done is I've kind of taken like this core code and reconfigured it so that it can look at arbitrary 3D objects. So if folks at CNEOS, if you can give me a point cloud of an asteroid that you want me to look at, I can remesh that with locally flat triangular facets, which themselves are electrically large. So the idea is that as you're looking at the bottom right, this is a mesh that I made of Itokawa. If the individual facets themselves are electrically large enough so that the basic axioms of radar terrain scattering theory can begin to play, then I can use all of the tools I already have to be able to say, all right, if we're coming at with this initial position where we start pulsing, and this is our initial velocity, not defined with respect to ground and some angle gamma declination with respect to horizontal, but just a Cartesian coordinate system where, arbitrary position, arbitrary velocity, I can predict success or failure of that mission given a particular radar. So there's a couple of model assumptions that are important. I'm looking at an isotropic antenna pattern for now. Part of the reason why I get away with that is that instead of being very, very far away from something where I know that I have this 1/4 die off of my receive power with respect to object separation, if we're going to be pretty close to an asteroid, I can afford lower power and I can afford less gain in a particular direction, and I can hedge my bets a little bit where if I have a very narrowly peaked beam width, where it's like maybe the full width half max is something like 3 degrees, just to throw a number out there. If my GNC is just a little bit off, then that main lobe maximum could instead be a null, and I don't sense the asteroid at all. Because we're so close to the object when we start pulsing, on the order of like kind of minutes away or, hundreds of kilometers, depending on your kind of local power consumption, you can get away with having less gain in any particular direction, but having it be isotropic so that you get signal from anywhere. So I think I already mentioned the thing about the triangular facets. And so I look at each facet, I model it as a point scatterer with an amplitude, depending on the angle between the normal vector at that facet with respect to the kind of incoming EM radiation. So all facets that are within the beam footprint that are effectively painted by the beam, I count those as scatterers that coherently sum for the total. All right, so here I'm looking at asteroid 2024 YR4. If you've been following the news, you were probably very excited about this asteroid a year and a half ago, and you're probably extremely bored with it right now because we now know that it is basically never going to be an impact risk to Earth. But it is interesting to look at because it is at least an example of in real time, like, hey, how do we exercise this model to determine whether or not this is a successful mission? So we don't have great data yet, or if we do, then Davide has not shared it with me about what exactly this asteroid looks like. But we're going to kind of basically look at it as an M&M for now because it's consistent with the light curve data, and I'm giving it dimensions of 87 by 87 by 29 meters. So, and I'm going to do a couple of runs, one kind of basically right at the North Pole of the asteroid, if you will, one kind of at the equator and one kind of sort of halfway in the middle, just to see how do local surface effects change our ability to correctly detect the asteroid on a nuclear mitigation mission. The idea being that you don't really get to control the local orientation of the asteroid with respect to your space module. Like you just kind of have to you have to look at a bunch of different cases and hope that there's no one case for which you are completely blind to that asteroid, because that would be bad. All right, so for the first run, I place the asteroid like so 128.5 meters above. I picked that number because it's related to some of my timing parameters. If I change the radar itself, I get different timing parameters. I get a different initial placement. Yeah, and I have the velocity direction going directly in the negative z direction, so I'm kind of going on an intercept basis with respect to the asteroid North Pole. And I try a couple of different magnitudes just to see how does it work. And from 2, 5, 10, 15, even 20 kilometers per second. So these are pretty high closing velocities. I am able to successfully detect the asteroid. And the PFS code I use, there's a floor function and it says, okay, the probability of failure is never less than 10 to the minus 5. That's just kind of a coding choice. It could be a different number. But the reason why is that before there is that kind of rounding up, you'll see values like 10 to the minus 308, like, sub machine precision values. And it's not really worth debating, oh, is 10 to the minus 90 a better mission than 10 to the minus 60? Like, no, we're not going to talk about that. We're just saying 10 to the minus 5. But then as we kind of clock up the initial speed, that the probability of failure very sharply jumps to less than 1% to 80%. This is essentially because this is a pulse Doppler filter. There's an onboard Doppler filter that basically says, okay, I'm going to look for things that have a Doppler shift of so many hertz. So the Doppler frequency or the relative Doppler shift is proportional to the center frequency times the beta, like velocity divided by the speed of light. And if I'm going too fast, I have too high of a Doppler frequency, and my digital signal processing on board is not going to see that. So it'll basically be a ghost. So we would only ever design a particular Doppler filter to go on board with this radar once our NASA friends tell us, hey, this is going to be like the maximum closing velocity of this mission. We're never going to ask you to go for more than 20 kilometers per second. So the value of doing the simulation is saying, yes, we actually can sense this asteroid and we can detonate at a given height, whatever my colleagues at Los Alamos and Livermore tell us is the optimal height. And I can tell you when this mission is going to fail. And if my NASA colleagues say, actually, we really would like to have the flexibility to go at 25 kilometers per second, then I say, great, thanks for letting me know before we launched. I will make you a new radar, and then we'll do it that way. So now as we go to a different orientation, so we're looking at the M&M, we're kind of looking at the broad side of the M&M. Now we're looking at the narrow side of the M&M. So once you get off the equator, the terrain is sloping away from you kind of more quickly with respect to angle than it was previously. And as you can see here, we're kind of just going dead on into the equator of it. And the mission now fails at 20 kilometers per second. So if I go back up just briefly, we saw it worked at 20, it didn't work at 25 kilometers per second, but now it fails at 20 kilometers per second. So this is a general feature of these types of simulations where a given velocity profile will correctly fuse for some trajectories, but not for others. And so if we really, really needed the flexibility to go at 20 kilometers per second, so this would be a problem. The radar that I use in my simulation would need to be changed, and we hopefully would do that with enough time to cut metal and make a new device before liftoff. Lastly, this is kind of like an interim case of like, okay, what if we're kind of going at the sort of intersecting at 45 degrees latitude, but it's an ellipsoid, so 45 degrees latitude is kind of a weird thing to think about. And we get a similar case where it doesn't fuse at 20 kilometers per second, but it's just fine at 15 kilometers per second. So, and again, this is a general case where as you change your trajectory, you should expect certain missions that have succeeded for some to fail for others, or vice versa. Okay, and my conclusion is that so in this particular case, with this digital signal processing, with this radar terrain and this assumption about terrain backscattering, that the radar successfully fused for all approach speeds up to and including 15 kilometers per second. So if our friends at NASA say that we will never close with that radar at a speed faster than that, then that's great. We're able to detect it and blow it to kingdom come, no problem. The better the shape model, the more confident we can be in final results. And for the runs that failed, if it turns out that we really, really want to be able to do that in real life, then that's no problem. That's why we do the simulations. It tells us, what to do with our hardware next. So this is kind of the basic, wrapping the bow into my talk, is that I can do a run like this for any scatterer at any desired closing speed and any timing configuration. So if we find a new asteroid tomorrow, or like a don't look up type comet event, if I can get a good shapefile, then I can start running these simulations and have results in a couple of days. This is very fast to get results. Once I kind of did the hard work of reformatting the code, and this is another arrow in our quiver of how we can best defend ourselves and mitigate asteroid threats going forward. And that's my talk, and I'll take questions if there are any. Thank you very much.
Thank you, Russell. Very useful method for characterizing asteroids. Are there any questions in the room or online for Dr. Tebik?
I have a question. My name's Adrian. Could you combine something like a SAR Doppler radar to approximate the object's shape, as it were, and perhaps compensate for that, and give you various fusing distances for the calculated dimensions of the object?
So the short answer is yes. The slightly longer answer is it depends on your mission profile. If you are doing a high-speed intersect, the processing time that is required to get a couple of good coherent processing intervals out of a SAR Doppler image, you might not have enough dwell time over target to be able to get a good image beforehand. On the other hand, if you're talking about kind of more of an orbital rendezvous, where you're basically kind of traveling in whatever orbit is determined by the asteroid's gravity, then you have all the time in the world. Then you can get a good SAR image, and you can kind of correlate that against particular asteroid models and say, that's the spot that I want to detonate over. So for orbital rendezvous, yes. For a fast intersect approach, where it's either like you shoot your shot and either you save the day or you go the way of the dinosaurs, I don't think that SAR would be good in that use case. It's not enough processing time.
Got it. Thanks.
Thank you. Any other questions?
Can I ask, I think I really have two questions. One, I've been thinking, just toying with the idea of how one might land on this asteroid when it approaches Earth again in 2028, and then before it comes close to the moon in 2032. And so it's interesting to me that you showed two different perspectives, and I've been wondering if one could land on the pole, in the summer season, so you'd have sunlight continuously. So I'm wondering to what extent the radar systems you're discussing would be good for landing. And the other question has to do with how would LiDAR compare with radar for this type of system?
So the first question, this is a little bit outside my wheelhouse because I'm an RF guy and not a GNC guy as much, but I think so. I don't see any reason why you couldn't land on the North Pole. It might be a slightly different configuration. I think the answer to the second part of your question is how what radar could do. You could basically just use radar as a real-time altimeter. It just tells you how quickly does the leading edge come. And of course, like the radar, it knows the frequency at which it emitted the EM, and so it can subtract that. It can kind of convolve the outgoing wave with the ingoing waves, and so that gets you down to baseband, which makes your processing easier. So if you know about the Nyquist Shannon sampling theorem, like that's where that comes in. So yeah, it would be a different configuration. There would be different RF circuitry on like the interior of the space module that was doing that. But that's a thing you could do. You would basically use radar as as an altimeter to tell you how far away you are from the scatterer. The other thing is, why RF radar versus LiDAR? It's a good question. It's one that is very frequently debated. The reason why, especially for nuclear explosive device fusing, the reason why I prefer radar is because it's much less sensitive to the details of the surface. Whereas, like optical light, it can be scattered in all sorts of ways. The return pattern you get back is a strong function of the local optical properties. Radar, it's a much coarser grained approach, and it just thinks of the object as basically kind of like a dielectric boundary. And so, yeah, you will get like a different bounce back signal in little ways, but as long as the overall axioms of radar terrain scattering apply, then you kind of weed out a lot of that stuff, and you're definitely going to get back some wave at some time, and it allows you to say how far am I away from anything, which is what you care about for like a nuclear standoff, versus like what are the fine details of the surface. If you have an asteroid, like say a rubble pile, and this kind of goes beyond my particular expertise, but like say folks at the physics labs or APL or whatever, if they believe that it doesn't really matter, like do you detonate over a boulder or over a valley? Like if the answer is who cares, then radar is good because it ignores a lot of stuff that's not really massively important for your mission.
Thank you.
Yep.
Yeah. I think it's time to move to the next talk. I do have a comment, a question. Understanding is that the difference between ground-based and space-based radar systems is the limitations of power and weight for the specialist. Do you have any insights into the future of those?
Are you talking about space-based in particular, or the trade-offs, or what? Okay, yeah. So you're definitely right that power is a limiting factor. The way that this would work in practice is you would have some kind of like a more passive optical sensor, or because like you've done your Newtonian orbital kinematics, you have an idea of when you're going to be kind of close to the asteroid. And you would then turn on your power because every extra kilogram of battery power that you want to throw up into space, that's really going to cost you in terms of propellant. So there are trade-offs. One of the things you could do is if you were really confident that you knew the asteroid surface properties really well, and of course you always want to hedge your confidence a little bit because if it's like Cleveland getting leveled by an asteroid, then it's like you want to be sure. But you could reduce your power if you knew that based on simulations you didn't have to be like massively far away, and you do these kinds of simulations to say how little power can I get away with and still accurately fuse over the target. So that's one of the things you could do, where it's kind of like at a certain point conservation of energy just sort of wins, and you can't really cheat that. And so you have to launch all the power that you need to bring. So what I would do is say, like, let's fine tune how much power we really think we need, and how much we can trim to get away with, so we can kind of save on the launch budget. So that's my approach. I would also say, and like all the JPL folks know this very well, but I would love to get Arecibo back online. That would be great, because the more that we can kind of work in tandem with ground-based radar, where power is not a problem, the better. We would get a lot of benefit out of that, and better ground-based radar observations mean that we have less uncertainty, and that the space-based radar, we can really trim that mission package to only set up exactly what we need. So that's how I'd answer your question.
Thank you so much. Interesting talk. Hopefully you will come visit us again in the future to tell us about additional developments with our approach. And now we are going to, thank you so much. We are going to now move forward to the presentation by Sasha Cohen and Brent Bailey, investigating hypothetical mitigation of asteroid 2024 YR4 via intentional robust disruption. So thank you. You can say a few words about yourselves. You are probably associated with Professor Lubin, so you can tell about what you do and how you got involved with that. Take it away.
Sure. All right. Can everybody hear me okay?
We hear you fine, and we love the animation on your front page.
Okay, perfect. Okay, so hi everyone, good afternoon. My name is Bryn Bailey, and my colleague Sasha Cohen and I are planetary defense researchers in the UC Santa Barbara Physics Department. Again, under Dr. Philip Lubin, as Nuhu mentioned. Thanks so much for giving us the opportunity to talk to you some more today about Pulverize It or PI, which is our multimodal planetary defense study currently in phase 2 of NASA's Innovative Advanced Concepts program. I know you've already gotten an overview this morning from Dr. Lubin, so now the two of us will take turns talking about various aspects of the program, starting broadly with a discussion of the methodology, and then focusing our attention on simulations of hypothetical mitigation for Asteroid 2024 YR4. And also, I know we're a bit behind schedule, and this is scheduled as a lunch hour. Thank you for your time. We're going to try to run a bit short and leave some time at the end for everyone to relax a bit and take a brief break before the next talk. Next. So, of course, space debris entering Earth's atmosphere is not uncommon and usually consists of small bodies or fragments of bodies that are generally not considered threats. But on occasion, we may be visited by larger objects that do have the capacity to enact damage. In practice, we have, of course, seen that kinetic impact is a tried and true method, as the DART mission showed us in a tremendous breakthrough for planetary defense. Though presently, deflection is the only method which has been reliably put into practice. And as we've kind of heard today throughout a few of the different talks, in a real mitigation scenario, a deflection mission hinges largely on time. An object's discovery must give us enough time to design and launch a mission to deflect it relatively far ahead of its impact, which is on the scale of years, if not decades. And while most NEOs are small and non-threatening, there's always some possibility that something bigger could come by or that we don't see an object far enough ahead of time. For some perspective, we can look to the Chelyabinsk airburst of 2013 and the Tunguska airburst of 1908, both of which have been brought up a few times today, which serve as examples for our need for both detection and mitigation efforts. So just a brief overview, Chelyabinsk was 18 meters in diameter, released an estimated impact energy equivalent of around 500 kilotons TNT. This caused damage out to 120 kilometers from the supersonic path, shattered glass in over 3,600 buildings, and resulted in over 1,000 injuries. And for context, objects at least the size of the Chelyabinsk asteroid are expected to impact Earth about every 50 to 100 years. And larger than this was Tunguska, with an estimated impact energy between 3 to 15 megatons or so. The resultant shockwave flattened a large portion of the surrounding forest, potentially on the scale of millions of trees, and produced an area of damage spanning about 2,000 square kilometers. And objects similar to Tunguska are expected to impact Earth every 300 to 1,800 years or so. I know Adrian was discussing this earlier as well. Next, please. As another more recent example, and the main subject of this talk, and I know you just heard a little bit about it, we have Asteroid 2024 YR4. This being a planetary defense conference, I don't have to explain much. It was our job to be glued to this news in late 2024, early 2025. And again, I know we've heard a bit about it today, especially from Russell's great talk. But for those maybe playing along at home, 2024 YR4 was discovered on December 27th, 2024, 2 days after its closest approach to Earth, in which it came within about 2 lunar distances, which is very close, but not the closest it's ever going to get. That title goes to its approach in 2032 on December 22nd. And the all-important question, is it going to hit us? Next. No, but we once thought it might. Next, please. In January 2025, oh, my little image isn't popping up, but that's okay. In January 2025, 2024 YR4 reached a record Torino scale impact rating of 3, meaning at the time it was estimated that there was a 1% chance that the object would hit us. The probability of Earth impact continued to rise, peaking at about 3% in February 2025, before eventually being reduced to 0 upon more and better observations. And as was mentioned earlier, then we thought it might impact the moon and stir up some different trouble, but now we know that isn't going to happen either. Next. Oh, never mind. It's already there. Okay. As for its physical characteristics, the object's diameter is estimated at about 60 meters, which, for perspective, is roughly in the ballpark of the Tunguska impactor's estimated diameter. If instead an Earth impact were to occur, which it won't, the collision could yield an impact energy of roughly 7 megatons, approximately 14 times the energy of the Chelyabinsk airburst and comparable to Tunguska. In a scenario where the impact probability doesn't go down, where we would only have a few years of warning before disaster strikes, or in a situation with even less warning time, what could we do about it? What are our options? Do we have a system set up to handle not only distant, long-standing threats, but also threats that may require more immediate action? So, current planetary defense strategies are not well equipped to combat a wide range of threat scenarios, particularly in the short warning regime where there's little to no time before impact. To achieve an extensive planetary defense system, it is imperative that we are prepared for a wide variety of threat scenarios that considers a large range of threat sizes and warning times to prepare us for anything. So that begs the question. Next. Can we append existing planetary defense strategies with a new approach that can provide reasonable mitigation of a wide variety of threats, including those in this short warning regime? And with that, I'll pass it over to Sasha to discuss the impact logistics.
Thank you, Bryn. Just want to make sure everyone can hear me. Is that okay?
Yep, hear you just
Very
good.
So along with Bryn, I'm a researcher in Dr. Philip Lubin's group at UC Santa Barbara, and I'll talk about how Pulverize It, or as we affectionately call it, PI, works. So PI works by coupling the kinetic energy of a hypervelocity penetrator into an asteroid target via shockwaves and material vaporization. The shockwaves generated by the impact damage material and crush porosity, which reduces the overall cohesion of the object. Over the duration of a few seconds, the asteroid is disrupted into a cloud of fragments which disperses at a speed much greater than the gravitational escape speed of the parent object. So there's no possibility that the fragments gravitationally recombine afterwards. In most cases, this is where the story ends. The fragment cloud disperses until it has a diameter much larger than the Earth, which ensures that only a tiny fraction of the fragments, if any, actually intercept the Earth. However, PI can also operate in a terminal mitigation mode. In this mode of operation, the fragments are limited in size to less than 10 meters, such that they airburst in the Earth's atmosphere at high altitude, dispersing the total impact energy. You'll hear more about this when I pass it back to Bryn. In order to simulate hypervelocity impacts, we make use of the hydrocode ALE3D developed by Lawrence Livermore National Lab, and we run this code using NASA's HECC, or the High-End Computing Capability. The NASA Ames Supercomputing Facility offers multiple independent clusters with varying system architectures. Legacy clusters include Electra, constructed in 2016, and Aitken, a petascale supercomputer constructed in 2019. Most recently, in December of 2025, NASA decommissioned its legacy Pleiades supercomputer to make way for its newest petascale supercomputer called Athena, which is now online. As an example of a typical use case, a typical 3D hypervelocity impact simulation of the type you will see shortly runs on 16 Aitken nodes, each of which is comprised of two 64-core processors for a total of 128 CPU cores per node. This amounts to a total of 2,048 CPU cores for an average run. Next, I'll provide an outline of our ALE3D simulation setup for hypervelocity impact simulations. Our baseline penetrator is a 10-to-1 aspect ratio tungsten cylinder with 750 megapascal yield strength. So further on in the talk, anytime I refer to a penetrator, this is the type I'm referring to. We use this penetrator as a baseline for comparison across simulations, but other penetrator geometries are being investigated, as will be shown shortly. We use a two-phase Livermore tabular equation of state for granite as our baseline asteroid material, though future work will expand this into more realistic materials like olivine. The asteroid material has a grain density of 2.6 grams per cubic centimeter and a porosity ranging between 40 and 50%. For the disruption simulation shown in this talk, we model our asteroids as weakly bound rubble piles, as shown on the left. Asteroid models are constructed by randomly packing granular boulders within a weak binder material. The binder material has an average strength of roughly 25 pascals, which is a value we will motivate on the next slide. Not only does the material yield strength vary from boulder to boulder, but we also vary the yield strength within each individual boulder using the Weibull distributions shown on the right. This allows for realistic simulation of fragment dynamics in geological materials like those simulated here. While we conservatively model individual boulders as having strengths as high as 250 to 500 megapascals, as shown by the Weibull distributions on the right, the cohesive strength provided by the binder material between the boulders is set to be much weaker. This is informed by measurements of asteroid rotation rates, which suggest that most asteroids above 100 meters in diameter are loosely bound rubble piles. Recent missions to asteroids like Bennu by the OSIRIS-REx mission and the asteroid Ryugu by the Hayabasa mission also reveal loosely bound rubble pile-like surfaces. While this doesn't inform us about the interior structure of asteroids, we can make generalizations based on observations of asteroid rotation rates. In this simulation, we show the robust disruption of a 50-meter diameter rubble pile asteroid model using a single 100 kilogram tungsten penetrator of the type I described before, impacting at 20 kilometers per second in the asteroid reference frame. A brief analysis of the fragment statistics after impact shows that the average velocity of the fragments, shown by the red histogram on the left, is almost 3 orders of magnitude larger than the gravitational escape speed of the parent asteroid, which is shown by the vertical dashed red line, which is roughly 2.1 centimeters per second for this 50-meter object. We also see that the specific impact energy, which is defined as the penetrator kinetic energy per unit mass of the target asteroid, is over 200 joules per kilogram. Previous work by Martin Jutzi and collaborators in 2023 has suggested that the limit for catastrophic disruption for sphere-on-sphere impacts is roughly 100 joules per kilogram. While not a direct comparison for penetrator impacts, we still see that exceeding this threshold does indeed result in robust disruption. These results suggest that a single 100 kilogram, 20 kilometer per second penetrator, or an equivalent specific impact energy over 200 joules per kilogram delivered below the surface, is sufficient to mitigate a 50-meter asteroid, with the use of additional penetrators showing similar results for larger objects. This means that payload capacities of pre-existing launch vehicles, such as a SpaceX Falcon 9 or similar, can be used to provide a single launcher solution for objects in the 20 to 150 meter diameter range. In this simulation, we show the robust disruption of a similar 50-meter diameter rubble pile asteroid model, but with 5 separate 100 kilogram penetrators arranged in a plus shape, so one in the center, and then one to the north, one to the south, one to the west, and one to the east. The histograms at the left indicate the distributions of fragment masses in kilograms, which is shown in orange, the diameters in meters, shown in blue, and the speed in meters, shown in green, meters per second, shown in green. The red histogram, corresponding to the right-hand axis, shows the original boulder size distribution generated for the target. When compared to the blue histogram of fragment sizes 10 seconds after impact, it can be seen how the initial boulders have been largely reduced into fragments with an average diameter of roughly 1 meter. As in the previous case, the green histogram of fragment speeds shows how the average fragment speed is over 2 orders of magnitude higher than the gravitational escape speed of 3.4 centimeters per second in this case. The inset plots at the bottom right show the material damage parameter D, which scales between 0, representing undamaged material, and 1, representing fully damaged material, which no longer retains its tensile strength. As can be seen here, near complete volumetric material failure is achieved in this case. As a comparison to the previous simulation, this one condenses the 500 kilogram mass into a single penetrator. The results show that the single penetrator case succeeds in transferring approximately 2 times as much of the initial penetrator kinetic energy into the target as the 5 separate penetrator case shown in the previous slide. This is likely due to the increased penetration depth of the single penetrator, which allows for better kinetic energy coupling. As before, when comparing the blue histogram of the fragment sizes 10 seconds after, when compared to the blue histogram of fragment sizes 10 seconds after impact, it can be seen how the initial boulders have been largely reduced into fragments with an average diameter of roughly 1 meter. This indicates that rather than merely disassembling the pre-existing boulders from the rubble pile, we are actually first pulverizing them and then dispersing the fragments which remain. It should be noted that in reality there would be a large skew to the fragment size distribution towards much smaller fragment sizes, but these are not resolved in our simulation since we must use a finite mesh resolution. In addition to robust disruption, Pi can operate in alternative modes depending on what is required to mitigate a particular threat. The first is an induced rocket mode, wherein material rapidly ejected from the entrance cavity created by a hypervelocity penetrator can induce a significant amount of transient thrust. This is common to all hypervelocity impacts with a high aspect ratio penetrator, and the induced thrust can be compared to a heavy lift launch vehicle for a short period of time. The second alternative mode is an enhanced deflection mode, where an asteroid is fragmented partially or asymmetrically, which can induce enhanced momentum transfer via very large beta, which is a momentum enhancement factor due to significant ejecta. As an example of the enhanced deflection mode, we show here a 500-meter rubble pile asteroid model. In this case, a 10 metric ton penetrator impacting at 20 kilometers per second can induce a beta or momentum enhancement factor as high as 80. This is evidenced by the significant amount of high-speed ejecta shown in the density and speed plots here. So the speed in centimeters per microsecond is shown on the right, and the density in grams per cubic centimeter is shown there on the left. So while this does not produce robust disruption, the significant amount of ejecta produces a huge momentum enhancement factor. An additional example of the enhanced deflection mode of operation is shown here for a 1 kilometer diameter rubble pile asteroid model. In this case, a 100 metric ton penetrator impacting at 20 kilometers per second can induce a momentum enhancement factor as high as 40, as illustrated in this plot of the fragment speeds. In order to better understand the internal dynamics of a penetrator during impact, we ran a series of high-resolution 2D axisymmetric simulations with 500 kilogram penetrators. The target in this case is a long slab of asteroid material with a 50 to 100 megapascal Weibull yield strength distribution and 40% porosity. Plots at right show density on the top and pressure on the bottom for a 10 kilometer per second impact. Note how the ratio between the penetration depth and the length of the original penetrator, often referred to as P over L, is slightly above 3. In this series of plots, we show how the impact pressure is distributed in the right column and how the plastic strain is distributed within the penetrator in the left column. The maximum of the penetrator color of the pressure color scale on the right column is set to 750 megapascals to illustrate regions which exceed the penetrator yield strength. Regions in yellow meet or greatly exceed this value, with the maximum pressure observed at any given time ranging between 60 and 65 gigapascals at the front of the penetrator. These plots similarly show density on the top and pressure on the bottom for a 20 kilometer per second impact. Note how the ratio between the penetration depth and length of the original penetrator, or P over L, is also slightly above 3 in this case, and not significantly improved over the 10 kilometer per second case. This is expected above the so-called hydrodynamic limit, where material strength becomes somewhat negligible compared to the inertia, and materials instead behave more like fluids. Also note the frictional interaction with adjacent vaporized material, which is distinct from the 10 kilometer per second case shown previously. To illustrate this more clearly, we can show how the pressure and plastic strain is distributed as before. In this case, we can see how the back of the penetrator is exposed to significant plastic strain, as seen in the left column, prior to achieving maximum penetration depth. This is caused by adjacent vaporized material being forced into contact with the side of the penetrator, which ultimately causes complete material failure in the back earlier than maximum penetration and depth is achieved. While this does not make a significant difference for a passive penetrator, it does play a significant role in designing mitigation scenarios where payloads are required to be delivered below the surface, as will be seen shortly. In order to better understand the internal structure of asteroid targets, or in order to enhance a particular mitigation scenario with a nuclear explosive device, or NED, a set of instruments could be included as part of the penetrator payload. However, survivability of the instrument package until far below the surface becomes critical to ensure. These simulations show a 500 kilogram penetrator with a suspended mass acting as an instrument package analog, impacting an asteroid simulant target at 5 on the left and 10 kilometers per second on the right. These results suggest a sort of zone of survivability between 5 and 10 kilometers per second impact speed, where below 5 kilometers per second, the payload is subjected to impact forces early since the impact speed is less than the phonon speed or sound speed in tungsten, and where above 10 kilometers per second, the frictional interaction with adjacent vaporized material also subjects the payload to impact forces early, as we just saw. Within this range of 5 to 10 kilometer per second closing speed, it is conceivable that a hypervelocity penetrator could deliver an NED below the surface of an asteroid. We approximate subsurface NED detonations using a method similar to that described in Schroeder, 1974, more commonly referred to as an energy pill. Radiation transport is not explicitly simulated. Rather, the simulation is initiated by injecting energy into a sphere of subsurface material. The radius of this sphere in meters is determined by this approximation, where W is the yield of the device in kilotons of TNT equivalent. This method indirectly simulates the absorption of the radiative output of the device by pre-vaporizing a volume of subsurface material. This is an adequate approximation since the mean free path of high-energy radiation is relatively short, typically less than a few meters within rocky materials. The energy injection heats and vaporizes the material within the prescribed sphere, generating a shockwave of similar magnitude as that produced by an NED. By removing the need to directly simulate radiation transport, this simplifies the methodology and allows coupling to hypervelocity impact models for simulations of subsurface NED delivery to a target. The simulation on the left is actually a longer timescale continuation of the simulation I just showed on the previous slide, and it shows oops, let me go back here. This simulation on the left shows a close-up of the energy pill simulation, specifically a 1 kiloton yield delivered to a depth of roughly 6 meters below the surface by a 2.5 metric ton penetrator at 5 kilometers per second. And then, as I was saying, the simulation here on the left is a continuation of that one that I just showed. So these simulations show a comparison between a 1 kiloton yield NED delivered 6 meters below the surface as before, which results in catastrophic disruption, and the same yield device detonated at the surface. The results show a significant reduction in coupled energy from the NED in the surface burst case, showcasing how even a modest depth of burst can result in greatly improved energy coupling. Future work will present simulation results for a variety of other impact scenarios, including close sequential penetrators for hole drilling and improved depth of penetration. And sequential penetrators with significant spacing are also being explored for purposes of delivering explosive devices below the surface. And in the meantime, while I was waiting for the talk, I noted that there was a question in the chat. I can't quite remember who asked it about off-axis angled penetrators, and that is an area of active investigation for us. These show 5, 10, and 20 kilometer per second cases with a 10-degree off-axis angle. These results show that this degree of off-axis angle reduces the total penetration depth of order 10 to 15%. And so for a passive penetrator, it's not as significant a reduction in penetration depth as we thought, although obviously if one of these penetrators was to deliver a payload, you would need to have very fine control over the off-axis angle. And then finally, we are also working towards using actual asteroid shape models, such as the one shown here, which is an asteroid shape model of asteroid Itokawa, so we can more accurately simulate a wider variety of asteroid types like contact binaries and see how the acoustical effects propagate throughout the asteroid differently depending on the geometry. So with that, I'll pass it back to my colleague Bryn to talk about ground effects.
Okay, perfect. Thanks, Sasha. Yeah, so now we're going to move away from the impact stage and talk about what happens afterwards. So we've seen now Pi represents this versatile multimodal approach that can be used in a wide variety of scenarios, whether the warning time is on a scale of weeks or years, or for threats like Chelyabinsk or like Apophis, or even larger. In longer warning scenarios, where an impact is months or years away, the fragments can miss Earth entirely, completely removing the threat. And depending on an asteroid's size and speed, a short warning mitigation scenario could be feasible. In these short timescale intercept scenarios, which we refer to as terminal scenarios, the fragment cloud would enter Earth's atmosphere, where it would disperse the energy of the original asteroid through spatially and temporally decorrelated ground effects. Of course, Pi's preferred mode of operation is in the extended intercept regime, where we could intercept an asteroid far ahead of its impact. It's always preferable for any method of planetary defense to be used far ahead of time and as early as possible to keep the aftermath away from Earth. Though our findings do suggest that Pi is uniquely capable of operating in a terminal mode in certain scenarios where the factors are favorable. So Pi could feasibly be used in this terminal mode in scenarios either with very short warning or in which an initial mitigation effort fails to eliminate a threat as sort of a backup method or emergency button. So in this terminal mode, during atmospheric entry of the fragments, the pressure exerted by the atmosphere eventually exceeds the fragment's material strength, causing a cascading breakup event. And as pressure and heat increase, the fragment ablates and the material fails, causing the fragment to burst. And collectively, these bursts produce optical flashes and decorrelated shock waves as observed on the ground. These optical and acoustic ground effects spatially and temporally distribute the energy of the original asteroid, which, in reasonable mitigation scenarios that are appropriate for the threat, result in little to no damage. We design our terminal scenarios to keep the ground effects below reasonable thresholds to prevent high-level damage from occurring. For the acoustic effects, we aim to keep all shockwave overpressures below 3 kilopascals, which is the point at which residential windows may begin to break. And for the optical effects, we aim to keep the cumulative optical energy below 200 kilojoules per square meter, above which organic materials can catch fire, like paper or grass. Next. Let me make sure. Oh, make sure the video plays.
There we go.
Okay, awesome. Thank you. So here we simulate the acoustic effects in a very terminal mitigation scenario for an estimate of asteroid 2024 YR4. Both boxes are looking at an asteroid that is 60 meters in diameter with an average density of 2.6 grams per cc and an exoatmospheric velocity of about 17.1 kilometers per second, which is the estimated velocity at atmospheric entry if an impact were to occur during the object's close approach back in 2024. So in the left box, we disrupt the body into 4,000 fragments 1 day before Earth impact, and in the right box, we simulate an equivalent unmitigated asteroid airburst. The upper movie plots display the real-time pressure, and the cumulative distribution functions on the bottom show the frequency of occurrence of various pressure values. And to note that in the fragmented case on the left, the simulation does include constructive interference from overlapping shock waves. In the fragmented scenario, we achieve an average pressure of about 1,200 pascals and a rarely occurring maximum pressure of about 2,200 pascals. So at no point during the simulation do we reach that 3 kilopascal limit. We also pay special attention to the value that occurs at 1% of the cumulative distribution function, which is the value that 1% of locations on the ground within the observation area will experience. So here we see a 1% CDF value of about 1.4 kilopascals, a little less than 50% of our threshold value. Conversely, the unfragmented case on the right has an average pressure of about 22 kilopascals and a maximum of 41. And again, 3 kilopascals being that limit at which windows might begin to break, and 10 kilopascals has the capacity to blow down small wooden structures like residential structures. So let's address the elephant in the room. The mitigation scenario on the left is an extreme worst-case scenario. This is simulating a hypothetical in which we discovered YR4 several days or weeks before its initial close approach in December 2024, assuming operational status could be quickly achieved. But we would never want to do this if we don't have to. I know Phil mentioned this this morning. I just want to make sure that we stress it, that it's always preferable to not to use any planetary defense technique as early as possible, and we do not want or recommend to disrupt an object only 1 day before impact. A preferable scenario is, of course, on the scale of months to years. But with cases like 2024 YR4's late discovery just after its closest approach, it's reasonable to imagine a situation in which we could have very little warning. And we show these extreme results because even with minimal warning, they suggest that PI could be effective in terminal mitigation of smaller objects, and combined with detection efforts, could potentially prevent events like Chelyabinsk or Tunguska in the future. Next. As for the optical effects, here we're looking again at the 60-meter asteroid cases, with the fragmented case on the left and unfragmented on the right. The fragmented case has an average optical energy deposition of about 11 kilojoules per square meter, a 1% value of 26.1 kilojoules per square meter, and a maximum of 26.4. Whereas in the unfragmented case, we calculate an average optical energy of about 2,500 kilojoules per square meter, a 1% value of 11,000, and a maximum around 18,000. So we again see that disruption works to dramatically decrease the optical energy flux to more manageable levels. In unmitigated cases like Chelyabinsk, the optical output caused retinal and skin burns for those who were outdoors and unprotected from the flash. Mitigation via fragmentation could help to decrease similar potential damage, even in extremely conservative worst-case scenarios. Next. On the other end of the spectrum, Simulations also suggest that Pi is capable of mitigating much larger asteroids, given longer intercept times. So here we have a 500-meter diameter asteroid broken into 100,000 fragments with an intercept 60 days before ground impact. Now, since this is a much larger asteroid, it of course would not airburst, it would impact the ground, which would be a much more damaging scenario. And while this intercept is certainly longer than the last that I just showed, again, designing and launching deflection missions take place on the scale of years. This could take place on the scale of months, which again, we don't recommend or foresee happening, but we show that it's possible. In reality, a 500-meter asteroid would generally be observed with much longer warning, especially as our situational awareness is drastically increasing with new and upcoming detection efforts like the Vera Rubin Observatory and upcoming NEO Surveyor mission, as was mentioned earlier. And note also that the scaling here has increased dramatically in comparison to the previous slides. The previous plots, looking at a one-day intercept of the 60-meter object, spanned an area of 300 by 300 kilometers, whereas here the scale is 12,000 by 12,000 kilometers, spanning roughly Earth's diameter. So cover a lot more space. And here, in addition to the real-time pressure in the upper left, we also plot the maximum pressure in the upper right, where each pixel holds on to the highest pressure value it experiences throughout the length of the simulation. At 500 meters, we're at roughly the size of Bennu, slightly larger than Apophis. If an asteroid of this size were to impact Earth, it could pose a yield comparable to Earth's entire nuclear arsenal. We also have the real-time pressure distribution and maximum and minimum pressures to keep an eye on things as they occur. And again, the cumulative distribution function shows that the pressures experienced throughout this scenario are reasonable. We see an average pressure of 440 pascals, a 1% value of 1.5 kilopascals, and a maximum of about 2.9 kilopascals. And this nearly hits our damage threshold. So again, this is a very conservative worst-case scenario for mitigation, but we show that it could be feasible. Next. So now just looking at the optical effects for this 500-meter diameter case, in the upper left, we see the optical power flux. The upper right shows the optical energy flux. And on the bottom here, we have the real-time power flux distribution and maximum and minimum power to, again, just keep an eye on things as they happen. And again, we see from the cumulative distribution function that the energy flux experienced throughout this scenario is reasonable, with an average of about 9.4 kilojoules per square meter, 1% value of 37, and a maximum of about 92 kilojoules per square meter. Next. So to kind of wrap up all that we've been discussing, we've also begun a mission design effort in which we're looking into feasible objects for an actual disruption test. For now, we have narrowed our focus on objects within the 30 to 140 meter diameter class, limiting our current scope to objects which can be reasonably disrupted with a single launcher, using that single launcher solution, which would generally decrease complexity. Our preferred starting vehicle that we tend to use in simulations is a SpaceX Falcon 9, as mentioned by Sasha earlier, but we're open to exploring different launch vehicles. But as was mentioned earlier, we can't exactly get an SLS, on short warning to go send up. So something that is easily reproducible and launchable is definitely preferred. We additionally focus on objects that have a close approach distance within about 0.1 AU within the next 10 years or so. And we narrow our query further to minimize the C3 required at departure and maximize delta V in hopes of impacting the target at high velocity. And recently, due to some questions posed at an interagency meeting, we've been tasked with investigating impacts at lower velocities on the scale of 5 to 10 kilometers per second, as Sasha was showing a bit of earlier. So as we get more results from those simulations and some others down the line, we're also planning on potentially modeling some missions at these lower impact speeds in the event that something on that scale may be more feasible to achieve. We're especially interested in designing a mission to 2024 YR4, as it is of such high interest and a lot of buzz, in the last year and a half or so. We're currently working with our partners on mission design and analysis, including groups from JPL and UC Colorado Springs. And if anyone here is interested in or knowledgeable about mission design, we would love it if you come talk to us. We have a paper in progress detailing hypothetical mitigation scenarios for both Earth impact and lunar impact of 2024 WIRE4. So keep an eye out for that in the near future. And please reach out to us if you are interested in collaborating. Next. So to conclude, PI represents an effective multimodal method for planetary defense that could prove useful in a wide range of threat scenarios, spanning both asteroid size and warning time up to these possible existential threats. It represents the first planetary defense strategy that is capable for use against short warning threats and allows for this sort of logical roadmap toward a robust planetary defense system, creating a single launcher solution with at-the-ready capability. And thank you so much for your time. And we'd be happy to take any questions if you have any.
Thank you, Bryn and Sasha. Super interesting talks in continuation for the talk that Phil gave earlier. I do see a couple of questions online. I don't know if you can answer the first one. It's probably outside of the scope of your research in terms of if the asteroid gets too close to Earth's orbit, what's the possibility of robust disruption causing cascading Kessler effect with satellites? Did you even look into that aspect?
So I'll briefly start and then pass it over to Sasha. We've gotten this question a lot, and it's something that we really want to dedicate time into looking into. I'm sure that Phil may be able to speak to it a bit more, but Sasha, if you want to add anything,
yeah, I
go
would
for
say
it.
we've really only specifically looked at cases where we allow all of the fragments to enter the Earth's atmosphere, or we allow none of them to enter the Earth's atmosphere. It's either quite terminal or quite far away. Obviously, there are cases in between which might be more relevant to your question, but I would say yeah, it's not something we've explicitly looked into yet, though we do intend to.
Well, if it is terminal, what's the possibility of the Kessler effect if it's really terminal last minute?
I wouldn't say I know how to quantitatively answer your question off the top of my head in terms of the likelihood of the Kessler syndrome. It's going to depend on the number of fragments and the size of the particular threat. I would say we'd be open to discussing this more outside of the context of the conference if you want to discuss this in more
So
detail.
unknown at this point. Okay, thank you.
Yeah, unknown at this point. Yeah.
And there is additional question about the critical angle. Do you have any insights in terms of any critical angle of intercept between?
So do you mean the angle of the penetrator like I was showing, the off-axis angle?
Yeah, Russell put a question into the chat.
Oh, let me.
Yeah.
Sorry about that.
Is there a critical angle?
That's a good question. Yeah, it's a good question. So, so one thing regarding porpoising, because we're so far into the hypervelocity regime, these penetrators don't really act like rigid bodies. All of the impact forces and everything, all of the impact forces are focused at the impact site because the acoustics don't have time to propagate back towards back towards the back of the penetrator. So you won't get anything like porpoising, I would expect. I would also expect that, very roughly the amount of area that's exposed by the back of the penetrator is going to go as the cosine of the angle of the off-axis angle. And so I would expect to see a fairly significant drop-off in penetration depth as the off-axis angle increases. And that's something we're actively looking into as well. At the moment, we've only sampled this 10-degree off-axis angle, but hopefully soon we'll be able to fill out that matrix of cases more densely. So.
Okay, so more things to report perhaps next year's conference.
Certainly.
And just before we move on to the question by Jason, I want to remind that we have young professionals and students in the audience, and some of them might be interested in learning and pursuing careers similar to yours. I'm just checking to see if it's okay to contact you, learn from your path, and
Please.
maybe get an advice.
Yeah, absolutely. We would love that and be super happy to.
Fantastic. So if there is any desire by anyone to learn more, collaborate, publish together, or anything like that, please approach Bryn and Sasha. And now I see a hands up by Jason. Jason, go ahead. I cannot hear anything. Jason, you have audio working?
If it doesn't work,
Maybe.
they can feel free to send us an email afterwards, whatever works.
Yeah, and also you can type the question
Yep.
in the
seems
chat.
to be having trouble.
Yeah. Actually, I do
We'll
have
send
a
our
question.
emails in the chat just in case for
Yeah,
follow-up.
Put the question in the chat and they will follow up. I do have a question. It feels that although the method that you're describing is characterized as a kind of last resort in case we couldn't either detect the object early enough or weren't able to mitigate it early enough in deep space, but it feels that this method is as applicable in deep space as it is in near-Earth space. And it could be added to the standard toolbox of methods that are proposed to be done when you have enough time to deflect or disrupt and all of that stuff. So did you do any comparison, or does your method has any advantage over other methods that are being proposed when you have 5 or 10 years ahead?
Yeah, I would say that when the primary objective becomes energy coupling into the target rather than momentum coupling into the target, the amount of launch or the amount of mass required off the launch pad is vastly decreased for the energy coupling case, as we show here. And so that's the primary benefit that we see in this method, other than the fact that it has this multimodal capability, as you're describing, that you can operate both terminally and on much longer timescales.
So in these shorter timescales, and not even talking about strictly terminal, so kind of on these timescales of weeks to a few years, in relation to the launch mass, robust disruption via pi or similar methods can actually be more efficient and easier to get up off the ground than something like deflection that Sasha mentioned. Requires momentum transfer as opposed to energy transfer.
Cool.
So there is certainly that, and I do want to stress as well, as you just mentioned, that using this method as sort of this backup or this last minute scenario, that's really just for the terminal method, the terminal mitigation mode, right? We don't want to have to hit something days or weeks or even months before it hits us. So that sort of short-term warning, that's kind of what we mean of using it as a safety net. But we would love to see for the longer, extended warning modes and the advanced deflection mode and everything Sasha discussed towards the beginning of the talk, we'd love to see that, taken more into the standard model for planetary defense.
Thank you. Thank you for that. Checking again if Jason has his audio working, and I don't see any question being typed in this chat.
Yeah. Can you hear me now?
Yes.
Now we can hear you. Go ahead.
Oh, yeah. I was curious what kind of error bars you thought you might have on the max fragment sizes you're getting out of your simulations, or if you had any sensitivities that you looked into on that.
Sorry, so your question was pertaining to what kind of air bursts we would expect, is that correct?
No, what kind of error bars you thought you might have on the maximum fragment size from your L3D simulations?
Yes, that is a good question. Let me go back here. Sorry, my computer doesn't like passing through all of these animations. So at the moment, the error bars are, while not strictly quantified, we can very roughly say that because we use a finite size mesh resolution, we can only resolve down to a certain size. However, everything above that size, we can be fairly confident in those fragment sizes. And so, for example, just in this case, can you see my cursor if I move it around?
Yes.
Yep.
Okay, very good. So apologies for this, massive numbers here, but this line here, which starts at average speed, mass, and size, corresponds to the average fragment speed, mass, and size. And here on the right, you can see the average fragment size is 1.3 meters, which lives somewhere here in the middle. Again, like I said, I don't have error bars to give you off the top of my head or really quantified at the moment, but we do have this distribution, which is pretty well defined above the mesh resolution.
Okay, thank you.
Thank you. Any other questions or comments for Ian and Sasha? Jason, I assume that your hand up is from earlier. You can lower your hand. I actually have a comment about the question that was posed earlier about the Kessler effect. It feels to me that if an object is about to collide with the Earth and cause perhaps millions of casualties, the risk to the satellites is going to become secondary. So
Yes.
the answer to that will be obviously to do some collision probability analysis between the cloud of fragments and the satellites and tell you, okay, this and this can happen. But probably much sooner than that, the disaster that will be averted by pulverizing the object ahead of time is going to benefit the risk from the Kessler effect, which we can probably deal with in some way or another. It's not going to be nice to be maybe without GPS for a while, but definitely we want to avert a big, big disaster. So I think that's my intuition in terms of addressing the question about it.
Better than the alternative.
Yeah. It's basically managing risk, trading a big risk with a small risk.
Mm-hmm.
Excellent talks, very interesting topic. I and Phil have communicated many times in the past, and we met at conferences. I hope that you will come to the next conferences to present your work and perhaps establish collaboration with the next generation of planetary defenders. I'm reminding everybody is invited to contact Bryn and Sasha for additional questions, comments, and maybe even develop a career in the planetary defense area. So I think with that, we are ready to move to our next talk, which will be by Madhu Thangavelu, and it's called Opera 2, Fast Flyby Concept for Reconnaissance of Near-Earth Objects. Is Madhu online? I see the slides, but I cannot hear.
I'm present here, and I was hoping that you would be with us.
I was hoping as well, but that is left for the future. Good to hear you, Madhu, and hopefully we will see you soon.
Oh, great.
Go ahead and start. Your first slide is...
Can you hear? Oh, it's going to say feedback.
We can hear you loud and clear.
So can I get it close to that?
Are you in the room right now?
I think we are here.
Okay.
Oh, great.
Use the wireless microphone. I think it works better than the podium.
Wonderful. Okay, good. Folks, I'm very happy to be here with you all and with the folks who get the real data in real time. Paul is here. So many others I know. And welcome you all to this very interesting topic. Now, let me introduce myself a little bit more. And what I do is give people a brain shake and a fever during our studio at the University of Southern California. Some of you may know that USC is very active in areas like planetary defense. And my own interest is about the moon. And recently we thought that the focus of planetary defense on just the Earth is simply not sufficient, folks, because lots of things can happen in our neighborhood. And it's good to see that some of us are expanding our ideas about space situational awareness. And we are new to this, but we are doing a good job. So with that, let me run you through some slides about what I do, and then we'll get to my brain shake fever thoughts. How do I click this now? Point at the laptop? Oops, okay. Let's do this. Oh, good. So when I saw this, Paul, my thinking was, what would somebody like Jay Melosh say about this object that is heading towards the Earth? I would very quickly say this is a humongous piece of, I wouldn't even call it rubble pile or anything like that. That is a serious hazard for planet Earth. This is not an airburst phenomenon that's coming. And how would I say that? I would say Jay Melosh would look at this and say, the craters are well formed, they're circular, and perhaps hundreds of meters in diameter at a minimum. And it's heading towards total calamity on planet Earth. I mean, I wouldn't go to the idea of calling it a Thea or anything like that, but pretty bad. Very bad day. Oh, this way. Okay, good. A little bit tricky here. Okay, good. So USC has a very small program. It's very selective. And we get students, or they're older, mature, the program managers and project managers from the industry. Usually they come in for, as every student does, for a grade so that can move on and complete the program. And here you see how we've been advancing over the years. Let's see here. Okay, good. So within the Department of Astronautical Engineering, again, there is a difference between astronautical engineering and aerospace engineering. Folks, you need to look at the curriculum to know astronautical engineering looks at things outside of the atmosphere. And we are looking at spacecraft design and so on. Of course, we also put up some big rockets. I think Ken has put up pictures of our altitude record in launching vehicles. And in this program, yours truly is embedded, nested as a studio exercise in creativity. The idea is not to be exact, not to be accurate, but spill your beans, and we'll take it from there. And that's what I do. And sometime, I think it's been a long time, Paul. Some time ago, we looked at the idea of studying this topic of planetary defense. And again, this thing doesn't, oh, there you go. And if you look at the image there, and you can take your cell phones and click on it to go right into this area. You'll see, I think it was in 2013. Yeah, 2013 that we first looked into this. And I had no idea I was going to get sucked into something so vast and so studied. And in my opinion, so critically important to the species, human civilization. And so anyhow, I got in there, and then lo and behold, we had a lot of questions about what planetary defense is and what we can do about it. Our guests at USC include some stellar performers. Here you see, besides, what was that question? You see Buzz Aldrin, yeah. Lunar. That's true. And Buzz is a frequent visitor, and so is Nahum. Nahum is a reviewer in our studio, and we have doctors, lawyers. This is a class that has about 8 to 12 students per semester, but we have 100 people coming to attend the class because we get students from the School of Architecture, School of Engineering, professors, lawyers, doctors enjoy coming to this program. cinematographers. And as you can see, USC is a school that is very international. I keep forgetting this slide. There we go. And this is what I do in the School of Architecture. In one semester, I teach in the School of Engineering, and in the other, I go back to my alma mater, which is the School of Architecture. You know, architects have a way of very quickly coming up with ideas. And this is what we want to inculcate in our engineering community. Here you'll see students from all over the world, starting from the left. Starting from the left, we have French architects. We have SpaceX people from here, people from the Navy. If you go by nationalities, Iranian, Chinese, French, India is the favored nation at USC. And you'll see Iranian people in there, and China and Hong Kong. And, all of those people end up coming to our studio. So they are always asking very earthy questions, folks. All of you here are looking at planetary defense, which is a precious topic. But how many people do you know that talk about these things? Very few. Architects spend their lifetime facing clients about things like, how do I get my plumbing going right? How do I first of all grab my client's attention? Because without it, you don't have a contract. So those are the things that bother me. And lawyers, doctors, all have the same feeling, dealing directly with humans. And I wish we had that capacity as well. So while we are looking up at the skies and looking for rocks up in the skies, most of the people on the planet are very busy solving problems and solutions, looking for solutions. So one of the areas where you get to see this is in the United Nations Sustainability Development Goals. Yours truly was called into one of these science summits a few years ago, and I looked at these tiles, which are all very, very earthy. And I look at it and say, hey, why isn't there one on space? Why isn't there one specifically about planetary defense? Because if bad things happen on a Sunday morning, we won't have any more tiles to talk about, folks, literally. And these are things that we need to be impressing on the population. Now, this 2013 project caught the attention of the International Space University. How many of you know about this organization? So yours truly, that's good to see that. And yours truly was the willing victim for a team project. They wanted me to head it because I had published about what we did in school. And again, the hardcore engineers quickly said, hey, we looked at the literature. Mostly, in fact, all of it is about long-term mitigation. What will happen, like we saw yesterday or last month, if something happens out of the sky and boom, goes up over a city? And this is an area where we are catching our recent interest, and Nahum is leading it at Aero. Anyhow, this document here has the most number of hits within the IUSC community and around our community as well. So if you want to get a chance, take a look. It's on. Did you see it, Paul? Did you? You did. Okay. So now here's the man sitting right here who knows what's happening every day and listing it on tables. And so we get to see interesting things. I do go in there once in a while. No one points me to it. And I do get to tell. But this is what is happening, folks. We don't get to see much of it because none of them over our city. Some of it happens some of the time, but most of it goes unnoticed because a lot of it happens over the oceans and the seas and so on. So you want to go take a look at this CNOS website that Paul and others, his team, has been working on. And you all know this happened. And it's very funny because every time you have a conference, somebody sends one over. So I'm starting to think there's something wicked going on. Anyhow, this was a humongous explosion. Now, you may not think much of it except that it looks like this. And it's getting right on the biceps of the bay. I thought it's very interesting. What you're seeing is, I quickly go to the traffic map rather than anything else because it tells you how people are moving around the cities. And here you see a Google traffic map. That strike happened about 200 miles from New York, Manhattan. 200 miles. That strike, if it had happened in an airburst over New York, the president would have done some serious things, particularly this president, I'm telling you. But anyway, so these are the kind of things. And the reason, as I said, is we don't hear much about it because we live in a water world. Most of these happenings happen over oceans. So this is my pet peeve now. I am very interested in taking out these objects as soon as they appear in our skies, rather than over long periods of time. Keyholes and stories. They sound good, but really, when it hits you, is when probability becomes reality. So I posed. We are all in the AI domain now, and I can but just get to AI and ask it, hey, what would it be like if an asteroid or a meteor shower with some sizable elements came down on the moon? And this is an image that we got. It said we would have very high power lasers and fry them as they come in, because if they're going to hit our habitats, no way are we going to survive on the surface. We're working on the 3rd edition of the Moon Book, and already images are coming through which says we are going to go inside lava tubes. But anyway, that's later. So in cislunar space, not only on Earth, you get a hit, it's going to mess up a lot of things. And this is a question asked of our earlier speaker. What will it do to our mass, our increasing mass of observation and communication satellites? It'd be a real mess. Kepler syndrome will take in in a matter of minutes. So LOSOL, line of sight, speed of light mitigation is what I think you already heard Lubin talk about this, or if you haven't, you must look at his D-star papers. So this is what I'm concerned with right now, how to quickly take out something. And we have done some work. It's in our book. You'll see them. And there are some slides out. I'm sure Paul has some very critical remarks on it. But all the same, we are advancing very fast in this arena, folks. We don't hear much about it. But bottom line is pennies to the dollar compared to an artillery shell. And that's why the DoD is very interested in it. So we are accumulating objects in near Earth space at a very dramatic pace. And this will continue. At least we are sitting in the city, in the suburbs, very close to where some of the action is happening. And if you notice, the US has the most number of satellites. And as you know, these are the areas in which we operate. There are others too, but this is the general near neighborhood arena. And particularly look for this area here. Oops, 1 minute. Paul, did you see something funny? Here we go. This area is where we think there are some real good assets to work with. So this is what we are afraid of. And once in a while, it comes zooming, screeching right at us because as we get closer to the Earth, the Hill's sphere of influence gets it very quickly on target. And these are the things that we worry about. And a typical asteroid mission takes several years, folks, to plan and execute. And this is a difficulty that is going to be faced not only in coming missions, but how do we quickly react? And I saw some slides earlier on that suggested there are ways to do that. And as you know, radar and optical imaging is important. And I don't know, Paul, I heard bad things about DSN running, and I hope that's fixed because it's my own mentor's Eberhard Rechten was the builder. And he would tell us stories about the building of those, the DSN. So what is Opera about? What is this thing about? It's an opportunistic mission just to get a flavor of what these things are very quickly as opposed to a long-term planning. And we want to target something that is on the way, perhaps even in our neighborhood. And we see this every few months. There's something coming our way, Paul. And we are thankful for the CNOS thing. And what we can do now is what we couldn't do in the earlier, and that is using AI to not only detect, but also to do things about it. And the idea is very simple. You use a spacecraft, an asset that is already in orbit, about to be decommissioned, or as Starlink calls it, those that are in the death row. I think you've heard this. And attach stages to them, upper stages to them, and do a fast flyby. So how would you do this? Everybody will tell you, anybody who has done fundamental orbital dynamics will say, no, you can't do this without incredible changes, plane changes, and delta vision. So we are thinking maybe we can do this using some very interesting orbital dynamics. Now, these are the available stages, folks. They range from the very small to the very, very large. And we know how to use them. You're looking at the Ulysses mission. It was an off-eclipse mission, very high energy trajectory, 2 stages. You have a big stage here, right here, followed by a PAM stage right there. It put it in a high elliptical orbit that went around the sun and did some real magic. I hope Marcello is listening. Do you know Marcello, Paul? Do you know him? He was the Ulysses manager for, yeah, and I keep in touch with him. He's up in Anacortes. But anyway, so here's my thing that you want to take home with you. You would put as much of a delta V using very large or small stages, depending on where your vehicle, where your target is at. And you would have a high power laser attachment to it that would first shine some very nice, paint the object so that we get some very clear images, and you'd ramp up the powers so that you ablate it. You ablate a little bit, and using AI, you would very quickly download data on characterization of this. It's very simple. And again, using AI, it will happen in a matter of seconds, not even minutes. And this is a fascinating thing for us. You want to be looking at it. And again, it's a part of the low salt strategy. So what are the existing orbital assets we can use? Now, how are we doing on time, Noam? I'm sorry, I love to talk, but we got to keep our time. So we can use retired satellites, and there are several. And these are some of the people who can help us right now, because some have these upper stages sitting in their warehouses. And SpaceX, to me, is a very different beast, folks. It's turned things around and upside down for all of us in the industry in these past few years. And Starship can do magic if you can start to think about what they can do with it. There are many other companies here in the Southland too that I've listed here. You can take a look at them. And what I like about SpaceX is that it is the only company on the planet that is profitable. You know, all of us talk about sustainability, but here's a company that not only sustains, but sustains a workforce of 10,000, 12,000 people. It's changing the way we do business. And the sequence is simple. We dock a upper stage in orbit, and a solid propellant and solid props are much better for this purpose. And we would use existing LEO broadband links and advanced robotics, aided by artificial intelligence, to do this mission. And the images you're seeing there are from the 1980s and 90s, when Space Shuttle used to attach these propulsion stages and fly things. But we can do this now using advanced robotics in Earth orbit. So sequence of events are like this. We'd go very quickly and get Is Lindley still at Petco, Paul? Do you know? No, not really. Yeah. Anyhow, we'd go to Petco and to Paul's group and to the International Astronaut Warning Group and Same Page and so on, and get a very clear idea about what it is that we want to do. What is the trajectory we need to take? And then fly the mission quickly and get as much optical and spectral data as possible. And I think it was Adrienne Rudolph. What was her name? I enjoyed her presentation from Maryland University. Hope all of you give your slides so that we can all look at them, not only the video, but slide sets are very useful. And Ken will ask all of you to look at and bring slides. Anyhow, what I want to show you is how one time a wayward spacecraft was taken over and executed some very interesting plane change missions in the Earth, Moon, cislunar space. And this happened, and it saved Hughes a bunch of money. It saved the client a bunch of money, and it can be done. The moon can be your friend when you want to plane change with very little propulsion. Of course, the penalty is time, but 2 weeks, 3 weeks, a month, 2 months, okay. Okay, so with that, I'm going to slowly wind down. That is the pith of the concept. Here you see Bill Ayler and our chair, Nahum, behind him on the left and right over there. Oops, right there, Nahum. And we had a wonderful time. And we must all thank Ken, who does a lot of heavy lifting for these kinds of events. Ken, you stand up and you get, there you go, good. So I spent 2 weeks ago, we had the National Space Society. It's one of their topics is planetary defense. Bill Ayler has talked there before. And I presented the earlier set of slides. Ken, we had this set presented last year, I think, and I gave you the slide set too. So we should be able to present all these slide sets. And this is what happened there. It was well received. And one of the things I found is that people are studying how to fund it, how to fund planetary defense. And this, I will get these slides out to all of you so that you need to see what lawyers and financiers are thinking how to make this happen. And I think Andy talked here early this morning, was it? Yeah, okay. He was at the session. And it was quite an interesting gathering. I mean, I took this image. Somebody took this image while I was talking because I think people left or something. But it was very crowded. We had a good standing room only activity. Now, I want to ask you again for the one more time. All these folks are talking about our species and how to preserve Earth and how to maintain our the light of consciousness, according to Elon Musk. And what would happen if one fine morning that asteroid that AIAA put up would impact Earth? It'd be a very bad, sad day for Eden. So, I would tell Bezos, hey, listen, your ideas are great, move factories up and so on. But, you got to pay attention to planet Earth from this other angle, planetary defense. So, conclusion and summary. The current literature is too long, studies a lot of things, and I would blame the policy more than anything else, Paul, in how we went about planetary defense till today, most of it till today. It all began with the policy out of the Congress, which said, go look out for things that can cause damage. Guess what? 25 years later, 30 years later, we are still looking for things when we're getting hammered. Not the way engineers study problems, Paul. But anyway, Opera is going to look for activities happening close to Earth, impacting Earth in real time. And we will look at satellites that are about to be decommissioned, if possible, and use them. So we will use existing upper stages, employ mature docking technologies using AI, and we have a very, very important low Earth orbit comm infrastructure right now. You probably saw how Starship descends during re-entry, and we can do magic with that, with broadband, and use the Earth-Moon system to make plane changes, which we are taught in high school and in undergrad school that it's very hard to do using propulsion. And of course, we can use high-power lasers, which Phil Lubin and I have been thinking about for a long time to do this. And welcome you all. In a few days will be June 30 Asteroid Day. And we know there are some activities here and in Arizona. There are some good people who will be talking there too. And this is one thing that Nate Silver, the statistician that all of you are familiar with, the 538, says in The Signal and the Noise. I really want to say this. There is a tendency in our planning to confuse the unfamiliar with the improbable. The contingency we have not considered seriously looks strange. This is a very interesting term, all these terms. It's strange. What looks strange is thought impossible. What is improbable need not be considered seriously. I mean, these are words we use every day: seriously, strange, impossible. But reality and probability are not the same thing, folks. And I really hope you think this through, tell your folks about it. With that, I call this Opera because if you Google, if you land up in De Gaulle or Orly, the buses will ask, do you want to go to the Garnier or the Opera? The bus will take you there. And then you study Charles Garnier, the architect, and you'll notice that he had some very interesting things going on in his time. It had nothing to do with planetary defense, but I thought you'd like to really know about this. And you should visit this place if you get a chance. Some references here for you from our last talk. And I'm sorry I took so long for this, but thank you for giving me the opportunity. And think about this, folks. How do we make planetary defense more publicly available? Thank you very much.
Thank you, Madhu. Interesting, fascinating, and inspiring talk as always. Much, much appreciated. Madhu?
May I ask a question?
Oh, please.
Yes. So
this is John. This is John Ferber online.
Online.
Yes.
Okay, go ahead.
that was a very interesting presentation about using using an available upper stage to take a laser up there. But my question is, why bother to stop and pick up an an obsolete satellite from LEO? Why not just go directly up there with the laser and not stop and pick up an unused satellite?
Well, if you can build a CubeSat like our friend Ms. Rudolph said, that would be the right thing to do, and we can go directly. But the idea was, in opera, E stands for economics, and use what you have as a technology that we've been studying for a long time, and I thought that may be the reason. Thank you for the question.
Thank you.
Any other comments or questions for Madhu? Madhu, I will just comment about the last Planetary Defense Conference, something that's going to probably grow into more prominence in the next conferences in the near future, is that the whole topic of planetary defense is proposed to be expanded into the interplanetary space, with the moon and Mars being the next targets for habitation and visitation, and they don't have atmosphere or very little atmosphere. Even small micro meteorites, small fragments that typically are absorbed by our atmosphere, those the moon and Mars are going to be severely affected without proper protection. So, planetary defense is proposed to be expanded beyond just our own planet. I see a hands up by Nikki.
Okay, did somebody have a question? No.
Yeah, John Breeza here has a question. I just have a comment. I believe that wonderful idea about reusing orbital debris or orbital objects. I believe that orbital objects are junk. Space junk is not junk. It has value. And you're showing it right now with this comment, this conference. Wonderful, wonderful. But there was a comment, why use a MEO or a GEO? Because it has orbital energy already, and the upper stage would push it, and you would actually end up being less energy because of the orbital energy of the MEO or the GEO satellite that's decommissioned as well. So I wanted to thank you again for bringing that up, because we really need to look at, like I said, space objects as has value. Thank you again for the great presentation. Much appreciated.
Thank you for saying that, because we'll put that in our paper. Any other questions?
Thank you, Mike. Anything else?
I just want to comment on what Nahum said. All of us live on planet Earth, thinking that the other planets are similar. I mean, it's natural, because we spend our years in this gravity with a blanket of air, and that takes out most of the. I mean, it was Paul who corrected me a couple of years ago when he told me for a long time he said we were getting, we were sweeping up like 40 metric tons, and Paul said the new data says 100 metric tons of kind of, and per day. This is the important thing to remember, and we live in a very protected environment. And the moon, as Nahum said, gets whacked every day. And, Mark Robinson's CAD has got several fresh craters. And even Artemis 2, they were watching some impacts on the far side. And so these things are very different from what we do. Thank you so much again. Thank you very much. And Nahum, good to see you. Hope to see you.
Good to see you too, currently remotely, hopefully soon in person.
Hopefully we will see you at the review at least, Neil.
Okay. Thank you, Madhu. Appreciate it. So now I think the next step is a new activity that we are introducing for the first time in those mini conferences, and that is an asteroid deflection contest. I'm going to call Ken to come and see if we are ready for 2 or 3 steps in this activity. The first being a demo, and the second being the competition, and the third will be a little ceremony. So, Ken, are we ready to start the demo?
Yeah, we were going to have the 4 groups, 4 teams to take their table to get ready. So I'll confirm with you. Once David and we have the students seated at their tables.
Okay.
So right now we have 4 teams. Now you can interrupt me anytime. So I'm just going to read out the team. So the first team, temporary called Team A, is Sohan and Mr. Philip Turek and Orlando Cruz. Orlando? Where is Orlando? Oh, yeah, raise your hand. And Sohan? Yeah, you 3, could you, we need to kind of shift the table a little bit. So I think maybe you 3 can sit here. Sit in the front, just borrow the panelist table as the first table. Okay, the team B, and you can think about your team name. If you want to use a different name, like A, you can use Andromeda or something, or something you like or catchy. Actually, for folks, other people, you are welcome to follow this. Actually, we are going to develop this context, for the future. We'll make it more like a, robot tech contest, something like that. Make it more fun. Okay, so team B is Mario Estrada. Mario, could you raise your hand? Mario, okay. And Jose Estrada, Marcus, yeah. You 3, I suggest maybe sit at the. Yeah, okay. Yeah. Okay, that would be great. But then you have to have chairs too. Yeah, so Jose, Marcus, Mario, that table there. You can follow David. That's a team B. You are welcome to think of a name. Team C, Christian. Where's Christian Diaz? Oh. Christian Diaz. Okay. Brandon. Great. Alberto. Yeah, you 3 on the next table. Yeah, the table there, right there. You can pull chairs, move there. And bring your laptop with you. So team C, you choose your name. You can choose Cassiopeia if you want. Something attractive. Or we just put you team D, team C. Okay, team D, those 2 gentlemen, they flew from Purdue, so we put them together. Marcel, Francesca, Fonseca, Mr. Becker, and Mr. Kevin Lewis. Oh, okay. So you can sit at your table. I think that's good. So whenever you are ready, well, Team D, the name, Dracula or something, or you just keep it Team D.
Ken.
Yes.
There is a question online. How much of the competition is going to be shared online?
Because we don't, during the contest, we don't want the team to see each other's screen. So we are not going to show their screen directly during contest, right? Now, that's what you wanted, right? They cannot see each other during
That's right.
Yeah. So I don't think during the contest is a good idea to show each team's the screen, what they are working on. But we'll put the camera around and show their faces, that they are working. That's your idea. That's what we can do. But it's probably
exactly to show the contest itself. And for Adrian and everybody else, there's going to be rounds that are going to last 10 minutes. So they are not very long, and you will see what's going on there during this time.
Yeah. Folks not attending the contest, they can see for in person here. They can also try the scenario you are going to give assign. They can try on their computer, not in attending the contest, but they can try themselves, or they can watch and cheer for the teams.
Mm-hmm. Ken, is there a way to display the parameters of the contest online so that everybody sees the numbers that they should plug in?
Yeah, I got your sheet, so I will put I highlighted, so I'm going to share on screen of the scoreboard. So once we collect the score, we will add it to the score so people can see the round
for each
one,
round.
and round two and round three.
Yeah.
Okay, team A, are you ready? Team
So
A?
Ken, one more comment. Before we start the demo, I would like to call Paul Chodas to say a few words because
of course.
Yeah. So we are going to use this tool, and I want to thank first and foremost NASA for funding it. We have started, I think, about 17 or 18 years ago with the idea, then with the development of the tool. Most of the heavy-duty calculations were done by JPL and Paul Chodas specifically. And Aerospace developed a software tool, and we had a wonderful collaboration going on between CNEOS and Aerospace. There were two major phases. The first phase was delivered to NASA many years ago. It is available on the CNEOS website already, and I'm going to show where it is for those that want to try it out. And the second phase was developed over the last few years. It just completed in the last several weeks with all kinds of security checks. And so that's the version that we are going to use online. It is currently on the Aerospace external website. And soon the software will be transferred to JPL to incorporate into their own website. But I want to let Paul describe a little bit about the history and the functionality of the tool.
Sure.
So go ahead, Paul.
Thank you. Can you hear me?
Yeah, we can hear you well.
You hear me? Great. Yeah, Nahum and I have worked on this for many years. You're right. I think it was 2013 when we first put it online. This is a very realistic simulation of kinetic impactor mission. I seeded it with a whole bunch of. There we go. Thank you. So there's a bunch of hypothetical asteroids in here. These are not real asteroids, okay? But their orbital dynamics are all very realistic, and the sensitivities of deflection, delta V's, and how much it moves the asteroid in the target plane when it's approaching the Earth. That's all done very realistically. In fact, we're using a lot of our JPL CNEOS operational software, at the core of this app. So it's realistic. The kinetic impactor trajectories are realistic. So it's a good demonstration of the kinetic impactor, a good simulation of the kinetic impactor ability to deflect asteroids. I have to add a comment, though, that we have learned a lot over the last decade, and other capabilities such as modeling disruption and things like that are not in this app. So we're going to assume simple assumptions such as spherical asteroids, which are not rebel piles, so they won't break up. So you can hit them and they won't disrupt. But with that background in mind, this is a very realistic assumptions.
Mm-hmm.
That's about all I can say.
Yeah, thank you, Paul. You will see with the updated software, there is additional features that were added. we are not going to use any of these additional features in the contest today. It's going to be a simple kinetic impact deflection example. And so the plan, and Paul, feel free to jump in anytime if you want to kind of, walk around the players and help them out. That would be helpful. You are as familiar with the tool as I am. So the plan is this. So I'm going to give a quick demo of the teaming version of the tool that we currently have on the aerospace side. And after that, we're going to have a contest of 3 rounds, 10 minutes each, where each of the teams will try to maximize a performance metric. So I'm going to show it in the tool, and Ken, let me know if we can start.
Let me check if the teams are ready.
Okay.
Okay, Team A. I assume that the team captain is Mr. Philip Turek. Are you ready? Is your team ready for the demo? Very good. Team B. Team B is, I think, is with. Let's see. Team B with Mario, Jose, and you are ready for the demo. Computer, did you bring up the app already? Yeah. Please turn on the aerospace diffraction app. Okay, very good. Team C, Christian, Brandon, Alberto, are you ready? You turn on the aerospace diffraction app, right? Very good. Okay, Team C is ready. Team D, okay. 2 gentlemen, are you ready? Very good. So, Nahum, it's a go.
Okay, very good. So let me know if you can see my screen.
We can, yeah, we can see your screen.
Okay. So what you see on the screen should be on each of the laptops, because this is the homepage that Aerospace put together for the NASA JPL Neo Deflection app. Does everyone on the team has it on their laptop? Okay, I'm going to assume a yes. And I'm going to show 2 different things here. So this is the homepage that Aerospace put together. It has several buttons here. Most of them are taken directly from the JPL Seniors website. There is a tour and an overview. And I think when I talked with Paul some time ago, it could be that those descriptions and write-ups will have to be updated, but we'll see about that. I think for now, we have what we need. There are 2 main buttons here that could be pushed. The first one is the JPL app. The JPL app is the app that is currently installed on Seniors. It's active, but today we are not going to use it. For the contest, we are going to use the Aerospace version of the app. So for that, I will click Aerospace app. And if you can see my cursor moving around, I'm going to click it. There's going to be a form that's going to be loaded here. I'm going to click confirm. These are the terms and conditions of use. And the app is loaded. There is nothing else to do here except one thing. At the bottom of the app, there is a button here to move the app to a separate window, which you can size to the your monitor or laptop monitor. So I'm going to click that. And in my case here, I'm going to minimize that window. And now I'm going to stretch this window a little bit more so we can see what's going on there. And right now, the only thing you need to do, and I'm going to do it in this demo, is to turn on team mode right here. When you turn team mode, you are seeing a few panels and plots. I'm going to describe them quickly. On the upper right is your mission design panel. There are several parameters for you to change. We will start from the simulated asteroids that Paul mentioned. So there is a list of probably a couple dozen different simulated asteroids. None of them is real, but they're all realistic. We are going to pick PDC-19 object. So by doing that, the data for PDC-19 is loaded to the app. I'm going to turn T mode on again. It remembers that I picked PDC-19. Does everyone have PDC-19 on your laptop? Of the 4 teams. If not, now it's a time to voice for help. Okay, assuming that's the case, let's look at the upper left control panel, which is what I'm pointing out with my cursor here. There are 2 parameters up at the top. One of them is called time of deflection, and the other one is called transfer time. The time of deflection is the time at which the spacecraft that had been launched from the Earth is going to collide with the spacecraft. I'm sorry, with the asteroid. So the spacecraft that was launched with the Earth is going to collide with the asteroid and give it a little bit of a nudge. The transfer time is the time it takes for the spacecraft to travel through space from the time of launch to the time it collides with the asteroid. The default values here are 400 days for transfer time and 3 years before impact for the deflection time. These are all parameters that the mission designers are invited to change. We have updated launch vehicles here. And Paul, this is for your attention. The launch vehicles that are currently on the seniors website are out of date. There are probably some of them are decommissioned or in the process of being decommissioned. We updated the launch vehicles with those that are currently active. And this is the Vulcan with Vulcan Center with 4 solid rockets attached, Vulcan with 6 rockets attached, Falcon Heavy, and also we can select the NASA SLS. Okay, so these are the current choices. The default is 1 Vulcan with 4.
Excuse me, Dr. Melamed. Now, Madhu, just remind me, your cursor is not showing up on the screen. Maybe you can need to make a cursor a little bit obvious.
I don't know how to do that. Are you not seeing my cursor moving?
Oh, now you can see. Okay, now you can see.
Okay.
Yeah. All right.
Yeah.
Thank you, Paul.
All right. So I'm pointing to those 2 parameters here, which are the time at which the spacecraft will collide with the asteroid and deflect it by a little bit, and the time of transfer, which is the time it takes for the spacecraft to travel from the Earth to the asteroid. Currently defaulted 400 days. I described the launch vehicles that are available to us. This list is updated with currently active launch vehicles. Additionally, there is the diameter and density of the asteroid. Currently, the diameter is defaulted to 140 meters in diameter, and the density 1.5 grams per cc, per cubic centimeter. So we are now, okay, so down at the lower left is a plot of the orbit of the asteroid around the sun and the orbit of the Earth around the sun. And you can see there is a place where the orbits intersect with one another. And this is the place that by design, the asteroid will collide with the Earth. That data is stretched over 30 years in the upper right plot here. where T0 or P0 down here represents the time of collision, which is the green dot in the center of the Earth here. So when Paul designed that scenario for the Planetary Defense Conference 2019, that was the data that was used in the conference for the exercise. In the middle, we see some information panel. The main thing to pay attention to is that currently the perigee distance is essentially almost at the center of the Earth, which means we are going to have an impact here. We would like to replace the word impact with a missed distance. And the other thing that we see here, that the geometry is not in our favor. So there is just not feasible launch window to launch the spacecraft toward the asteroid. We will need to change the orbital geometry of those objects to be able to transfer a spacecraft from the Earth to the asteroid. And then on the right side, we see the B-plane, the so-called B-plane, which is sort of like the target plane. We see two circles here, one of them being the physical Earth in blue, and another one is a red capture zone in red color. The goal is to move the green dot outside of the red capture zone. Notice that the red capture zone is bigger than the radius of the Earth, and the reason for that is the gravitational focusing that occurs as the asteroid approaches the Earth. If we were aiming just to the edge of Earth, Earth's gravity would pull it in slightly and cause it to collide anyways. So we need to compensate for that by deflecting the asteroid slightly further out to compensate for the gravitational attraction of the Earth as the asteroid approaches the Earth. So with that, I'm going to start a quick demo. One of the useful tools in the demo is going to show something that was called deflection map. The deflection map is a map that is pre-calculated with deflection solutions. So everywhere you see here that has a color, it means there is a solution. White space typically will not have a solution associated with it. And so each one of those represents a value, which is the time of deflection. Remember the D value, and the time of travel from launch to deflection. And so if you want to use one of those dots as a starting point, you have to remember those values here and see what happens. So I'm going to close it now. This is a useful tool. And I'm going to try to design a deflection mission. Now, I'm familiar with this object, so I already know one of the solutions. But there are many, many, many solutions that are available. And so when you do your competition, we are going to use this object. We're going to try to maximize the performance index. Currently, the performance metric is red and negative. What does it represent? It represents the ratio between the distance of deflection and the cost of the campaign. As you can see here, we can use multiple rockets. Each rocket costs a lot of money. And so the more rockets you use in order to try to improve your performance metric, the campaign becomes more expensive to try to achieve a certain missed distance. So just maximizing the missed distance is not enough. You need to maximize the ratio between the missed distance and the cost of the entire campaign. And that's the performance metric here, right here. So currently, the default is just one launch vehicle, is this Vulcan C4 with 4 solids, and the cost is estimated by $200 million. And before we jump into the competition, I will just give a quick demo of how it works. So now I need to design a mission. You can change any of these parameters here in order to find a solution. I already know of a solution, so I'm going to change the time at which the asteroid is deflected by the spacecraft. As you can see here, the location of the object is changing along the respective orbits. I'm going to continue to do that until we get a solution. And soon we are going to see a solution. So now we can see we can launch, let's say, about 2 tons of spacecraft to collide with the asteroid. It's going to collide with the asteroid and give it a push. And surely you see the green dot moved from the center of the Earth to a new location. That's not enough because we need to move it outside of the red capture zone. So I'm going to continue to change the time of deflection here. And now I was able to move the green dot outside of the red capture zone. The performance metric became green and positive because we were able to create a deflection distance of about 0.3 Earth radii with a perigee distance of 1.3 Earth radii. And this value became green and positive. This is the goal of each of the teams, to find solutions that maximize the performance metric. And the highest value at the end of the contest will determine which team is the winner. Maybe one more piece of information here is that so obviously you can try to add additional launch vehicles here to try. Okay, so this is currently limited. So I'm going to change it in the campaign limits soon, you'll see. One of the things you could do is, if I will continue to click on any of those design parameters, you see that the green dot starts to move back. This is a nonlinear problem. Just changing it in one direction does not mean it's going to change in that direction. Currently, when I click any of these buttons, they jump by a value of 10 days. But you can refine it by going into this slider delta V's here, where you can change those increments to smaller, let's say 1. And I'm going to change the time of flight down here to 1 as well, which means now every time I click, it will change just by 1. And therefore, I can refine my solution to try to maximize the value up here. If something goes wrong with the app or between rounds, you click reset, and the app just goes back to its initial condition. You turn on the T mode and make sure that you're still on PDC 19. And now let's give a quick demo of how the contest will look like. So the first step for you to do is to pick a team name. You can either pick from pre-made names here, or you can type in your own favorite name. So I'm going to say Team A. A. And therefore, now I can see the Team A is showing on the screen. The second step would be to open the dialog for the campaign limits. And here, there's going to be a certain amount of numbers that Ken will share with you, and you will be typing those into your campaign limits dialog here. Just for as an example, I'm going to change the number of rockets to 2 here, everywhere, so that we can do something with that. I'm going to change it to 2. I'm going to change it to 2. And then the other parameters we need to determine is the time that the object was first spotted. When was it discovered? So I'm going to say, let's assume 8 years before collision with the Earth. And then there is a certain maximum campaign size. How many rockets can you launch all at once? So let's assume I have 4 here. And also there is a maximum budget that is available to me. I'm going to assume 4 as well. And now we are basically ready to start a competition. So where each team will input some set of parameters that Ken will share with the team. And when the ready, set, go signal is given, they will push the set limits and the contest will start. But for the demo, I'm going to change it to 3 minutes or maybe 2 minutes just to demonstrate what's going on. I don't want to drag it over 10 minutes because it's going to be a very quick demo, which I showed earlier. And when I click that, you'll see that the time, the clock is going to start ticking here. So I'm going to do that now. And you see I have 2 minutes to try to deflect it, but I know what to do, right? I'm going to, so the first thing I think I'm going to go back and change those increments to 10. So it's better to be crude in the beginning so you don't get bogged into just like very local area. And now I'm going to click on the time of deflection. Everything is like I showed earlier. And I see the green dot is moving outside of the red circle. It's kind of stalled. I can try to add additional value by changing the time of deflection. And I see that I have a value of 2.373. Now it's time to play perhaps either with those dates or with the launch vehicles. For example, how about launching 2? I can do that. So I launched 2 and I was able to increase the performance metric to 5.4. Maybe add another one of those rockets. And sure enough, I moved the object further out, but the value of the performance metric did not rise by a lot because it's now much more costly campaign. I can try to add another rocket there. It did rise it a little bit. So you can see here that by selecting a combination of launch vehicles and times, you can try to maximize the performance metric right here. So my timer is about to expire in a few seconds. I'm going to basically, I can try to add one more thing. Let's try to add maybe the, okay. So they tell me the maximum of launch vehicles exceeded. I cannot add anymore. So I'm stuck with that at the moment. And my timer is just about to expire. At this point, everybody is hands off, and the coordinators will read for each team the value of the performance metric that the team was able to achieve. They're going to put it into a spreadsheet, and at the end of the competition, they're going to sum up the metrics for every one of the rounds, for every one of the teams, and will determine who is the winner. So there are many, many combinations that are available here. And at the end of 10 minutes, you will see what's going on. So are there any questions so far? Okay. If there are no questions, then Ken, I think we can move forward to the contest itself. And Ken will share some cards with the numbers to plug in here. So Ken, can you hear me? I see people moving around. I don't know what they're doing. Is Ken still there? Can you all hear me? Ah, okay. Here's Ken. I cannot hear you, Ken, if you're speaking.
Coordinators.
Okay, now I can hear you. Mm-hmm.
I was talking to the coordinators.
Okay. Do you want to display the parameters for the first round on the screen? And I will fill it in as we go. So I'm going to click
Not yet.
Reset. Okay. Okay.
So your demo is done. You finish the
Yes.
demo.
Yes.
Okay. So now you're looking to start, right? Looking to start the contest.
Correct. Correct.
Okay. So I'm going to ask the coordinator to give the parameters to each team. So when they will input in the campaign limit, and they will input a parameter. When the coordinator will tell us if they are ready, but don't hit the set, right? The pop-up window, don't hit the button. Once you hit the button, then it will start. So we'll keep the pop-up window, and they will tell us whether they are ready or not. And when they're
Mhm.
ready, and you tell them it's go, and they will click the set limit, and that will start the contest.
Yeah. So
Okay.
can you read the parameters to me for this first round so I can plug it in?
Yeah. But first, yeah, let me give it to the coordinators.
Okay.
Yeah. So because if I read it, then the teams will know, right?
That's okay. Now it's time for
Okay.
them to know the
Then-
parameters.
Okay. Okay.
I'm going to plug it in as if I'm one of the teams, and they will see what I do. So
Yeah.
you can
It's
definitely.
PDC, yeah, it's PDC 19.
Yeah, PDC 19 should be here. I'm still sharing my screen, so make sure everybody has PDC 19 selected as the simulated object.
Okay. So now we are going to start the contest. So the each team and the coordinator, please listen to me and Dr. Menemet. Okay. Dr. Low, Toby, Mickey, Ajit. Okay, you stay with me because I'm going to read the parameter. Okay, so pay attention right now. So Dr. Menemet want to read the parameter. So the diameter, okay, the first C4, campaign limits. Have everybody clicked that window? Campaign limit. Did you
Look
click
on this. Look at the screen. You should see what I'm seeing here. Maybe
Yeah,
with
look at-
different parameters. We are going to
Yeah.
update the numbers here.
Yes. Yeah, did you have every team? Okay, team A. Have you started the campaign limit window? Did you open the campaign limit window?
Like I have on the screen.
Campaign limit. Did you see the pop-up window? Yes. Team B. Do they have the pop-up window for the campaign limit ready? You have? Toby, did they open up the camp? Okay. Did they open up the campaign limit? Oh, you need a pen. One second. One coordinator. Okay, Team D, did you have the campaign limit window pop up? Okay, the coordinator is going to give you the set of parameter.
You can read it loud. I will type it in as you read it, Ken.
Okay. So Ajit, please give it to the Team D. They are ready. Okay, so the first parameter is Vulcan C4 is 2, and
Okay.
Vulcan C6, that's
Mhm.
also 2, and Vulcan Heavy is also 2. NASA SLS is also 2.
2. Okay. All right. How many years?
Wait a second. Can I borrow? Oh, sorry, Nahu, I was reading from your screen. I saw you changed parameter. So, okay,
Oh,
so
no.
yeah. No. Okay, let's start it. Sorry, I was reading on the screen. So
No.
let's follow the paper given by your coordinator. So let me repeat again. Vulcan C4 is 1.
1.
Vulcan C6 is also 1.
1.
Falcon Heavy is 1.
1.
NASA SLS-2B is 0.
0. Okay.
Time first spotted or newly observed is 8 years.
8.
Number
Okay.
8. And vehicle campaign max is 3. Total launch vehicle number is 3.
3.
Campaign budget max is $3 billion. Is also 3. Exercise time is 10.
10.
Don't
Okay.
click the set limit yet. If you click the set limit, it will start a timer.
Yeah, don't click. Every team now should be ready with the numbers that you see on the screen, but don't click set limits because your timer will start to click.
Dr. Mena, there's a team, they have a question about the software, so I'm going to take a look.
Okay.
So,
yeah, go ahead.
So team, don't start yet. Don't click the set timer yet.
Yeah, don't click anything yet. Just be ready with the numbers that you see on the screen.
Which asteroid should we pick from the list?
No, just 19. PDC 19.
A or C?
Just 19.
I think just 19. Okay. This is
Just 19.
Yeah, they said 19 has several. Do you any? Just any?
Not any of them. No, just the one by itself. No, not A, not PDC 19A, but
so any PDC 19 is okay, right?
No, not any. The first one that has
the first
no
one
A next to it.
A
See,
is equal to.
I cannot click it now because I'm in the competition mode. But
Okay. So team, remember to select the PDC 19, the first one.
The first one.
Yeah, A equals to 1, 1.92, and then it's 1.8 and 0.53. So coordinator, please make sure they first select team mode and type in the team name, and then select the PDC 19 from the simulate near Earth object panel, and select the first PDC 19, and then click campaign limit and to type the numbers that's on the paper. So I'm going to take because this first round, I'm going to walk around and make sure they do it right.
Okay.
You were working, right? Yeah. Okay. Yeah. You can see it. Okay, so 111A3310 and PD's 19. Okay. Looks like you're okay. So who is the team captain? So this is PDC 1918 53 11130. Okay, don't click that yet. Did you type in the team number? Team name? You type in the team name? You did, okay. So you select who is the team captain? Okay, it's a 1.92, 1110, but A3310. Okay, don't. Did you put the team name in the beginning, right? But anyway, I in the beginning.
Your team C.
You have to type team C.
Yeah. Go back to
Yeah, make sure the PDC is correct. So you type in the team number, right? Team name in the beginning. Oh. Did you choose the team name?
You didn't prompt me for.
Yeah, you can type the team name. Okay. Wait, yeah, type in the name. Boiler. Purdue is the boiler, right?
Yeah, but boiler.
Okay.
we're switching
Oh,
out
okay.
with-
More your like okay,
More
very,
than
very good. Okay, then make sure PDC 1. Okay, and put the parameters.
Campaign limits
1110A 3310. Okay. Ready, right? Any question?
No, we would win is by what's the cursor? Do we win by the highest amount of processes here?
The highest of the performance metric.
Okay.
Then you can adjust.
Yeah.
Here, and you can do the fine tune. Remember, he was in the delta. You can change fine tune. It's good. Good. Okay, I look around the, seems like everybody get the right parameter and also input the team name. So just remind everybody the key point is to optimize increase the performance metric as high as possible in the green direction. And the other thing is, if you, as Dr. Meneman showed in the demo in the past 2 days, you first do the course adjustment. Then if you push the green dot outside the red circle, then you can try to click this the delta S, at the bottom, the slider delta S to fine tune. You can shrink each step by 10 years. You can 10 days to 1 days, and we can make some such adjustment. So Dr. Man, I think they are ready to go.
Okay, very good. So in this round, you can basically just repeat what I was doing. We are going to use the same object, the same parameters of the object, same diameter and density, and just like play with it for 10 minutes, try to maximize the performance metric, right? You've seen what I've done in the demo. Try to move those times around and the launch vehicles around and develop some intuition how to maximize your performance metric. So if everybody is ready, we can do a ready, set, go, and everybody click the set limits and go. Are we ready?
Yes, we're ready.
Ready, set, go. I'm clicking. And my clock is ticking now with 10 minutes. I'm going to do it myself, repeating the values that I've seen earlier in the demo, but you are free to use any of the parameters to maximize, right? So this is just like my first few steps. I have 1.554. Each team would like to maximize the performance metric. Try to make it as large as possible. You have about 10 minutes, 9.5 minutes. Good luck.
Everything okay, right?
Yes.
You can also start, yeah.
Right?
So you can adjust those things.
Yeah, just accidentally.
Yeah, that make sure there's
Wait,
a green and
yeah,
as high as possible.
Nice. 22%.
They just tell me they got a negative infinity, and I know we're more than
Yeah, that's
it's a little bit hard to make it.
difficult. Yeah, special price.
That's very low.
Needs to be green. This number needs to be green and as high as possible.
Yeah, right now we're still.
You see that, Christian?
Don't restart the timer. You cannot restart the timer.
Yeah. Yeah, no.
You basically adjust those parameters.
I got negative.
That you need to get it to green. Positive, high as high as possible.
Okay, 22.
Everything good?
Yeah, all good.
Excellent. Keep this number needs to be green and as high as possible.
Yes, yeah.
Excellent. You know, if you need to fine tune the steps, you can do that delta something.
Yeah.
You can adjust the steps. Okay, you guys are still 79.4. I'm not that good yet. Yeah, if you need to fine tune the step, you can click the delta. Okay. Right now, I'm not. I can't what you're trying to say. Let's stay in touch.
Yeah.
Very good. I think you can save the
About a minute and a half left.
Dr. Meneman, I'm trying to pop the scoreboard on the screen. Can you
Mhm.
see it? Did you see it? The sheet on your screen?
Let me see.
Maybe could you temporarily, because you are, can you temporarily stop the screen sharing from your end?
Oh, okay. Yeah, I can do that. Stop share. Okay. I'm not sharing anymore.
Okay, one team has finished. But for some reason, yeah, it's part.
Yeah, everyone should basically expire now. My timer is just about to expire. So everybody basically should expire at 0. And then the values of whichever performance metric is available should be plugged in. Exactly.
So you see the screen?
Yeah, I can see the scoreboard.
You can see
So the coordinator should read for team A, B, and C. Team A, B, C, and D should read the performance metric for each team now.
Okay, so
and plug it into.
Oh, so you have the score? Yeah, the problem is I cannot.
Can you type it into the scoreboard or no?
Yeah. Okay, let me see. Speaker standard. Something is strange for the screen here. I try to share my scoreboard, but let me first take care of the board. We have the score right now.
Everybody should have a score. You just need to put it into the round one line there. Can you type anything there?
Yeah, I'm typing it now.
Okay.
Team A.
So the coordinator should tell you the values, right?
Yeah.
7982. Okay, very good.
Team D.
Very good.
So for team B and C, you should have the score ready, right? The performance metric. Thank you. Thank you. Thank you.
Yeah. Okay. So that's very nice. We have round one completed. And we have the scores for round one. They have been summed up. Obviously, at the bottom, they're identical at this point. But after round 2 and 3, we will see how the total score will change. So with that, are there any questions or comments about the scenario? Are we ready to move on to?
Yes, yes, we are ready to move to round 2.
Okay. So do you want me to share the screen again or?
Yes, yes.
Okay, give me just 1 second here. I will share the screen.
Yeah, the same PDC 19. The first one. Where's Toby? Toby. Oh, yeah, sorry. Give it to them. The same PDC. No. Yeah. So each team coordinator has the parameters. Please give it to the team.
So let me just say one thing. Can you see my screen?
Can everybody see Dr. Menemet's screen? Teams? Yeah, listen to Dr. Menemet.
Okay, so at that point, I'm going to click the reset button. Don't start from the previous value. I'm going to click the reset button here. It's going to take the up to initial condition and get into the team mode. And now the scorecard will be given and we need to plug in some new numbers. But before we plug in some new numbers, I want to explain what we are doing. So previously, the asteroid was discovered 8 years before impact with the Earth. But over time, we took additional measurements. And so now we are moving forward by 2 years. And after 2 years, there were some adjustments to the size of the asteroid and to the campaign limits. So now, pay attention to the scorecard. I think there's going to be changes to the diameter, I believe. And I'm going to type it in on the screen like everybody else. So what are the new numbers for diameter and density after additional measurements over 2 years?
Okay, so I'm going to read the Vulcan campaign limits, new parameter, Vulcan C4, 2 launch vehicle.
No, don't read the campaign limits yet, Ken. Because you need to start with diameter and density. We need to adjust the diameter and the density here. Do you have those values?
That's right. All the teams, pay attention here. So the diameter for round 2 is 0.18 kilometer for the diameter. The density is 2 gram per centimeter squared. So the first one, 0.18, density 2.
Okay, I typed it in. Now, open the campaign limit.
Please, each team, you still have to use the PDC 19. A equals 1.92, and the E is 0.53. Please stay with the first PDC 19. And you follow Dr. Menemet, you click the campaign limit. So the C4 is 2. Vulcan C4 is 2. Vulcan C6 is 1. Vulcan Heavy is 1. NASA SLS 2B is 1. Time first spotted or newly observed is 6 years. 6, yeah. Then vehicle campaign max is 4 total launch vehicles. 4. And campaign budget max is $4 billion. 4.
Okay, so I typed in all of the numbers that you read, and every team should have these numbers in their campaign limits, but don't click set limits yet until it's confirmed every team has those numbers plugged in.
Yeah, exercise time is again 10 minutes.
Yeah. So the diameter now is 180 meters. Density is 2. Vulcan C4 is 2. The other ones are 1. 6 years before impact, and 4 and 4 and 10. Does everybody have those values plugged in? Do the coordinators confirm?
1116. Yeah, make sure the input correctly. Make sure the input correctly. Yeah, the PDC 19. Yeah. No, this is wrong. Diameter.
You didn't change that.
You need to change the diameter.
And to plot to.
And set the. Yeah, that's important. You set everything right? Oh. So the PDC 19. 6, right? 6. Yes, they are ready.
Okay. Everybody has the screen. Just look like my own screen here.
Yes.
Okay. So now we are ready to start round number 2. And I'm going to say, get ready, set, go. And you have 10 minutes to maximize the performance metric.
Started?
Everybody should have started.
If you can help me to move the camera around. Dr. Melamed?
Mm-hmm.
I will send the spreadsheet to you, so you can share the screen of the score from your end, because I try to share from my end, but somehow because the laptop here connect to the projector here is using the browser version of the Zoom, it didn't show up my screen properly. So in order for people here to see the score, it need to be displayed from your end. So I'm going to email you the score sheet, so it can pop up from your end, and then I'll update the score and send you the new one so you can share.
Okay.
All right.
Okay.
So I'm going to email you now for score.
Yeah. 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 And currently I'm not sharing, right? So.
Thank you. Yeah, I just email you, see if you can share the screen.
Okay. Not arrived yet. Probably will take a few seconds.
Yeah, this is a surprise because I share here. It looks like it show up on the attendees, online attendees Zoom, but it doesn't show up on the projector here. Realize the projector, they connect to the laptop using a browser version of the Zoom, so it may not show up to the right scale. So hopefully from your end, people can see.
Okay, I just got it. Let me drag it to the desktop here. All right, I have it. I am going to open it now. Okay, I have it opened up, and I'm going to size it so that it's showing. Yeah, okay, I have it.
See if you can share the screen. Hopefully that will work for the from your end.
Okay, I'm sharing my screen, and it's going to be this one, and share. All right, can you see my screen?
No, no. Somehow it's a black screen for the spreadsheet.
Really?
Yeah, it's the same issue on my end. I did the same thing, and it doesn't show up. But
what do you
I think
see?
no, I think what I can do, I can screenshot for that screen, and I'll just instead of the spreadsheet itself, we post a screenshot. So let me do this.
Oh, okay. I'm puzzled. Basically, the timer is expired for the teams, so the numbers should be plugged in. And you don't see my spreadsheet here?
No, now I don't even see the NDA. I don't even see your desktop. It's just a black screen.
Oh, so let me. Wait a minute. It jumped out of. Share.
I took a screenshot. So let me see if that will. Let me see.
Do you see anything now?
I think the spreadsheet affected it. There's some issue with the spreadsheet.
It's weird.
Oh, great. Thank you. Thank you. That's the score? Thank you. Very good. Yeah, something is very strange about the browser on the. I take a screenshot. It didn't work either. So probably going to ask if we can switch to my laptop.
Can you still not see my screen?
It's a black screen.
Ah,
it's
okay,
very
you know
weird.
what? Let me close this Excel.
I can see from my computer, and the online attendee can see. Oh, now I can see your screen. Now
Okay,
I
you
can
can
see
see
your
my
screen.
screen?
Yeah, and can you pull up the spreadsheet?
Okay, I'm opening it up. The spreadsheet causes some issues.
Yeah. Hopefully it
Do you
works.
do you see the spreadsheet opening up?
Yeah, it's opening up, but not yet. Oh, yeah, now it's good. Okay, now it's good.
Okay, you can see everything?
Yeah, keep it like this. Keep it like
Okay.
this.
Okay. So
Okay, so
let's plug in the numbers for round number 2.
Do you want me to just read it to you?
Yeah, read it to me.
Okay. So I'm going to read it to you now. One second.
I'm going to type it in.
Okay, I know. Okay, so I have the team E.
Which team?
Team B.
Team B,
Beta.
okay.
Yeah.
Team B, okay.
Let me. Team B is Toby. 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 Is this 9 or 4? Is this 9 or 4?
The 9.
Okay. Oh, 14. Okay. Okay, so team B is 14.934.
Okay.
14.934.
Yeah.
Okay.
Can you see? Can you see?
No, I cannot see.
You cannot see my screen? Again?
I can tell you, I can see from my computer, but not on the projector. You probably have to shrink it and reopen it. It's not
Okay, let me
updating.
type in the numbers. I will open it again.
Yeah, I can see it from my computer, but on the projector, it didn't show up.
Okay, let me type in the numbers for round 2, and then I'll close it and open it again.
Okay, the other team is Team D.
D, okay.
Team D. Yeah, the team name is, sorry, please correct me. It's a boiler maker. It's not
Boiler
boiler.
maker.
Yeah, boiler maker. Please correct it. Yeah, and their number is 18.670. 18.670.
I have it.
Where is team A and team C? Do you have the result? Who has your result? Mickey, do you have the result for team C? And Dr. Low? Yeah, the amendment is, I think after you input, you need to close and reopen.
We'll do that.
Thank you, Dr. Low. So for team A, performance. Okay. Team A performance metric is 6.189.
6.189, okay.
Team C,
Mhm.
3.808.
3.808. Okay.
That's right.
All right. So I'm going to save it. And I'm going to close it. And I'm going to reopen it now.
Yeah.
Okay. Can you see the spreadsheet?
Yeah, now it's okay. It's very strange. This the browser mode of Zoom is very strange. So you have it. So
Okay, very good.
So are we ready?
Let's move forward.
Round 3. So coordinators.
Coordinators, yeah. So first thing, reset, like I'm doing here, reset. And turn on T mode. And now we need to update diameter and density.
Oh, 18.6. Yeah.
Oh, okay. Yeah. Yeah, so now each coordinator for each team has parameters given to each team. So please, again, select PDC 19, the first one, and enter your team name. Data management, again, is a boiler maker. That's a Purdue, the famous brand. It's boiler maker. I make a typo.
Okay.
It's not boiler,
Okay.
it's a boiler maker.
Okay, we can fix it later.
Okay,
Let's
okay.
do the round. Yeah.
Okay. So now they are inputting the parameters.
Okay, can you read them to me as well?
Okay. Can I borrow it shortly? Yeah.
Diameter.
Okay, so each team, listen here, coordinator and team. So first you have to input your team name, and then you select the PDC 19, the first one. Then you have to change the asteroid parameter diameter to 0.19 kilometer, 0.19, and density it changed to 3 gram per centimeter square. So did you change it? 0.19 and 3 for the diameter and density.
Mhm.
Okay, so then, Dr. Management, can you shift your spreadsheet a little bit? I cannot see what you type.
Spreadsheet?
Yeah, because your spreadsheet is blocking your depression app on the screen here. Okay, so
Can you see now?
now I can see. Okay, 0.19 and 3, yes. And the campaign limits, so you click the campaign limits, then you see the pop-up window. So campaign limits for Vulcan C4 is 2. Vulcan C6 is 2. Vulcan Heavy is 2. NASA SLS-2B is also 2.
Okay.
Time first spotted or newly observed is 4 years.
Yeah, so this means that additional measurements were taken from 6 years to 4 years, which resulted in bigger and heavier object, 190 meters in diameter, 3 grams per cubic centimeter. That's going to be a tough round to achieve. So, and what's the campaign max?
Vehicle campaign max is 5. Total launch vehicles.
5, okay.
5. Campaign budget max is $4 billion.
Okay.
Exercise time 10 minutes. So
Yeah.
again, it's 2, 2, 2, 2, 4, 5, 4, 10.
Yeah. Okay.
Okay.
So is everybody ready with these numbers?
Let me go around and double check.
Okay.
So team A, are you ready? Okay. So it kind of took your sheet. So double check.
Okay.
You see the first one, 0.193. Okay. Yeah. So you ready? So this is the first PDC 0.193. Okay. 2, 4, 5, 4, 10. Okay. You ready? Let me check. Make sure this time, did you change here? 0.919, right? Yep. 3. 2, 4, 5, 4, 10. Very good. Yeah, you ready? Yeah. 0.9. Okay, great. 19, 3, 2, 4, 5, 4, 10. Very good. Yes, all team are ready. All system green.
Okay. All right, excellent. So we'll start it now, and it's going to be a tough one. My hint is that at some point when you get close to a solution, try to refine it with the deltas. Change the deltas to 1 or 2 so that you can make smaller steps to try to find a solution. So good luck with that. That's a tough one. So get ready, set, go. And I click set limits. Every team has 10 minutes. Okay, go ahead.
Started? Good.
Yeah.
Started? Good. Started? Good. Good. It's good to have big screen, right?
Yeah, I'm too nearsighted.
We need bigger. Yeah, first time we're perfecting. Yeah. Next time it will be, easier. Thank you.
Another hint that you might want to use is try to use the deflection maps. They might give you some suggested parameters if you cannot find them by trial and error.
Yeah, Dr. Melamed.
Mhm.
Yeah, since you are not here, so could we ask Paul to hand out the medals?
Absolutely.
Okay.
Absolutely.
Yeah,
It's going to be very appropriate.
all right. Thank you. Now he's not here, so at the end we're going to give the medals to the winning team.
Oh yes.
So could you, hand this to the team captain?
Yes.
He will announce the result, and you.
Okay.
Yeah. Yeah, the teams. They are the team. Next time you can mention. In the future, we'll have some music. Yeah.
You told us earlier, like on the back, that this is it's too short for them to understand the whole thing.
We have two trainings.
Yeah. We attended both, but it's like
not everybody attend.
Use they can't. Yeah, but we also send on the recording, so they can try. Yeah, now we get used to it. So this is how we do it. Yeah, we should have done it earlier. People, join the team. At least you have something there.
Minute.
2 minutes. 50 seconds. Oh. Yeah, but it's a lot of work for you. You are on emailing and this and that, all this setup. Yeah, whatever you need, let us know. I can. That means, yeah. Yeah, I mean, Glendora. Yeah, same. Near Pasadena. That's right. Yeah, so anything you let me know.
I am Gene Singh. I work with a lot of spatial folks. Shuttle was many things about the space age. You can learn anything you want about the shuttle. You can't learn what you learn. You can't even get to look at all media, probably as good a source of data other than space. Their own site is so limited. You'll see.
So the timer is just about to expire.
Dragon that becomes that
Oh, time up, right? Time's up.
Time is up, yeah. And the coordinators should bring the values from the different teams.
Yes.
And I will.
Yes, I'm waiting for their result.
Okay. Can you see the spreadsheet I'm sharing?
Well, again, not on the projector screen.
Okay. I will just send it back to you once I type in the values. And you can project it from your side. We only need one more line to fill in and it's done.
No, actually, on my side, I have the same issue. So you have the same issue, I have the same issue.
Okay, so what I do,
you need to close and reopen.
Close it and reopen. Okay. Okay, I closed it.
Okay, I have the score.
Okay, let me open the spreadsheet one more time.
Okay. I actually email you the round two. I changed name to Boilermaker. You can copy paste that name.
You just tell me, I'll type it in.
Oh, okay.
Okay.
Boiler. B. Boiler.
Boiler?
Maker. Yeah. Boiler.
Boiler.
Huh?
Maker?
Hmm?
Okay.
Because I saw you put a Boiler Baker. Oh, so Boiler Baker is good. Okay. Sorry, Dr. Mena, it's okay. They say Boiler Baker is okay.
I changed it to Boiler Maker. It's not right?
No. Change it back.
Okay, back.
Now I see what they are trying to. Actually, I got it right. It's Boiler Baker.
Okay.
But when I collect the sheet, become Boiler Maker. I think it's a confusion between their produce, the brand name and the team name. So they say Boiler Baker is okay.
Okay, no problem. And can you see the spreadsheet on my screen?
Yes.
Okay. So now I'm ready to type in the values.
Team A, 1.610.
1 point what?
610.
610. Okay.
Okay. Now I can see you typing, so you don't have to close it. Okay, so team B, 0.719.
719. Okay.
Team C, 1.777.
Okay.
Team D, round 3, 2.567.
2.567.
Okay, let me double check. 1.60, 0.1, 719, 1777, 2567. That's right. That's correct.
Okay. And now we have the total scores. And according to this, we have Team D, the winner.
Yeah, Team D. Yes. Team D is the winner. Yes.
And Team A, second place. And Team C, third place. And now they deserve their medals, which Paul can present to them.
No. Okay. The team. Okay, the first place, Team D, please come forward to receive
Team
your.
D. Yeah.
Oh, sorry. Team. You are the last one. Team, the third place. Who is the third place? Team C, right?
Team C is third place, correct.
Team C. Yeah.
Team C, congratulations. As one of the developers of this app, I'm happy that you know how to use it really well. Who's the captain? All right, captain of Team C. Third place medal, congratulations.
And maybe take picture of Team C with Paul, just for the record. Okay.
1, 2, 3. 1, 2, 3. 1, 2, 3. Thank you. Congratulations. Team A, right?
Team A.
Yeah. Team A, second place.
Do it here. Who is the captain of Team A?
This guy doesn't get the captain.
All right, congratulations, Team A. You did really well. Right. Go. And gather for a photo.
Photo.
Team 1, 2, 3. 1, 2, 3. 1, 2, 3. Excellent.
Thank you. Well done.
Nice job. Nice job.
And finally, we have the winner, Team D.
Team D, come forward.
Very good score, and especially in that last round. Thank you. Yeah, I think you had a good learning curve on this. So congratulations. You're the team captain.
Yeah.
All right.
Thank you.
Well done. Yeah.
Perfect. Okay, so now the teams, you can go back to your seat, and please, the panelists, please come forward to the front, and also on the screen. We here in person, we should have Dr. Paul Chodas and Madhu, panelists. Yeah, and Joe, since you are here, do you want to join the panelists, Joe? Yeah, and for yeah, sit here. Once they leave. Yeah, I put the in front of your so yours. Locally, three of you. Okay, 3 of you. You should have your that's sorry. Yes. Yeah, please take it back. Take it back. Yeah. Joe? Yes, this is your. This is your cup? No. Okay. So while panelists is joining, so for the panelists online, let's see who they are. So Nahum is still there. Okay, let's see. So who else is there? Professor Lupin is there. So let's start. Jason is still there. That's good. Jason, can you turn on your camera? And we have Russell. Okay, folks, get seated. We have very exciting panel session, so don't wander around. So grab your food and get back to the seat. Jason, can you turn on your camera? Dr. Pearl? Yeah, because you're not presenting, so your bandwidth should not limit your, the network speed. But anyway. So once Jason is back, we will turn on his screen. So, Dr. Manaman, I think we have all the panelists here ready. So you can go ahead.
Very good.
Folks, be seated. Get seated here. Folks, get seated. The panel discussion session is starting now. So please have a seat. Okay, Dr. Manaman, it's all yours.
Thank you. Okay, so I see who is on the panel? Jason, Phil, Russell, and Paul and Joe, right? In the room.
In the room, we have Dr. Paul Chodas, Mr. Joe Carroll, and Madhu here.
Madhu, and online we see Phil Lubin, Jason Pearl, and myself. Okay, very good.
Yeah, Dr. Jason Pearl should. Oh, he joined. He joined.
Yes. Jason Pearl and Phil Lubin have joined the panel. Okay, you have the mics, Madhu, working. Test.
Can you hear us?
A little bit weak. I think that the wireless mic works better.
Okay, can you hear us?
Perfectly.
Oh, great.
Okay.
Can you hear me?
I can hear you, Paul.
Okay.
All right.
This is for the local.
Oh, good. Okay. All right, folks. Who is in charge of the agenda? I think Nahum.
So yes, can you see me online?
I can see you very well.
Okay, very good. Okay, so I think that most of you all of you have introduced yourself during your presentations. So we don't need to go through that step, I think, unless you want to say a couple of words about what do you do now and what do you think about today. So some of the things that I'm looking for is a feedback about our talks. What can we do to improve? What can we do to add value? We are planning another one next year, obviously, and we fill the entire day today with very interesting talks, including the new feature of the contest that you just witnessed. I'm looking for feedback about all of these activities, ideas for new talks. One of the things that came up was, should we extend it to 2 days or keep it as a one-day mini conference? I think 1 day is plenty, but I'm willing to hear opinions. Any ideas for new topics? Sometimes we talk about planetary defense and asteroids, but there were ideas of expanding it to small bodies of the solar system. So that could be another topic of interest beyond just asteroids and planetary defense. So let's start with Joe. And Joe, say a few words about yourself. I think you already said it in the morning, but give us an update about your career, just like 2 or 3 minutes, and some ideas about feedback about today. And you need a mic, I think.
Yeah. I've enjoyed this. There's been a wider range of topics that than I expected, and I look forward to next year's.
Okay, great. Thank you. Okay, Paul, a couple of words about your experience today, takeaways. Yeah.
Sure. I noticed I didn't have a bio on the flyer, so I just should mention, I'm the former director of CNEOS at JPL. I've retired, so that's why it's blank. But still consulting with JPL on asteroid problems, including asteroid deflection. My background is in computing the trajectories, so I started decades ago before this was even called planetary defense, and worked many real problems, and then started working with Nahum and others on the planetary defense conferences and developing scenarios, so hypothetical asteroid impact scenarios for several of the iterations of those conferences. And we learned a lot by going through realistic cases and considering all of the variables that you would have to worry about, in particular uncertainty in the impact probability, uncertainty where the asteroid was going to hit, and so it took time, to learn enough. And then, last year we had 2024 YR4, and suddenly, it became real, and we had practiced this many times at the planetary defense conferences. So a lot of it was kind of automatic, not just the software, but the procedures and the notifications and all of that. So that was a lot of fun. I'm happy. I'm one of the two main developers of this app. Nahum is led the other aerospace team. I wrote the engine that you guys were using. I want to emphasize it's realistic in the sense that if we put in a real asteroid into this, and you had a real launch on one of these vehicles, and it's computing the correct trajectory to reach the asteroid, it's computing the maximum mass using the NASA coefficients, and it's computing the arrival velocity vector and transferring momentum, and all of that is done realistically. So you guys were working a real problem. That software now, Nahum, is 10 years old, 12 years old now. And so as I mentioned, we have learned a few things since then. And that brings me to one of the key topics today is disruption. Now, if you put in a small asteroid size into this app, such as YR4 was like 60 meters, you put that in and it's going to tell you how much you could move it. And it looks really easy to move YR4. But no, if you hit YR4, it's in a very eccentric orbit, and you're probably going to hit it with a centimeter per second or more, and that's going to disrupt it. And it may fragment into a few pieces, maybe not a total. In any case, disruption was a key today. So I should wrap up just by saying that that disruption was well treated today, robust disruption by Phil and his group. It was mentioned, first of all, by Andy in the first talk. He mentioned disruption. And Phil went through his modeling of disruption, and we heard about it also from Brent. And it's really important because on the small side, disruption is probably going to end up being the most useful mitigation technique. So
most painless to test.
well, yeah. Okay. So just because the asteroid is small and you can disrupt it easily. So I was really happy to see that today. I have a few other comments as well. I would point out that disruption depends on the mass. So you can't, the ability to disrupt depends on the mass of the asteroid. So you need to characterize the asteroid accurately if you want to be certain of disruption. You can't have the mass uncertain by an order of magnitude or 2 orders of magnitude, because then you won't be certain whether you can disrupt it or not. So characterization was another important part today. I don't want to dominate too much here, but there's a lot of good talks, and I'll leave the rest to discussion.
Oh, I would commend all of you for having participated in this exercise that has evolved over time, as Paul mentioned, and it's delivering what seems to be accurate results, and that's wonderful to see. I'm just looking at all of you right now, and you have to go out and make this topic of vital interest to the public. And I've been in that for, 12 or 13 years myself. And there is much to be done, because for some reason or the other, as I spoke to some of you, planetary defense it does not ring a bell like many other programs do, like we do with earthquakes or tsunamis or other very destructive elements like wildfires. Lots of people die, and then it makes the news and it seems to go away, because something in our species, psyche, it seems to forget or seems to disregard what we usually term as a probability event, and the possibility is very low, so we don't have to worry about it. But the consequences, Paul, I remember Jay Melosh, telling us about cratering and what it really does to planetary objects, and how far-fetched the effects are, particularly when you have a blanket of air atmosphere around you. And then you ask a geologist, and they'll just go through the history and tell you, oh, it's happened a couple of times, including maybe as later as the recent as 15,000 years or something like that. But the bottom line remains that all of us, I'm so happy to see so many of you at this meeting, thanks to Ken, who makes all this magic happen. And I'm hoping that all of you will go out and send the message out that planetary defense and impactors play a role, a deadly role in our evolution, and even more impactful role in our daily lives today. I think I showed you a slide about the airburst. These are terms we use easily and comfortably, but airbursts over Tunguska, for instance, devastates sizes and areas that are remarkably out of the discussion, because unless humanity sees it, I think we will keep on rolling in the same way. And from the academic point of view, from our little group at USC, we see that when you express your ideas in a manner to link it with large disasters that happen, like the tsunamis or the recent earthquake, and it's a human condition, Paul and Joe, that we have to somehow get over and make more public aware of.
Thank you, Madhu. Let's move on to the online panelists, and let's start with Phil.
First of all, I want to thank everybody who organized this conference. I thought it was terrific. I personally would not favor extending it to 2 days, but that may be just my age. I thought you did a great job. So I wanted to thank everybody who participated, whether I saw them in person or the behind the scenes here, because it really was a great job. I would like to bring up just a couple of quick issues. First on the point that was just raised. From our point of view, a lot of this really is a psychological issue. This issue of rare events being like history, those who forget history are doomed to repeat it. And in a sense, I think we're very much like that. The example I brought up of cars, for example, is a really good one that I often, being a teacher, bring up, is that you're used to participating in something which kills 100 million people a year in your lifetime. Sorry, about a little over 1 million people a year, and you don't think you don't think about it. Does that mean that you're guilty of participating in mass murder? No, you just find that the benefits of driving a car outweigh the risks of driving a car. But this is an area of rare events. So if Chelyabinsk had been over Washington or Moscow or Beijing, we probably would have funding flowing. But it didn't, and it doesn't happen frequently enough to interest a lot of people to put real money into it. I'm impressed that those of you that have spent much of your life in this area, spent much of your life in this area. It's very worthy to do so. But it's been a slog knowing, what you've had to go through. So, how do we get to the point of actually defending the planet, having an operational program, which is something we focused on a lot, as you probably saw? And how do we get the public to realize that it will happen again, and it's better if you're prepared for it rather than not? Also, I love the participation of the young people in particular.
Yeah.
And I think that would be good to encourage even more of. I like the fact that there is an asteroid day and that foundations like, B612 and others exist. I think those are very, very helpful. It's kind of like Earth Day, which took off, from an event in Santa Barbara, by the way, oil spills. Why can't we have an asteroid day? We'll arrange for an asteroid to hit the Earth, and then we'll have asteroid day after that. I know we have asteroid day, but it's not based on something that people fear. So anyway, you did a great job. I'd love to see more of it. The only thing I'd recommend is looking at other defenses. We've started some work on both the lunar and Martian defense as an example. The moon doesn't have an atmosphere, so that makes it more complicated, obviously. And also these issues that were brought up of damaging resources, satellites, spacecraft around the Earth, is a good example. We put a little bit of brain cycles into it, but not enough to do simulations. I don't think it's in general an issue. Also, it'd be good business for the companies that put things in orbit. They would love it. Just take them out every once in a while. Anyway, great job. So
say Phil, Paul here. Can you hear me?
Yeah.
Yeah. Don't forget we have Asteroid Year coming up, and that's sponsored by the UN. And so we're going to have a lot of focus from the public in 2029, and Apophis is going to bring it to us. So I expect a great deal of interest and enthusiasm about what are we doing in planetary defense and the International Year of Asteroids at Planetary Defense.
That's right.
Yeah, it's getting somebody to, put up the money to make it real, and that's the the biggest problem I've seen. We've been called in to give briefings before Space Force and other multi-agency groups, but getting someone to say it's my responsibility to do that, I'll take care of it. I have a mandate from, ideally international, but we know how that's likely to go.
Remember the International Geophysical Year in 57, 58, 18 months that led to the first launches into orbit.
Yeah.
And Phil, before we move on to the next speaker, I want to commend you on what you have done personally with respect to thinking about terminal mitigation of these bolides, rather than all the difficulties associated with long-term mitigation. Thanks, Phil, for taking on that part.
Yeah,
Thank you,
that
Phil.
program
Thank you, Madhu.
actually started in 2015, just in case you're interested in any of the history of it. Dave Dearborn and I at Livermore were chatting about stuff, and I said, hey, you know what? Well, can't we just bust stuff up? And, I like to blow things up as a child, so it probably came from that. It's toxic masculinity or whatever you want to call it. And then I put it on the back burner because I couldn't figure out how to do the breakup computations and the shockwave computations properly. When I got sent home in 2019 or 2020, whenever it was for COVID, I said, finally I've got something, I can work on in addition to several other papers I wrote. So, that was really the start of putting the whole thing together and saying, this should work. And then when I finally presented it to Dick Garwin, literally, it wasn't a joke. 6 hours later, he got back and says, yeah, this works, great. But, I know not everybody likes that idea. And we do get stereotyped into, these guys want to play chicken at the last moment. But that's not true, as I tried to express, that it is a technique which can be used universally. And I know we all have our turf, so there's always the NIH part going on here, not invented here. But I think if we all work together as a team, we could really make progress. I like the work you've done at JPL, Paul. I've been so impressed by the work you do to help everybody else see what the current threats are. And I send all of my students to your site to look at that. Just say, here are, real scientists working on a hard problem and doing the hard mathematics for us and showing what the orbital characteristics are, and this is critical. Anyway, thank you.
Thank you, Phil, and everybody else. So now we are going to move to Russell break and see what message do you have for us.
Yeah. So first off, thank you very much for inviting me. It was a pleasure interacting with you all. I came in a little, sorry, I came in a little bit late into the fold, but yeah. So I would say for my first time overall, I found the experience really kind of broadening. It's easy to kind of get in your personal rabbit hole of like, well, I work on this type of planetary defense, and you just kind of think about that. And it's good to hear from people who are working on other kind of complementary approaches. The more tools we have at our disposal, the better we are, for the human race. I also think keeping it at 1 day is probably a good idea for now, unless there's a preponderance of evidence to the contrary that no, we really do need to have it for 2 days because of all this amazing stuff we need to talk about. I echo the suggestions that have been made so far by Phil and Paul and everyone else. One thing I would add to that is I think it would be a good idea if we could loop in somebody from government, like any level of government, maybe like LA City Council, fire department, what have you, disaster response. Because we're all scientists and engineers. We can talk to each other about our cool ideas until the cows come home, but ultimately somebody's got to implement it. And someone with governmental authority has to say, yes, we're doing that one, launch. Because the best solution that never gets off a launch pad is really no solution at all. So I think if it's easy for me to say this because I'm not the organizer, but if somebody could loop in a government contact, maybe like a congressman or something like that, or someone from their office to say, hey, people are working on this. It would be great if you showed up and like maybe they get a speaking slot. I don't know if what that would be about, but just to have them even just here listening to what we have to say to kind of, start that conversation between people like us who are working on the cool stuff that's going to save the world and also the people who are going to fund us hopefully, and then make a decision on what gets picked. So that would be my suggestion.
So we do have those exercises, and not just at the PDC conferences, which are every 2 years, but also the NASA FEMA exercises. The latest ones conducted at APL, and we do involve decision makers from government. In fact, the 2021 exercise, which we called TTX4, I think it was, check them out on our website, the CNEOS website, did involve specifically the FEMA teams at the impact location. So, so not only did we have decision makers about deflecting the asteroid, sometimes that's possible, sometimes not, but also the response to the disaster itself and what to do to prepare for it if you can't mitigate. So we have been having yearly exercises that do involve the government, and that's eye-opening for us technical people because we don't know always how they think. The last couple PDCs were held at the UN, and we had international participation. And it's interesting to hear how different cultures would accept and interpret a warning of an impending disaster in their country, in Africa in particular. So we do that was one thing. And I have to mention our surprise at the TTX5, I think, which was conducted at APL, when we had a 13-year warning or something, and decision makers were called up, and we presented them with a 75% impact probability of a large asteroid. I don't know if you remember that one. And that, even though the warning time was getting down lower, that was apparently not enough time for them to fully approve a mitigation mission, which surprised some of us because 75% was to us meant you give authority to proceed to launch, not just one mitigation mission, but many different types if possible. So that was eye-opening. So my point is that we learn a lot when we involved other communities, decision makers, and disaster response people.
I think adding on to what Paul was saying, he's talking about the very high level, the highest level of government, domestic and international, that are involved with those exercises. And I can tell an anecdote from my side. I live in Culver City, which is a relatively small town here. And occasionally they organize a disaster response exercise or a drill for earthquake, tsunami, and who knows what. And we met with them, and I said, would you like to organize something around what happens if a Chelyabinsk happened in Culver City? And they looked at me like I came from outer space. They didn't even know what I'm talking about, right? And so it's a challenge, I think. It's the kind of thing that happens so far in between. It's like, how often do you call the plumber versus an asteroid deflector? Not very many. So I connect, it's a challenge on the local, very local, municipal level. And it's an ongoing and developing effort in the international level for the PDCs and the TTX. So that's excellent. Let's move on to Jason Pearl to see what you have to give us as a message for today.
I just wanted to thank you for organizing it. Yeah, you and Ken. It's been a great experience. I got to echo Russell and Bill. I think one day is nice. It's kind of nice to have a tight, focused conference meeting. I was thinking a little bit on what Paul was saying and how our network can be kind of disjoint at times, and what Russell was saying about people being siloed in their own kind of worlds. I know I kind of fall into that as well. It could be useful for a venue like this to have someone from like PDCO who just kind of overviews organizationally what's going on with planetary defense. So who's working on what, what the network is currently kind of looking like, what efforts are being made. Because, we do have these interactions like the modeling working group and the TTXs. So, there is effort towards solving these problems and money being spent on it. Kind of impetus with the government to try and get some systems in place. So it's good to just that everyone can be, I guess, more aware of what everyone else is working on. So it could help foster collaboration and things like that.
You do have a question for the panel at large. It's kind of a question that is open in my mind that I read about it and heard about it. So let's say, excuse me. Let's say an asteroid hits the planet on average maybe once in 1,000 years, and it kills 100,000 people. And you bring it to the decision maker, he says, well, that's 100 people a year, we can take it. What's your opinion about averaging the risk over the lifetime of the threat versus treating it as like an airplane crash, which kills 200 people in one shot, and they ground the whole fleet because of that? I mean, what should be the point of view to look at the risk?
Well,
anyone who wants to tackle that, feel free.
No, this is a question that should be addressed really beyond the scientific community. I think it has to reverberate in the humanities disciplines, and I think your son is probably more adept at being asked this question than we are. But I think, Nahum, that in our day and age, we seem to be quite deaf to anything that happens to our neighbors, and this is not only with planetary defense, but disasters like the one that happened just a few days ago in Venezuela, and and then wars. We seem to have become kind of I wouldn't say insulated, but the empathic response is lacking. And how would we respond to that? That's a good question, Nahum.
I'd like to break in. People who climb Everest know that they have a 2 or 4 or whatever % chance of not coming down alive. Okay, they accept that, but I don't think any of them would accept a 2 to 4% chance of dying in the plane getting to them or back home. People are willing to take chances when they are in control of that chance. Airplanes are far safer than cars because they have to be in order for people to fly them, to buy tickets and fly in them commercially. So there's a big difference between what causes a death. Is it your own screw up? Supposedly the most common last words of guys that die young were, "Hey guys, watch this." And the guys that survive, the first explanation is, it seemed like a good idea at the time. But you don't want other people to treat your life the way they are willing to treat their own. Okay.
These are issues that deal in collective psychology and
it does boil down, Nahum, to a cost-benefit analysis, and you can actually you should take a look at the science definition team reports that have been put together. I was on the most recent one, which was, I think, it's about 5 years ago or so, where you can actually try to do the balance of what it costs to mitigate an impact versus what the cost is of the disaster itself, and you have to put dollar values on lives and economies and all sorts of things. It's very complicated, but it does boil down to cost benefit analysis in the end. Unfortunately, there's going to be a residual risk that the current planetary defense policy is to focus on detection, because and let's find them before they find us, because that's the first step, and then predicting whether or not any are going to impact in the next 100 years, and the likelihood any serious impact in the next 100 years is small. So we're taking the risk that we're not going to have one in the next 100 years. And regarding one more point regarding developing an operational standby system for planetary defense, that's going to be costly at some level. You have to balance that against the likelihood that you will need it not in 100 years, but in the time frame of its technological viability, which for a defense system might be, 10 years. And so the question then is whether you will need that system in the next 10 years versus the probability of, the damage that would happen if you didn't have that system. And it's, again, cost risk balance. So that's my view of how it boils down.
Yeah.
One other thing I'd like to add is, so Nahum, you asked about, an airplane kills 200 people and that dominates the news coverage, but you didn't know when that airplane took off that specific airplane was going to crash. Whereas with planetary defense, we do know, like, hey, this asteroid will kill us in about 12 years, say. And to do nothing about that when you know with precision that it will kill you, it bespeaks a certain callousness that we rightfully disdain in our fellow human beings. So if you live in Southern California, you know that there's a certain risk of wildfires, and if you live in Los Angeles for 70 years, you probably will evacuate at least once over the course of your lifetime due to a wildfire. But nobody would put a house down if they knew with precision, hey, there will be a wildfire that will burn down your house on February 12th, 2033. So I think that's what makes planetary defense and asteroid impact risk kind of special, is that we do know quite far out that this is going to be a problem. And that's what I would tell the hypothetical skeptic of oh, who cares? So many people die from fires and plane crashes or whatever. But to know and to do nothing seems kind of categorically callous on its own.
And to go back to Nahum's first question, which is, how many people do you think are gray-haired leaders will accept in a disaster before they do something about it? And if any of you have thought on that, I would love to hear it. Nahum?
Kind of reminds me the Italian example with the scientists that were hired to alert for earthquakes, and an earthquake occurred anyways. So they were charged with crime because, hey, you didn't let us know. We hired you to alert, which tells you that, those kind of things are inherently unpredictable. And the question is, what do? You prepare some means that allow you to respond on demand, or just wait for the emergency and hope that you have enough time to do something about it, right? We talked about what Phil was describing, essentially minutes before entry versus years ahead of time in deep space. These are huge extremes. How do we tackle those extremes? That's an open question. I think Phil has a comment to say.
The way I often speak with my students is it is partly a psychological issue of rare events, but it's a little bit different in that there are some very rare events which wipe out a species or many species. And to some extent, I think we all know that the public is pretty sympathetic to the ideas of defending the planet. It's not a national boundary issue. It's something which is, the global good. So I don't think it's a problem getting the public on our side. I do agree with Paul and others that it is a cost benefit analysis. If I ask all of you, how many of you know somebody who was killed by something that came in from space, and hit them on the head, and the answer is, well, nobody. Whereas if I ask you, how many people do you know that were harmed by, whatever, car or walking across the street, or, you can probably think of somebody that was at least hurt. Yeah, I think it is a tough area to be in. The good part is the public is empathetic towards us. They really like it, as was mentioned, that we're going to see a very heightened interest in planetary defense over the next couple of years. How you translate that into an operational program or more observations, that is a difficult part, and it might not come from the public sector. It might come from a different sector.
Can you think of some, Philip? I'm sure you've spent some time wondering those topics about where a solution might come from, or who might be in charge.
The reason we looked at this so-called single launcher solution is that it's something which is very much already a part of our public persona. We launch these things very frequently for putting stuff up in space. We're going to be launching a lot more of these. If we start putting data centers in space, which I personally don't think is the best idea, but it's something which you tag on. You literally, hold the coats of somebody else that's doing something else and say, hey, if we just took one extra of yours and had it either available, or you would say that we could always borrow one of those if we had an emergency, then I think it's a viable plan going forward, and it doesn't cost that much differential compared to the cost of all the launches that are going up for other purposes. It's a delta, and the delta is small. So I think there might be something there. I do agree, working together as a community, so we're not working against each other, but we're working, for each other. We could bring something together to the public and explain. It wouldn't cost that much. I think that part of the issue, my background's in early universe studies. I just got this because it was kind of fun. It was mathematically interesting to me. But, if I look at it from a cost-benefit analysis, I totally agree. The number of people I know is zero. The number of people on average that's killed per year from events, just averaging over long time periods, is pretty small. And so you'd have to say it's not worth doing, given that there's so many other things that are more important, such as solving, for example, polluted water kills about 3 million people per year, most of them children in the world. So that to me is a much higher priority if I have to prioritize things. But if the delta to protect the planet is small using technologies that already exist, then I think it's a much easier sell. And I don't know, just urge a little bit of thought. Maybe we could talk more about that in general. And there are people who are interested in stuff like that too.
Can I add just one point while I have it in the front of my mind, and that is we hear about cases of commandeering a satellite or something and putting a stage on it, and let's go protect the Earth with that, or make it a kinetic impactor or something. I just wanted to caution, having worked many realistic scenarios over the years and developing, a hypothetical. I looked at the population of asteroids. Most of the asteroid orbits are eccentric. So they spend a lot of time far from the Earth. YR4 goes all the way almost to Jupiter, spends many, a year or more way out there. My point is that asteroid orbits are not circular, as you often see, and if you just see a diagram, the spirograph diagram that is something that I created that you saw in some of the presentations with all of those orbits indicates that they're eccentric. It doesn't really show how inclined they are. My point is that the orbits of the asteroid, threatening asteroid, can be very difficult to get to. And so it's not non-trivial to go and intercept them, rendezvous with them. Interception is not so much of a problem because by definition they come to 1 AU at the Earth's orbit. So that's actually a great interception point. It turns out that, we have a lot of missions to asteroids where, scientists want to investigate them, and let's see what we can do. DART, for example, picked an asteroid to test kinetic impactors on. These asteroids are selected by the scientists because they're easy to get to. The threat of an incoming asteroid may be in an orbit that is not easy to get to. In science,
Way off the ecliptic.
are they highly inclined or very eccentric? The point is that in science, you get to pick the target, but in planetary defense, the target picks you.
And that's what we have heard. Nahum, an interesting thought that you may want to query everybody about is, are there any examples that planetary defense as a topic can hitchhike on to make it viable? One of the things that came out of that READY study at ISU was the idea that if you look at how a fire station works, they may have some interesting analogies to follow. And then the CDC has some things, and FEMA has some other things. And are there ways to make PD established, take root in some of the other organizations, Nahum?
Yeah. So for that, my opinion is that I think it was Paul, or I forget now who said that it's down to return on your investment. What are you gaining in the short term, right? Nobody wants to see a return on his investment in 100 years, right? Because it's irrelevant to its business. They want to see some return to their investment in the relatively short term, unless it's a government policy that says, this is in the benefit of the nation. We need to invest in a certain protection that will protect the nation, regardless of do we make money out of that. But if we are moving into the commercialization era now, where there is partnerships between private and public organizations that basically just use public money to do things, they have to see relative return in the short term. Otherwise, they will not invest in you. Even if in 100 years something really bad will happen, they don't see it as a part of their business. This is the business of the government to protect us from something that might happen in 100 years. One of the things that we were thinking, I guess this was in one of the conferences that I attended, with a lot of representation of startups that are intended to do space resource utilization. And we said, we have so many techniques to deflect asteroids. Some of them involve fairly elaborate engineering operation. And so, okay, we took an asteroid that is headed to the Earth. We did a whole bunch of things to move it away from the Earth. Can we now use that capability to extract some stuff from the asteroid and use it for commercialization? So that's an open question, right? This is probably, we're currently in the baby step era of trying to exploit the space resource for our benefits. I think that I saw Mark Henley's hand up earlier, and I wonder if you have a comment to add.
Sure. Why don't I add a couple things? And thanks for inviting me into the panel discussion.
Good to see you, Mark.
Yeah, you too.
Are you local or in Hawaii?
I'm here now in California, but
Okay.
in my 100-year-old house. But let's to Phil Lubin. This, I see a lot of effort going into trying to say that the terminal defense is not what you're really aiming for. But to me, that's actually the biggest hazard. Those are the things that, for two reasons. One is that if there's a real hazard, people will put off the decision until it's too late, and then they have to do terminal defense. That's one. And the other one is that, the real hazard is smaller stuff that you're not going to see and be able to catalog ahead of time. So, when I think about the kind of systems you develop, it seems like you would want an airborne system that would be able to, to be deployed ahead of time all around the world, and like a Pegasus type of thing that could just fly in and intercept a small body. That's not a severe hazard to the whole globe, but it's a local hazard. That's kind of one of the things that I came out of this with. I might talk a little bit later. I had hoped to talk about the effects of lunar impact on the Earth, and I talked to Nahum and had kind of a slot for that, but I worked on it overnight and wasn't ready to talk about it in detail yet. It's just that I suspect that the Earth has really had rings around it like Saturn and other planets in the past, and that those are due to lunar impacts. But let me go back to the whole real hazard of small bodies and the possibility of interception and terminal defense on a small scale. Because to me, to have a big launch vehicle sitting on the pad is tricky, but to have a Pegasus type of airborne launch system on the wing of an airplane is pretty easy. Yeah.
Oh, let me take it to a different level. I am wondering if in the room or online there are still some of the students that were involved with the contest. Anybody is still there in the room or online that would like to voice an opinion about their experience today, or left for dinner?
I think most of them have left, but
Have left. Okay, so we'll skip
but,
that.
but we have one IRCU student who was a
ISU
long-time
student.
IRCU.
Okay, who is the person? Would you like to say a few words? Why not? Yeah.
My colleague have written here. So it's a question for all the panel members. What is your take on multiple kinetic impactor strategies, especially like what do you see as the most promising technology in the near future for deflection? Because there's been some talks on ion beam deflection, kinetic impactors, right? We're now sending the Hera mission as a follow-up to the DART mission. So there's some interesting new higher level of technology readiness in terms of kinetic impactors, but now we're also bringing into the discussion there's other technologies. I wanted to see what are your takes on that. We saw also interesting case presented for the PI, the pulverizer, right? Appears to be more for short term when the warning time is short, but it seems that if it's done correctly, it could also be done in longer time frames, right? So that's more or less our question. I want to see your views on that.
Sure, I'd be happy to address that. In particular, ion beam is something that I've been studying for years now, and it is one of the possible tools in our quiver for mitigation. So I could address that one first. You need to rendezvous with the spacecraft, with the asteroid, and then establish a station keeping position. Have two equal and opposite thrusters, one of them aimed at the asteroid, and the beam from that thruster is close enough that the beam from that thruster impinges almost entirely on the asteroid. And so what it does is effectively slow push the asteroid over time. And you might ask, well, a beam can't, deliver that much momentum, but ion thrusters exhaust velocities are like 70 kilometers per second in some cases. The current technology is a little bit less than that. So and if you have 1,000 kilograms of xenon and you have a couple of years or more, let's say 4 years, you can apply that over time and push the asteroid enough to make it miss the Earth. That is a technique that will work for increasingly better for smaller asteroids because of momentum transfer. And so if the asteroid is less massive, you're going to get a larger delta V. It won't take as long, etc. So ion beam deflection is very useful for the asteroids smaller than, let's say, 150, 200 meters max if you have 10 years, let's say, of warning. And by the way, that's a whole nother topic that we should address, is how long it takes to develop and a spacecraft and launch it and get it there. And ion beam takes time. I forgot the other part of your question.
Paul, I think that if I remember from...
So thank you. Multiple kinetic impactors, definitely. The idea there is that a single kinetic impactor, if you don't want to disrupt the asteroid and fragment it into pieces, you can't have a large spacecraft because it will simply deliver too much momentum at the typical intercept velocities. As it turns out, the place where you want to intercept an asteroid is at the node, which is at 1 AU by definition. And it's really easy to get a spacecraft from the Earth to another location on the Earth's orbit. Right? That doesn't take much delta V. So typically, you're going to be intercepting it at 1 AU, so the velocity that you're intercepting it with is basically from what the asteroid velocity is at 1 AU. And so it could be, I don't know, 10 kilometers per second, 15, 20, something like that. And so, the intercept velocity, you have to design the size of the spacecraft, mass of the spacecraft, so that it won't produce too much delta V to disrupt the asteroid. And that depends on the asteroid mass. So it's a long-winded answer to say that we need to characterize the mass of the asteroid before we would want to use a kinetic impactor that comes anywhere close to this disruption threshold, which we use as 10 times 10% of the escape velocity. So that's why you can't necessarily deflect the asteroid with one kinetic impactor, as we've been doing in our app here. In reality, you've got to size the spacecraft according to the mass of the asteroid, which you don't know initially. So that's why you need a characterization mission, which is why you have to delay the launch of the kinetic impactor until you know the mass of the asteroid. And so there's all these complications. If you design multiple kinetic impactors, you have the same problem, but you can make the spacecraft smaller. Now the question then is, how far apart can you deflect an asteroid, and what does each one do to the strength of that asteroid?
The choreography would be...
It gets complicated, is my answer.
It'd be good for a movie.
Well, but I think it's a viable technique if you're within the right range mass of the asteroid, and you don't need too many of these kinetic impactors. So it's certainly a viable technique. Yeah, I agree. I hope that answered your question.
So I think Jason has his hands up, but before that, I think, Paul, in some of our previous conversations, I think you mentioned that the ion beam deflection has the advantage that it is agnostic of the shape, right? Yeah. And so you don't need to know. It's kind of less of a burden on characterization because you don't care about the shape of the asteroid. You only care about the mass.
And in fact, LeHoum is a rendezvous mission, so you don't even need to know the mass when you design the spacecraft, frankly. You can just go there and measure the mass, and then you'll know how long it will take and where to station the spacecraft in order to get enough delta V on it. So the ion beam is to a large extent independent of the asteroid physical properties. You can design and build it and launch it. Problem is, it takes time to get there. And I just said in an earlier comment that some of these asteroids are very difficult to get to, and especially for rendezvous. So it's not something you can use in all cases.
Yeah, of course. There's a whole toolbox of methods and techniques to do that, and this is just one of them that might be suitable in certain situations. But let's go to Jason. I think Jason has hands up. He wants to say something.
Yeah, just one minor comment on the multiple impact is, an area that it's an area we need to explore more. And particularly, if you're hitting it with one impactor, you're going to generate a debris field. So any subsequent ones will be passing through this debris field, which could be a complication, especially when you're traveling at those speeds. And then, timing multiple impactors at the same time, you end up, getting into engineering challenges. So there's a lot of interesting work to be done in that area and pursued further.
And Jason, I have to mention that if one kinetic impactor breaks it into two pieces, suddenly it's a mess, because then we have to predict where each piece is going, whether it hits the Earth or not. That takes time. We need a data arc. Yeah. So you just don't want to fragment it into significant large chunks. So you got to stay away from there.
You have to break it up. You have to break it up into many small pieces.
Yeah, either you break it up entirely. That's a viable solution, but you don't come in this gray area where you might just split it in two.
Yeah, that's a great point. And also, as in DART, they used optical systems to navigate towards the impact. And once you have this bright cloud of material, that could be a complication for those systems. But again, I'm getting a little bit out of my this is important.
No, I'm trying to visualize this to see you have an impactor and it gets the bolide right head on, face on. It splits into several pieces. And then you have a second series of vehicles that are headed towards these separate pieces. So I'm wondering if any of you have thoughts on how AI might tackle this kind of updating of the trajectories in flight so that each of these separate impactors could go after the more dangerous ones. I mean, so there's a lot of feedback and in the loop. Yeah.
I'm not aware of any concept that involves using AI with planetary defense.
No.
Maybe others have heard about some techniques like this. I would say that just like intuitively, if an object breaks into several pieces, there's probably a large amount of uncertainty with the resulting trajectories. And I don't know if you have enough controllability to even maneuver vehicles that are already in space to tackle those fragments. I think it's a whole engineering study, but I'm open to hear after other opinions.
If I might add, this is why really you don't want to use a kinetic impactor until you have an observer spacecraft there and measuring the effect and the change in velocity. And in case it splits in two, that would also provide enough data. You cannot get that data from the Earth. So you would have to wait years to find out where the fragments were going, and that's not possible. So you need to have an observer already on station, which means you can't hit the asteroid until you can rendezvous with it with an observer spacecraft.
And that takes more time.
And that's going to take time. Yeah. So all of these mitigation methods do take time, and probably on the order of a decade warning time required to get all of these things done, characterize the asteroid, get a rendezvous mission there, and then design how large the kinetic impactor should be once you know the mass, and then launch them and get them there. That all takes time. And so roughly 10 years is a good estimate.
I can imagine our meta going out, in a certain choreographed pattern to tackle this issue. I can see an inkling in Philip's eyes. Maybe he has some thoughts on how we could do that. But don't underestimate AI, because I've been subjected to some on my machine, and I'm still scratching my head to see how it all works out. It's got its tentacles on everything, and yours truly handles mostly the graphics part, and some of it is pure hallucination, and sometimes you get up and say, how ridiculous. But the fact is, there are things going on in the mind of AI that may have implications for planetary defense. Philip may have some thoughts on this. I don't know.
I think Mark had his hand up first, so I wanted to.
Yeah, Mark, go ahead. Have a comment.
A question earlier, and so I hope to get a response. But this is also to Paul's comment about how difficult it is to rendezvous with an asteroid, and I noticed that this 2024 YR4 asteroid is coming back in 2028 before it comes back in 2032. and it's it's unusual in that it seems to be almost on a 4-year return cycle. I wonder how that happened or why, but it seemed like there's an opportunity to rendezvous with it if you were to put together a mission quickly and launch it and be there in time to match speed and perhaps even land on it and do other things, investigate it over a long period of time, and before it comes back to in close proximity to the Earth in 2032. And so that one just seemed like a very unique opportunity, and I hope to explore that more.
It's a unique opportunity, but don't confuse the fact that an asteroid comes near the Earth with the fact that it's easy to rendezvous with it, because you need to match the velocity, and wire force coming by very fast. And so it is non-trivial to rendezvous, even despite how close it comes to the Earth. You've got to match the velocity.
Essentially, you launch to the vicinity of where it's going to come by, and then you match its velocity, right? And have some period of time to observe it. Anyway,
Phil, do you want to add something to that?
Are you asking me?
Yeah, go ahead, Phil.
Sure. Yeah. So just a couple of quick thoughts. First of all, absolutely going far away to stop something that's going to come to you seems like maybe that's not the right approach. Let it come closer. There's an old saying, keep your enemies close. So let it come closer and do the hard work for you, and then you take it apart, which is one of the reasons why we focus partly, and we get stereotyped, but we partly focus, hey, we could actually deal with pretty big things on pretty short notice. So let it come close. We don't have to rendezvous. We just take it apart. The other thing I want to say, which I probably shouldn't say, but I'll say it anyway, is that we wrote a short article once called "Planetary Defense is Good, but Planetary Offense is Better." Now, that will disturb a lot of people, but that's okay. So there are repeat offenders out there that perhaps should be incarcerated. Apophis is one of them. And most people in this community, I don't think, would be in favor of this, but I don't think it's such a terrible thing to ponder. If you know a threat's likely in the future, maybe just get rid of it, just like we do with vaccines, is you get rid of that which is going to come back and hurt you. Just a thought. Okay, so I probably don't want to push it too far.
Thank you. So I think we are getting close to wrap up here. I have a question to everyone about, I like to hear how the day went, any suggestions for improvements or changes, and especially about the new element, which was the contest. And Paul, I'm sure, will have some suggestions for improvement on that. I will just say a small anecdote about the development of the app. As Paul mentioned, it started about, I think, 17 years ago, and the credit should be given to Lindley Johnson. Right? We were looking for a project, and Lindley Johnson said, "Why don't you develop an app, an asteroid deflection app?" So the credit really belongs to Lindley Johnson. But how it really happened was, as you know, I work at Aerospace. Aerospace has many social clubs, right? Reading club, working club, astronomy club, investment club. And they have a women club. And one day I see an announcement that someone like one Bill Ailier is going to give a talk to the women club about asteroids. And I'm saying, I would like to hear the talk, but it's a women club. Shall I walk into the lion's den, so to speak? I decided to do that. I went into their meeting. There were several dozen, aerospace women that came to hear Bill Ailier. He talked about it. I was the only man. Everybody looked at me. And I didn't care about it. It was just a topic of interest for me. And on our way back, I told Bill, I'd like to do a project about it. And this is really how the deflection app started. we approached Lindley. Lindley gave us some ideas, and then we got funded, and that's where we are now. So many thanks to Lindley, to Paul, for all of the hard work that went into developing the app. I just want to hear, as a wrap-up, any feedback about today and whether the contest was useful, should we do something different there, and so on and so forth. I thought it would add some dynamic element in the afternoon. Sometimes people tend to leave in the afternoon, but hey, if there is a dynamic activity, they can participate in a contest, they will encourage them to stay and then also to be part of the panel. And so just general feedback from everyone. Phil, your hands is up.
Yeah. One suggestion is to hold lightning talks. You know, yeah, these sort of 1-minute talks, which you've probably been to some conferences where we do things like that. And I find them actually to be quite interesting, also particularly to ask students to present, 1-minute talk. It doesn't take much time, and often the dynamic is really good. It's a lot of fun. And you might ponder something like that. I did love the app. I would love to see your app more applicable to what we're working on, which is, you have two choices. You could deflect it or you could destroy it, your choice. And if the app could give you that option, that would be really fun. Okay. I love the app. I was starting to play with it myself, but it looks great.
Absolutely, Phil. That's on our list. I think it would be a great idea. I mean, the app just does kinetic impactors only, doesn't do disruption. I think we should put disruption in there as an option. And frankly, we should have a toggle because there's different kinds of disruption. Energy imparted disruption versus our standard model for the rest of the community is momentum. The momentum threshold disruption. So that would be interesting to put into the app as well. I agree. In addition to maybe ion beam deflection and other mitigation methods, nuclear as well. Let's try everything, because as you saw on that color diagram, all techniques are applicable. Okay. Almost anywhere on the diagram. The question is, which is the more likely effective technique depending on size and warning time. And so that would be an interesting thing to put in as well.
Yeah. So Paul, I would seek your advice. Now that the software has been completed for phase 2 of the development, the teaming is just a small part of it, just for fun. But it has a feature in which we use a simple equation from Lawrence Livermore that does nuclear detonation above the surface. It is part of the software now. And the other part is the part that you and me worked several years ago, and that is the deflection uncertainty. We modeled that in the app for one specific case, which was used for development. And I think now that the software is pretty much ready for deployment, I will have to send it back to JPL. I don't know who is the right person. Is it Davide or someone there that can do the development of those different uncertainty files, or you can do it? Just give me an advice.
No, I'm just thinking that this is so fun for our little community. Can you imagine this package being appended to some of the games that the young generation plays? For instance, there's what's called it's a Chinese game that the kids are all crazy after, and it's a multiplayer game. And well, I mean, if we go to our generation, we could think of appending this to Microsoft Flight Simulator or something like that. But
yeah. So Madhu, let me answer you. Up to the beginning of COVID, I had 3 years of capstone project with UCI informatics to gamify the app. And so every year they assigned a group of 5 students to take the app and put the physics into what was it called? I forgot the language they used there for gamification. And we got to a certain level in which it kind of started looking like the seeds of a game. It was all voluntary on my part, and it didn't require any investment. But the idea is not new. It's actually an idea that came up early in the development to get more attention to the app. We wanted to retain the physics, and we did, right? The version that we have from the latest version that we had from the students retains all of the basic physics from the app. So it's not really a truly game. The game is just like playing around with surprise appearances of a new asteroid with a certain characteristics that you have so much time to address it, and maybe another one, maybe it breaks into 2 pieces. All kind of things that we discussed today are kind of the kind of things we wanted to put into kind of a game version of it. But my sense is that eventually it will have to be taken by probably some company that can invest in developing the game for it, retain the physics, so that it's not just a game, but it's an educational tool that is fun to play. So that's not a new idea. Phil, do you want to say something about it?
Curveball. Curveball.
Oh, okay. I just wanted to say,
yes.
Talk to Curveball, right? Because
Yeah,
it's
yeah,
a
we
very
looked
popular game.
Yes. We looked at Kerbal and all of that. But COVID kind of killed it. You know, when COVID came, we barely finished the phase that we were in. And after that, it kind of faded away. And, you know, somebody has to pick it up. But
yeah,
Paul,
so bear in mind, so Nahum, just bear in mind, as you know, this app was designed to be really accurate and realistic with all the physics in there from the beginning. And that's kind of incompatible with making it fun and gamifying it and all of that. So it's different purposes. You could write something that would do that wouldn't be physics based, which is fine and would be fun. But this app is supposed to be serious and super accurate. Yeah. You know, you plug in a real asteroid orbit, you're going to get the real results. So it's
believe it or not, Paul, believe it or not, but some of the students were bright enough to put all of the physics, including the partials that you gave us, and all of the files into I forgot now the language that they used, but it's one of those languages that are used to develop games. And we were starting to be creative with inventing scenarios, right? Using the app. So it kind of on its own, maybe randomly come up with some scenario. Here's an object that was just discovered. You have 5 years to do this and this and that. What can you do? And some curveballs from the side. But, you know, we did it. We did some of it. Somebody has to pick it up. It could be curveball.
Yeah.
But for Paul, are you still involved with JPL? Or not at all?
Say again. Sorry.
Are you still involved with JPL? Are you?
Yeah, consultant now. So yes, just send it my way. I have more free time. I'm retired.
Okay, so like you could create the uncertainty files for the other object, and I think Alan retired, right? Who is going to pick up adjusting it to the JPL website?
Well, let's talk.
Okay, so let's talk soon about it. The intent is that the version that you've seen today being delivered to JPL, it will have many additional features, and we just heard about even additional features that would be useful to put into the app. Obviously, behind it, there is some sponsorship that has to be done to put additional features like disruption and maybe slow push approximations, things like that. So we can talk about it, but I think the next big step would be to deliver it to JPL to make it public on their side as well and see how it is accepted. I will say that Brent Barbie is interested in the app for his class that he's teaching at the University of Maryland, and he gave us a few models to put into the app, which was part of the delay. So the app is now ready to be delivered. it doesn't mean it doesn't have any small glitches or something like this that are discovered with testing. So anybody who wants to take up testing the app and tell me, hey, this and this and this doesn't work, this will be very beneficial for us. So for wrap up, maybe everyone on the panel can say last words about today, about how do you see the near-term future, maybe extending it to 2029, when it's going to be the International Year of Planetary, of Asteroid Awareness and Planetary Defense. How do you think the next 3 years should be spent?
Well. Let me say that this was a very interesting meeting. Always excited to see our colleagues and, more importantly, youngsters, and keep that rolling, because we'd like to see more of these students come in and interact. I would like to mention that before we all head out, we want to get a group picture of the rest of the people in the room. If you'd come back after our closing thoughts, we'd love to have a good picture that Ken will shoot for us. Right, Ken? Oh, good.
I think, Madhu, what you said is deserving kudos to Ken, who arranged the collaboration with the school and the teacher and the students. So kudos to Ken.
Guys,
okay.
Come out here and Ken will shoot from the other side. Come on this side. Stand behind us.
But there are people. Have you finished each sharing? Not yet, right?
Not yet.
Each should take a round.
We have to close right at 6.
No.
Okay.
But if you don't take a picture, people will move.
Oh.
I saw each of you should share like.
Last thoughts? Go ahead.
Oh,
Yeah,
last
that's
thoughts. Yeah.
Not yet. Not yet.
Oh, okay. Oh, no.
I thought I said what I wanted to, and keep this going. And I liked Philip's comment that many of these concepts can be, I wouldn't say all of them, but many of them can be kernelized into 10-minute lightning talks. And so then we can have more talks and more fodder for thought, and still make it in time for a one-day conference, Ken. And
yeah, I think repeating what Phil
possibility.
said, lighting talks, not necessarily 10 minutes, but maybe a couple of minutes, and involve more student involvement in order to encourage the next generation of planetary defenders. So things like this are definitely going to be workloads. Okay,
those are my thoughts. And somebody was talking.
Yeah, I just mentioned. I just repeated what you said.
Yeah, those are my closing thoughts.
And I just want to thank all the speakers. Excellent talks. So well done, Ken. Excellent talks.
Joe, what about you? Any closing remarks?
Again, I've enjoyed it. It's gotten me. There's more work to be done on thinking through a larger range of ideas, and thanks for organizing it.
Thank you. Phil, how about you? Closing remarks?
Great job. Thank you so much, Nachum, and everybody. It was really a terrific day. Thank you.
Thank you. Mark, closing remarks from you?
Sure. I did not talk about the hazard to Earth from lunar impacts, and I think that's something that's important to consider in the future.
Maybe you can prepare something for next year, and we'll invite you in, no problem. Anybody else? I think some of the panelists must have left already. Anybody else that are still in the room online that wants to give final closing remarks?
We got the mic for anybody who wants to say anything.
Before I want to show you a plaque. I don't know if Dr. Menemet can see it.
I can see, yeah.
This is actually a plaque our section chair, Louise, and the treasurer, Mr. Lin Jensen. They want me to make this one for you because they have been helping us organizing this planetary mini-con for many years. So this is a special plaque for Dr. Nahum Menemet.
Thank you. I'm delighted.
Thank you.
I'm delighted.
Thank you. Thank you.
Yeah, I'm impressed from the quality of the talks today and the dynamic activity in the afternoon. I think that I don't remember, Ken, when we started maybe 7, 8 years ago, it was a very, very simple, basic conference, mini conference, which evolved into really highly technical and informative talks, much above what we envisioned in the beginning. And so it was, I mean, there's a lot to learn. It's almost like a mini planetary defense conference here where experts actually present their work. The conference, I believe, is recorded. Anybody is invited to observe it, listen to it. So those that are involved with students are encouraged to encourage them to view part of it and attend the conference virtually after the fact.
Will you send a link out? No.
I think Ken will do that. Ken
Ken will.
is
Okay, very good.
yeah,
Thank you.
Yeah, Paul is about to say something. Yeah, we will send a link. It probably tomorrow. It need to be processed after the meeting. But one thing, Dr. Mendel, one thing, as you said, 8, 9 years ago when we started this, there's one thing we haven't done yet, because that I mentioned to you, we're trying to get like AIAA times, like what people say today, get the, the leadership like mayor or governor. That is something we still need to work on,
Yeah, approach the media.
Yeah,
to see
we are
if
still
there
working
is
on it.
Okay. So all of these are good ideas for next year. We'll try to work on lightning talks, on more student involvement, on maybe involving the media, maybe some local politicians or advocates of planetary defense, things like that are something we should consider for next year.
No.
Yes.
One thing that we are all thirsting for is curation of these talks. Now, Ken does an incredible job, editing and putting it up on YouTube. But it'll be beautiful for each of us to send in our slides so that people can take their own time and view them, not only on YouTube, Ken.
Yeah, but this will be great. But understand, some company or a research project have like something.
It's a lot of work.
Yeah, so if you want to share, it's not enforced. If you like to share, you can take some of the slide you feel you can share. And if you don't share, that's fine. We respect that. But if you want to share a few slides, you make it PDF so people cannot modify it. Then we can post on the website. Madhu had this on December 20th for the section Holiday Gathering. So Dr. James Words and some other speaker, they put a few slides and we pile them together. And if it's some data you're still getting funding or is a company secret, just don't provide it. Paul has something to say. Paul wants to say
All I want to
something.
say, if we're at the end, let's celebrate Asteroid Day. Happy Asteroid Day to all.
Happy Asteroid
Go
Day.
spread the word.
Happy Asteroid Day to everyone. Thank you very much for sticking through the entire day. I had a lot of fun. I learned a lot. And I'm sure that some of you, even though you are experts in your field, you have learned a lot from others. So thank you, everyone. Happy Asteroid Day. Safe world. Let's protect it from future impacts. And we'll be in touch soon. All the best to you.
And stay on camera, guys, because we're
stay on
going to get a
camera.
group picture.
Okay.
Stay on camera.
A
All
picture
of you,
time.
come on over.
Okay.
Yes, folks online, stay online, and we'll take group picture with all together.
Okay.
Come right behind that guy. We can stay right here. We can be right here. There are enough people to come behind us.
Great job, Nachum. Thank you so much. It's really excellent.
Thank you, Phil. Thank you, Phil.
It was really terrific. So good.
Yeah. Well, trying to make it a meaningful event with meaningful deep talks by people who are discussing their latest research finding. So it's becoming a little bit more and more academic over the years, So
Yeah,
I'm happy to do that.
these were good talks. They were great. Very, very
Yeah,
good.
yeah. High quality talks by everyone. Okay, so picture time, everybody.
Right over there.
What would the light away with? Yeah. Maybe close that.
It's saying it's so good, that's why it's being like. There we go.
Thank you.
Thank you for your presentation.
All right, thank you.
Thank you all, and see you all at the next conference.
Good night, everyone.
Take care.
Safe
Bye-bye,
world.
everyone. Bye-bye.
Happy Asteroid Day. Bye-bye.
Happy Asteroid.
I'm guessing next time you're adding fresh asteroids to the atmosphere.
Thank you for the talk.
Yeah. No, it's not. I streamlined
your first.
Is there like a subroutine?
Enjoy your.
Yeah, I wrote the code.
Activity?
I assume
It's difficult to put it online.